when
Mm.
you visit Kolkata, I shall try to see
Sir, our president will be joining within couple of minutes. Then we will start our program. And as you know, this is the 58th annual convention of chemists organized by Indian Chemical Society on virtual mode. And in fact, for the last 2 years, under the pandemic situation of Corona, we have been compelled to organize all our programs through this virtual mode, and all the some of the activities already curtailed because of we cannot reach the students as well as the scholastic persons physically. But somehow the courageous president has advised us to continue our program as much as possible through this online process. So our activities like seminars, conferences, students' competitions, as well as publications, everything is running appropriately at appropriate time. And our students, volunteers at different places of the country, they are very much inclined towards the chemistry now. More than 3 crores of Indian students are learning chemistry every day. And since the chemistry, the central science serving every parts of the civilization, and growth indicator of a country is the chemistry. So the Professor Jadhav sir is joined. We will shortly start our program, and I do hope the other members, more than 400 participants today in different sections and sessions will join in their places. Certainly will start. So without delay, I just request our Honorable President Professor G.D. Jadhav to welcome then our advisor, Professor D.C. Mukherjee, former president of the society, will talk about the activities of Indian Chemical Society. So, Professor Jadhav, sir, please welcome the
Yeah,
audience.
good morning to all and welcome to this annual convention of the Indian Chemical Society. I'm sorry for the delay because my son is getting married and I'm in thick of something. Okay, so I had to, also arrange things, and so I'm sorry for this delay. But at the same time, I want to welcome all of you from across the world for this annual convention. And we'll at the very outset, we'd like to pay tributes to Professor Robert Grubbs, the Nobel laureate, who was honorary fellow of the Indian Chemical Society. He passed away on December 19th, in California. So we pay our tributes to him. He was very generous in accepting the fellowship, and I had met him on several occasions. He was given an honorary doctorate by ICS. Then he was also given the Dhirubhai Ambani Lifetime Achievement Award by ICT. And at the same time, we had participated in small business a conference of ACS in United States, because he was also an entrepreneur. He is running a company which makes catalysts, and his work is very well known to all of us. So at the outset, I want to pay rich tributes to Professor Bob Grubbs. And then with this, we will proceed with our regular session. Professor Sinha, will you please take over?
Yes, sir. Yes, sir. So we pay our tribute with 1 minute silence for the Professor Grubbs. So thank you, sir.
Okay.
Thank you. Now, as per our program schedule, I do request our Honorable former President Professor D.C. Mukherjee and advisor to Indian Chemical Society to introduce the program as well as the activities of Indian Chemical Society. Professor D.C. Mukherjee, sir.
Thank you, Professor Sinha. Honorable President, Professor Jadhav, our distinguished past presidents present here,
S. Swaminarayan Sastra.
Professor Mittal, our council members, fellow participants, the Lifetime Achievement Awardees, the endowment speakers, ladies and gentlemen. My proud privilege to sit before you and to say a few words about the activities and about something about the Indian Chemical Society. It is a proud moment for all of us to remember some great names which had been associated with this society. As you know, the society was established in 1924. The three, at that time, very young talents of our country, Professor J.N. Mukherjee, J.C. Ghosh, and S.S. Bhatnagar. While they were studying abroad in London, they took a decision that on going back, they would establish a society, a national society, with their teacher, Acharya P.C. Ray, as the president. On the return, they established the society with the first president, Acharya P.C. Ray, a name which we should remember every morning with great reverence. Since then, the activity of the society is directed in diverse directions. The main activity is the establishment of a journal, is the creation of a journal. The journal was being published by the Indian Chemical Society for a long time, but it is a matter of great happiness to us that with the leadership of our president, Professor Jadhav, this time the journal is now recently transferred to Elsevier, an international publishing house, and that's a great activity. Let me remember with great name some of the presidents, past presidents. P.C. Ray as the founder president, then Gilbert Fowler, Baba Kottar Singh, N.R. Dhar, even the Brahmachari, J.C. Ghosh, H.K. Singh, S.S. Bhatnagar, J.N. Mukherjee, Hriday Ranjan Ray, Mata Prasad, Professor Biresh Chandra Guha, Professor T.R. Sheshadri, Soyed Tasin Jahir, Jagadish Shankar, T.R. Govindachari, R.C. Mehrotra, D. Noshipuri, D.S. Bhakuni, all these great names which are no more with us. And there are many friends of mine. We are happy that they are with us now. Professor Mittal, Professor Tolapatro, so I pay my respect to all of them. Professor S. Yameta, I pay my respect to all of them. They have done a good job for the society. We organize this annual convention of chemists, as we all know. We publish a periodical on education, chemist education. Occasionally, we organize some seminars. Some of the past secretaries are Professor Sushil Mukherjee. He is very well known to us. Professor B.N. Ghosh, our teachers. He was the past secretary. And all these great names, they have done a lot for the society. And one point I want to emphasize, that this is a national society and our national duty to do something for the society. It is the first chemical society in India. And if we come forward to give our service, to render a great service to the society, we should all be very serious. So as a very senior person, my fervent appeal to all of you that you please be serious to render your kind services for the amelioration of our society. this year, very good lectures have been arranged. We are going to felicitate the great talents of our country by giving the Lifetime Achievement Awards. Many good endowment speakers will deliver the lectures, and I'm sure that the convention will be a grand success. With this hope, I offer the best of my wishes to all of you. Thank you very much.
So I don't have any words to thank Professor Mukherjee, who is our constant inspiration. At the age of 85, almost every day he is spending 12 to 13 hours for academic activities, and certainly within this academic activity he has 3 to 4 hours for society. Every day he is visiting the Indian Chemical Society office. Now,
Thank you.
now our President Sir, Professor G.D. Yadav Sir, I do request him to address his inaugural speech on opening of
Thank
book
you.
of abstract and
Thank
our
you.
chemical.
Thank you so much, Professor Sinha. Professor D.C. Mukherjee gave a background of the society. Ladies and gentlemen, you know, the society has to do things collectively. And we will be entering into the centenary year of the society next year. And we'd like to do it with gusto from 9th May 2020. So what we have done is that the current council will be the members of the National Committee for celebration of the centenary of the society. And we have planned many different things because we have to, honor the legacy of our Acharya P.C. Ray. It is my personal desire that, and also efforts are underway, that the Prime Minister of the country or the President of the country should, be invited during one of those days. I cannot, tell the date because it depends on their availability and their schedule for, this centenary celebration. It is also our desire to have August 2nd as the National Chemistry Day, and efforts are also underway. And so I think in this regard, all the regional chapters, colleges, universities, IITs, NITs, and whatnot, wherever there is chemistry being taught, they should organize, the different kinds of programs which are, are contemporary, and maybe they can have a half a day seminar or one full day seminar, or sometimes maybe 2-day or 3-day seminars throughout the year. And that is one of the ways of making our society known to everybody. That is our desire, and I'm sure we will do it. Another thing is that I've been writing to industry to support many of these awards. You know that we have this many memorial awards, and we need support for that. So we'll approach the industry to support some of these awards where the money is short, so that the interest, half of the interest could be used for as an award money, and the remaining half will be plowed back into the corpus of that particular award. So we are going to do that. Perhaps you know that we have been publishing the Journal of Indian Chemical Society from the very beginning, and Acharya P.C. Ray was at the forefront. He was the editor-in-chief. Now it is a fortuitous coincidence that I have been the president, as well as I'm, editing the Journal of the Indian Chemical Society with 6 editors, renowned editors, and 56, advisory members of the International Advisory Board. So it is very good. In fact, the impact factor of our journal has gone up. And I would like to mention to you some statistics which will tell you about the standing of our journal. We have accepted 296 articles so far, rejected 589 articles, 25 articles were withdrawn, 3 articles were transferred, and 43 articles have gone for revision. So what it means, do not assume that if we submit to the journal, it will be accepted, because the standard has to be increased, and it is us who are going to do that. And at the same time, every day there are 3 to 4 articles which are submitted to the journal. So I'm very happy that and we are publishing ahead of time. So we must thank, Elsevier for providing us this great platform, and we are going to make use of it fully. At the same time, I would appeal to the fellow members and fellows to submit good quality articles to this society journal. That will enhance the prestige. This, journal is available as a part of freedom subscription by Elsevier. So many universities and libraries across the world are, having access to our journal. At the same time, anybody who becomes a member or a fellow new member, they have to pay a subscription for 5 years, and there are different rates. And that is being, fully implemented by them. There are special rates for the libraries who are not members of the freedom subscription. So this should be remembered. At the same time, we are trying to see that the building of the society is built with the help of all stakeholders. The state government is involved, DST is involved, and we have to generate funds. So we are trying to find out different ways by which we could, build this building, and efforts are underway. I would also like to tell you that, the society is also publishing, the Chemical Varta, which is, a sort of news bulletin. And, the additional publication is also being published, where, we have a new advisory board and editorial board. And some details of that will be, given to you later. Ladies and gentlemen, I thank all of you for joining this morning session today. And I'm sure we'll have many things in future. At the same time, it is my pleasant duty to, inaugurate, open the book of abstract, and that I'm going to do shortly. Okay, so I will click on that. So let's, Professor Sinha.
Yes, please, sir.
Yeah, you can show this book of abstract. I have in
Yes,
front of me, but then I'll have to put it on the screen.
Okay, sir, I'm doing it.
Please do it. From your end, please do that. The book of abstract, and also education in chemical science and technology. Okay, that I would like to open. So please bear with me.
Is it visible, sir?
Just 1 minute.
It's coming up.
I think it is visible now. It is visible.
Yeah.
Yeah.
You need to make it on the slide mode.
Yeah, please.
See, this is, in fact, it is difficult to get since it is fully in the book form, page-wise. Just I'm showing you still, I think it will be around 500 pages book, only abstract book. And is consisting of 9 different sectional presentations as well as lifetime achievement award citation and their abstract along with endowment awards, invited awards abstract and plenary awards abstract, along with the abstracts received for general presentation and award presentation, both in the form of oral as well as poster in the award format as well as in the general format. So it is a very mega event on behalf of Indian Chemical Society, such a big event and such a big abstract book we have not published yet. And different branches of chemistry, organic, biochemistry, inorganic, material, physical chemistry, theoretical chemistry, environmental chemistry, chemical engineering, green technology, analytical chemistry, industrial chemistry, applied chemistry, and many other branches of pharmaceutical chemistry, all sorts of chemistry branches are being published in this book. And this will be available in our website, and those who are the contributor, they can easily access to the website freely. Sir, can I continue the...
Yeah, please go ahead. Please go ahead.
Okay, sir. Okay, sir. Since it is very difficult to, within this time limit, to go every page.
No,
sir.
you don't have to. You're given a glimpse, so you can cut it short now. Incidentally, I also want to mention, dear attendees, that previous issues of the Journal of Indian Chemical Society will be freely available on the website and then Science Direct. We have got donations to digitize it. It will have DOI numbers. In fact, part of the work has already been done, and we will go in the reverse order. So that is another great thing which is happening, so that people can access those back issues freely on the website. And that link will be provided in Science Direct. Our journal is available on Science Direct.
Okay, let me to stop this presentation, sir.
Yeah, please go ahead. Please stop it and start.
Sir, then you open this chemical education.
Yeah, please do that.
Right. And if I have to do the presentation?
This is one periodical. It's publishing by the society since 2013. During after the advice of Dr. T. Ramasamy, the then DST secretary, and after with his ambitious project of publishing this educational journal, educational periodical, Education in Chemical Science and Technology. This name is given by Professor Animesh Chakraborty during this time, and it's continuing. And we are going to publish this periodical in the book form, and we received the ISBN number. And very recently we are going to institute one journal, education journal, education in chemistry and research, chemical education research. We are waiting for the ISSN number, and then the publication of this periodical will be stopped. But we will continue the publication of the chemical education related book. And in this issue, you can find in Education in Chemical Science and Technology. This is edited by Professor G.D. Yadav as President, C.R. Sinha as Honorary Secretary, and Dr. Biswajit Pal, Dr. Gauri Shankar Rai Mahapatra, and Dr. Soumitra Dev as Honorary Editors. And this issue contains uh, 10 articles. 10 articles. Article 1, Importance of Catalysis in Grid Chemistry, published by D.V. Prabhu. And the objective of this publication is to bridge between research and the teaching, since after completion of master's course, students are becoming afraid to join any research group, which type of research he will receive or where he will go. That type of information is available with reference to their present status. And framework chemistry, renovating our insight into the chemical sciences, by Chitranjan Sinha. And the next one by Sagar Pal from IIT ISM Dhanbad, polysaccharide-based hydrogels in controlled drug delivery applications. And next one, an introduction to composite material by Rajarshi Maiti, Sabir Ali Khan, Timir Baran Sinha, Shivaprasad Maiti, and Piyush Kanti Khatwa, and so on. And these 10 articles are published here. And this, in fact, useful for the students, those are willing to participate in their higher education. And let me to talk about the Acharya Rai's one quotation that is published in the back volume of this book. While a student at Edinburgh, I found to my regret that every civilized country, including Japan, was adding to the world's stock of knowledge, but unhappy that India was lagging behind. I dreamed a dream that, God willing, a time would come when she too would contribute her quota. Half a century has since then rolled by. My dream I have now the gratification of finding fairly materialized. A new era has evidently dawned upon India. Her sons have taken kindly to the jealous pursuit of different branches of science. May the torch thus kindly burn with greater brilliance from generation to generation. His dream is now materialized, and this torch is now kindled with greater brilliance. So, thank you, sir. Thank you for your kind presence and opening of this book.
Thank you. Thank you, Professor Sinha. If I'm not mistaken, the next will be the presentation of the Lifetime Achievement Award.
Yes, sir. Yes, sir. Yes, sir.
So, you know what I will do? I will announce the names of the awardees, and Professor Sinha will read the citation. So, first and foremost, the first lifetime, there are 3 Lifetime Achievement Awards. And I'm indeed very pleased on behalf of the Council of the Society and the Fellows to congratulate Professor Sridhar Gadre, in recognition of his lifetime achievement in teaching and research in the field of chemistry. Particularly, he is well known for theoretical and computational quantum chemistry. I have known Professor Gadre for a number of years. No words can describe his simplicity, humility, and the kind of impact he has made on our profession. So, Professor Sinha, will you please read his citation, and then we confer upon him this Lifetime Achievement Award virtually.
Okay, sir. Okay. Professor Sridhar Gadre, FNA, Lifetime Achievement Award 2021. Members of the Council and the Fellows of the Indian Chemical Society feel highly honored to felicitate Professor Sridhar Gadre in recognition of his lifetime achievement in teaching and research in the field of chemistry in general and theoretical and computational quantum chemistry in particular. Professor Gadre received his undergraduate and master's degrees at the University of Pune. He did his PhD with Professor P.T. Narasimha at the Indian Institute of Technology, Kanpur, India. following his PhD, he did postdoctoral research work with Professor Robert Parr at the University of North Carolina and Robert Macha at the University of Houston. During his postdoctoral work, Professor Gadre carried out research in density functional theory and on rigorous inequalities in quantum chemistry. Professor Sridhar Gadre has made significant contribution to theoretical and computational quantum chemistry. These belong to two main research areas, studies of atomic and molecular scalar fields and the development of a method of ab initio investigations of large molecules and clusters. Which noteworthy research under the first area includes pioneering topological investigations on molecular electron momentum densities and electrostatic potentials MESP. The latter provides proofs of two basic general theorems on MESP, definitions of lone pairs and aromaticity, as well as the treatment of substituent constants and aromatic sextets via MESP. And his works on Shannon entropies in position and momentum spaces for atoms and molecules leading to a new maximum theory entropy principle are also widely recognized. Under the second area, his group formulated a fragmentation-based method called as molecular tailoring approach, MTA, and a parallel code for implementing it. The method has been applied for geometry optimization and calculation of vibrational IR and Raman spectra of large molecules. This group reported several applications of MTA to large molecules and weakly bound molecular clusters, as well as an MTA-based algorithm for a direct and reliable estimation of intramolecular hydrogen bond strengths. For his contributions, Professor Gadre was elected Fellow of the Indian Academy of Sciences in 1992 and the Indian National Science Academy in 1996 and received the prestigious Shanti Swarup Bhatnagar in chemistry in 1993. A dedicated academician, Professor Gadre has contributed significantly to the development of chemical education and research in the country. He has built up a vibrant school of chemists and inspired a large number of students and colleagues who are carrying torch of his mission. Sorry, sir. He has built up a vibrant school of chemistry and inspired a large number of students and colleagues who are carrying the torch of his mission. The Indian Chemical Society sincerely wishes Professor Sridhar Gadre a long, peaceful life with sound health and continuous academic activities for the achievement and propagation of scientific knowledge. Professor G.D. Jadhav, President, Indian Chemical Society, Professor Chittaranjan Sinha, Honorary Secretary, Indian Chemical Society.
Yeah, thank you.
The Society will send the bound citation along with the medal.
Okay.
Yeah.
Since Professor Gadre will be speaking, giving a lecture, so he can say, he's accepting a speech at the time of his lecture.
Okay, thank you.
Yeah. So the next award is given to Professor Arbinda Kumar Das. Professor Arbinda Kumar Das is a very well-known chemist, and I've known some of his work in environmental chemistry and green chemistry. So we'd like to, recognize him, and I request Professor Sinha to read the citation.
Yes, sir, I'm sharing it. Indian Chemical Society Lifetime Achievement Award 2021 conferred on Professor Aurobindo Kumar Das. Members of the Council and the Fellows of the Indian Chemical Society feel highly honored to felicitate Professor Aurobindo Kumar Das in recognition of his lifetime achievement in teaching and research in the field of chemistry in general. Professor Das received his undergraduate and master's degrees at the University of Calcutta, Kolkata. He did his PhD at the Yadavpur University, Kolkata. He was a teaching and research associate at the Ohio State University, visiting researcher at University of Valencia. Professor Das has made significant contributions to the metal ion speciation in diverse matrices, correlation of trace metals variation upon low dose radiation on human, low cost methodology for arsenic and other heavy metals removal from drinking water. Professor Aurobindo Kumar Das was the pioneer in introducing the environmental chemistry in 1980 and the green chemistry in 2009 at the postgraduate level of studies. He had rendered stupendous service at the University of Kolkata, West Bengal as the Vice Chancellor 2004 to 2009. He has published more than 175 original papers, reviews, and invited articles. Professor Das is the author and co-author of a dozen of higher-level books on bioinorganic chemistry and green chemistry. He is an activist of People's Science Movement and wrote numerous articles on popular science. For his contributions, Professor Das was elected Life Member of Indian Chemical Society, Honorary Fellow of West Bengal Academy of Science and Technology. A dedicated academician, Professor Das has contributed significantly to the development of chemical education and research in the country. He has built up a vibrant school of chemists and inspired a large number of students and colleagues who are carrying the torch of his mission. The Indian Chemical Society sincerely wishes Professor Aurobindo Kumar Das a long, peaceful life with sound health and continuous academic activities for the advancement and propagation of scientific knowledge. Professor G.D. Jadhav, President of Chemical Society, Professor Chittaranjan Sinha, Honorary Secretary, Indian Chemical Society.
Professor Das, hearty congratulations.
Thank you very much. Thank you. Namaste.
So he will give his acceptance speech as well as a lecture in this convention. So we move to the third, award, and that third award is given to, Professor Dr. Rakshavir Jasra. He is a senior vice president at Reliance Industries Limited. And so Dr. Jasra is known for development of several technologies and contribution to catalysis science and engineering. So I request Professor Sinha to read his citation.
Thank you, sir. Indian Chemical Society Lifetime Achievement Awardee 2021 conferred on Dr. Rakshavir Jasra, FNA. Members of the Council and the Fellows of the Indian Chemical Society feel highly honored to felicitate Dr. Rakshavir Jasra in recognition of his lifetime achievement in research in the field of catalysis, adsorption, petrochemicals, nanoporous materials. Dr. Jasra has made impactful contributions to chemical, defense, agricultural, and human resource development sectors of our country by developing and commercialization of innovative technologies and products. Dr. Rakshavir Jasra is presently the Senior Vice President R&D of Reliance Industries Limited. Previously, he was the Director Grade Scientist at Central Salt and Marine Chemicals Research Institute, Bhavnagar. He has led R&D groups for the last 2 decades, and developed over 50 and commercialized 16 technologies. He has published 281 research articles, including 6 chapters in books and 7 review articles in national and international journals of repute. He has also 64 patents to his name, including 24 US patents with 50 patents in process. For his contributions, Dr. Jasra has been elected the Fellow of Indian National Science Academy, Indian National Academy of Engineers, Gujarat Science Academy, and Life Fellow of Indian Chemical Society. Dr. Jasra is the recipient of many individual and team awards like Professor S.K. Bhattacharya Eminent Scientist Award by Catalysis Society of India, Bhasbig Award, Professor K.G. Naik Gold Medal by the MS University of Baroda, Bronze Medal by CRSI, 5 national awards from Ministry of Chemicals and Fertilizer Government of India for innovation in polymers and elastomers. Dedicated academician and professional scientific personnel, Dr. Jasra has contributed significantly to the development of technologies in different sectors like chemical sector, defense sector, agricultural sector of our country. He has built up a vibrant school of professional scientific personnel and inspired a large number of students and colleagues who are carrying the torch of his mission. The Indian Chemical Society sincerely wishes Dr. Raksbir Josra a long, peaceful life with sound health and continuous academic activities for the advancement and propagation of scientific knowledge. Professor G.D. Yadav, President Indian Chemical Society, Professor Chittaranjan Sinha, Honorary Secretary Indian Chemical Society.
Congratulations, Dr. Chester.
Thank you. Thank you,
See you in
everybody.
person. And I'm sure you are now keeping well.
Thank you. Thank you.
So let us go ahead with the next program, Professor Sinha.
Yes, please, sir. Next program is the address by the Honorary Secretary Indian Chemical Society, Professor Chittaranjan Sinha. Okay. Good morning, everybody, and all the participants present in this virtual mode. Our Honorable President, Vice President, members of the Council and members of the Indian Chemical Society, Lifetime Achievement Awardee, and other invited speakers and the audience. Indian Chemical Society, already Professor Mukherjee told about the history of Indian Chemical Society, how it develops under the scrupulous condition of the countries during the freedom movement. And Acharya Prafullo Chandra Rai, father of Indian chemistry, and who started his venture from Edinburgh University to India. I want to share some of the slides about Acharya Prafullo Chandra Rai, Chemical Society and its activity. This is 58th Annual Convention of Chemists and International Conference on recent trends in chemical sciences for 21st to 24th December of this year. Every year we organized at least 4 events of the Chemical Society. One is this annual convention, where all the members and the participants join with this program. Second is the National Science Day celebration on 28th February, where we organize students' competition and also some presentation. And on the Foundation Day of the Chemical Society on 9th May, and this year we organized the same chemical competition among the students through virtual mode and some lectures. And the August Symposium, that is the August Conference of Indian Chemical Society to commemorate the birth anniversary of Acharya Prafullo Chandra Rai with some presentations and scientific program. And Acharya Prafullo Chandra Rai, a patriot, a nationalistic, entrepreneur, educationist, philanthropist, scientist, and whatnot. He authored 158 research papers. History of Hindu chemistry in 2 volumes, volume 1 in 1902 and volume 2 in 1909, and Life and Experiences of a Bengali Chemist in 1936, and Atmacharita published by Ananda Publishers. About Acharya Prafullo Chandra Rai, Prafullo Rai was the ardent follower of Gandhiji. Mahatma Ji announced that it is difficult to believe that the man in simple Indian dress wearing simple manners could possibly be the great scientist and professor. And this is the Science College, University College of Science and Technology, started in 1915. Sir Ashutosh Mukherjee was the second Indian Vice Chancellor of the first University of India, University of Kolkata. Under his leadership and the leadership of Acharya Prafullo Chandra Rai, Indian Chemical Society started. This is in the Palit building, 2nd floor. This is a small room established. This is also constructed by the contribution of Acharya Prafullo Chandra Rai to Calcutta University. Acharya Rai donated huge amount of money throughout his life to the development of science and technology. Even he donated 1,80,000 rupees during that time to Calcutta universities to start biological science in the University of Calcutta. And then this is our Library of Indian Chemical Society and gateway of the University College of Science and Technology. And this is a small room maintained by the Department of Chemistry, Calcutta University. And this is the pilgrim of chemistry in India, where the Acharya Prafulla Chandra Rai spent his whole life in this room with his belongings and bed. And his relationship with the national movement, this national movement, since he was the government employee in Presidency College, that's why he directly could not join in the national movement. But at the latter part of his life, after 1915, he joined directly in the national movement. And he was the great admirer of Gandhiji. So throughout his life, he used this charka. And if you, with the Bengal Chemical, which is the finest establishment during that time, and that Bengal Chemical has also a national contribution in the freedom movement. And that Bengal Chemical, at one hand, is making charka, on the other hand, they are providing revolver to the nationalistic freedom fighters. And the contribution of Acharya Rai, a history of Hindu chemistry, this is the only historical development recorded by Acharya Rai, where he had shown how ancient India is so powerful in science and technology. Some of the evidence is still available in Delhi. This Qutub Minar having the iron pillar, still it is rustless. What technology they have used. And India is the first country that isolated iron and zinc. India is the first country that prepared alcohol, that is the elixir of life. And this is being recorded in history of Hindu chemistry. During his time, he was being severely criticized because of this terminology Hindu. And he clarified it. Hindu is not the religion, Hindu is the culture. And his finest contribution is the establishment of the Indian Chemical Society and its journal. Every day, our Professor Mukherjee has reported that every day and every moment we are remembering Acharya Rai through our scientific activities and his Bengal Chemical and his discovery of mercurous nitride and some thiocamphors as well as thiacrown ethers. This crown ether received Nobel Prize to Jean-Marie Lane and Pedersen Kramp in 1987, but Acharya Rai reported it in 1934. And this mercurous nitride created a lot of debate, and many of the Indian scientists did not believe its existence, while the Professor Animesh Chakraborty prepared the same compound following the same procedure, and it is X-ray characterized. And chemistry, higher education in chemistry started from Presidency College in 1872, and the postgraduate chemistry teaching as well as its research started in Presidency College in 1885. And Acharya Prafulla Chandra Rai learned his chemistry from Alexander Petler and Alexander Cram Brown. When he was the student of IEA in Metropolitan Institution, that is now in Vidyasagar College, but he joined in the classes of Alexander Petler in Presidency College. Alexander Petler was the first chemist of the country who published a scientific chemistry paper in the Asiatic Journal of the Asiatic Society. And second paper was published by Acharya Prafulla Chandra Rai. And the third paper, that is the second paper of Acharya Prafulla Chandra Rai, that consists of mercurous nitride. And this mercurous nitride, already I told you about its problem and its future. And this is Acharya Prafulla Chandra Rai started this chemistry research in the country along with its chemical establishment of Indian Chemical Society. They are the associates during its time. J.C. Bose, S.S. Bhatnagar, P.C. Mitra, and Jain Mukherjee, Fowler, Limson, and they associated with him to develop this Indian Chemical Society in the country. When the Journal of Indian Chemical Society came in the daylight in November 1924, the Nature London reported the great work in chemistry which has occurred in the Indian Empire during the past 10 years had led to the establishment of an Indian Chemical Society. The first number of the quarterly journal of the society has now appeared, There are 13 papers and only one of these is published under the English names. The remaining papers are published by Indians and come from all parts of the Indian Empire. 4 of these emanate from the College of Science, Calcutta. And this is as it should be, because of many years past, this institution has been the backbone of chemical research in India. And the first volume of Journal of Indian Chemical Society, published in 1924 November, this is now in our office, and the publications, and now present form. As you know, this there is a long story about the evolution of this Journal of Indian Chemical Society in different forms, and the present form is available in the website of the Elsevier, the Journal of the Indian Chemical Society. Already this has been reflected by the talk of our president and former President Pranab Mukherjee. And the Chemical Education Journal, Education in Chemical Science and Technology, that is open today, that makes a bridge between the scientist and the students. Students during his master's course, even they are in a conflict situation in which area they will be researched. And the modern area of research will be focused in the education periodical. And other activities of the society. Society is everyday, society is remembering Acharya Prafulla Chandra Rai. This is one place where Acharya Prafulla Chandra Rai started the Bengal Salt Company. Under his leadership during Dandi Abhijan of Gandhiji, Acharya Rai started this Bengal Salt Company in nearby Digha in West Bengal. And one of his disciples, Manoj Datta, who started it. And Acharya Rai visited this company at the age of 80 to train the laborers how to make a good quality crystalline salt. And we are, unfortunately, we have a land given by the government of West Bengal in 1967. This is nearby our office. And not only far away, it is only 1.5 kilometers from our office now, Raja Bazar Science College. But we could not establish our own building of Acharya Bhavan. And there is many types of problems. The hawkers thing of occupied the boundaries, and nobody can enter into this periphery. And our present president, fortunately, he is trying best to recover this land and to establish the Acharya Bhavan, the own building of our chemical society. So now the chemical society is growing in different aspects. Already I told you we have the 8 chapters in our country: Bhagalpur chapter, Chennai chapter, Raipur chapter, Baroda chapter, and our Mumbai chapter, along with the Northeast new branch has already started their work and will be continuing their work in future. And with this chapter, one of my intention or the dream is that every state of our country could have one chapter with reference to Indian Chemical Society. Although the big country of 130 crores of people, where the 3 crores of students are learning chemistry in different ways, so to cater the need of the students, Indian Chemical Society has to reach the students every day in different ways. And already our president told you that he is trying best to make a National Chemistry Day as the Acharya Prafulla Chandra Rai's birthday. Meanwhile, I have one request to our president as well as to the chemistry fraternity. You know, there is no national chair in the name of Acharya Rai. Although Acharya Rai is the teacher of all scientists during that time, there is J.C. Bose, who was the friend of Acharya Rai, while the S.N. Bose, Meghnad Saha, P.C. Maulanavis, they are the students of Acharya Rai. In their name, there are many chairs in different institutes as well as in DST. I do request our president sir as well as other powerful chemists of the country to have a national chair in the name of Acharya Prafulla Chandra Rai. And a few years back, only NASI, National Academy of Science in India, started one Acharya Prafulla Chandra Rai lecture. And also, there is no higher institutes, only few colleges in the country, particularly in the West Bengal, in the name of Acharya Rai. Although you can find the largest number or the highest number of statue of Indian scientist if you find in the country, it will be of Acharya Prafullo Chandra Rai. So I do request to the honorable chemist of the country as well as our president to establish at least one higher learning research institute and the chemical hub in the name of Acharya Rai, so that every day they can remember the contribution of Acharya Rai for the larger benefit of the country. And also, with these our intention of Chemical Society, I do request to join with this program, and I request to all of you to read at least these two books. You may read the history of Hindu chemistry. You can go through the website. You can download the first volume. It is freely available. By life and experiences of a Bengali chemist. It is his love to Bengal. That's why he writes the Bengali. But it is not that. It is related to the freedom movement and the contribution of a scientist towards the national movement. And every detail is there. It is published by Asiatic Society in 2 volumes, and also another book published by Indian Chemical Society, which is written by Professor Animesh Chakraborty, a glimpses of Acharya P.C. Rai's work in chemical science, and where he enumerated the activities, research activities of Acharya Rai. Still, those are very important today. And finally, the Royal Society of Chemistry had given this plaque, considering Acharya Prafullo Chandra Rai as father of Indian chemistry, philanthropist and entrepreneur who founded modern chemistry teaching and research in India. And our courageous leader of Indian Chemical Society, Professor G.D. Jadhav, with his courage and advice, the Chemical Society is progressing now. And this is, they are the honorary members. Those are out of them, Professor Grafs have died. All these members from different parts of the world. Professor Richard Roberts, Professor Noyeri, Professor Venki Ramakrishnan, Professor Stoddard, M.M. Sharma, R.M. Maslekar, Vijay Raghavan, Sukumar Banerjee, Ashutosh Sharma, Renu Sarup, Colin Suckling, Eric Jacobson, Mukesh Ambani, the Raju Bhai Ashraf, all they are the honorary members of the society. So society is now approaching towards a glorious time of to achieve the ancient glorious times of the country. And the Lifetime Achievement Awardee, Professor Gadre, Professor Rabindra Das, Professor Rakshit Josra, already known to you. And still there are lifetime endowment awardees, endowment awards. We have 21 endowment awards, and still there are 3 endowment awards are cleared by the council, like in the name of Professor Sadhan Basu Endowment Award, Professor Asima Chatterjee Endowment Award, and Professor T.R. Seshadri Endowment Award. And our Honorable President has taken a challenge to collect money to fund for the establishment of this endowment award. Besides that, the Young Scientist Endowment, Young Scientist Award in the name of S.S. Bhatnagar is running in our society. The endowment award is like Professor Amitabh Chattopadhyay from CCMB, and Professor Pradhat Ghosh from ISCS, Professor S. Kotha from IIT Bombay, Professor Sujit Ghosh from ISCS, Professor Jhanjau Guo from USA, Professor Samal Kumar Chattopadhyay from IIST, Professor Purushottam Jena from USA, and Professor S. Vasudevan from Sikri, CSIR Institute, Professor Asit Baran Panda from CSIR Institute, and Dr. P.A. Hassan from BRC, Professor Shiva Umapati from IJR Bhopal or IIC Bangalore, Dr. Mukul Shankar Chorgade from USA, and also Dr. B.V. Subbareddy from Hyderabad, IICT Hyderabad, Professor Dipankar Das Sharma from IIC Bangalore, Professor Devabrata Maiti from IIT Bombay, Professor Surajit Chattopadhyay from Kolkata University. They are the recipients of different endowment awards, and they will present their work along with the plenary lectures, plenary programs will be there. And this is the present 2 days program, or the annual chemist 58th annual chemist conventions program in 9 different places. You know, this physical chemistry in Calcutta University, organic chemistry in IIT Kharagpur in association with IIR Kolkata, physical chemistry is associated with Pandit Ravi Shankar University, inorganic chemistry with in IIT Guwahati in association with Yadavpur University, chemical engineering and green technology in ICT Mumbai, analytical chemistry in Baroda University, MS Baroda environmental chemistry in IIT Ropar, industrial and applied chemistry at IOCL Faridabad, and Asima Chatterjee scientific session in JNU Delhi, and young scientist conclave in Hyderabad University. And so they are contributing, they are participating in different ways with this convention, and they are the in this convention, the programs are conducted by committees. The Asima Chatterjee scientific session was conducted by Professor Kasturi Mukhopadhyay, JNU, along with Professor Chanda Mukhopadhyay, Professor Bimlesh Lochap from Signadar, and this analytical chemistry section was conducted by Professor Arun Sawant, along with Professor R.N. Jadeja and Dr. Kamalika Sen. Organic and chemical engineering and green technology is conducted by Professor Virendra Kumar Rathod, along with Professor Bhanage and Dr. Vijit Ghosh. Environmental chemistry section is conducted by Dr. Sanjeev Kati. In fact, every activity is being in environmental chemistry taken by challenge by Professor Dev-Prasad Mondal. Professor Sanjeev Kati is quite busy in other way, and Professor Praveen Ramurthy, Dr. Sarath Lande, and in industrial and applied chemistry in the leadership of Dr. S.S.V. Ramakumar, along with Deepak Saxena and Dr. Gauri Shankar Rai Mohapatra. And inorganic chemistry section is conducted by Professor Saurabh Das in association with Chandan Mukherjee, with the advisor of Professor Samaresh Bhattacharya. Organic chemistry is conducted by Professor Deepak Bala, scientist in charge, and Professor Alokesh Bishoy and Samik Nanda, along with other members. And physical chemistry conducted by Kallol K. Ghosh and Nikhil Guchait and Dilip Kumar Maiti. So this is the all about the Chemical Society's activity. And I do request you all to be a member of this Chemical Society, to execute the dream of Acharya Prafulla Chandra Rai and to host the flag of Acharya Rai in the global scenario. So for the next 3 days, you will enjoy in the different sections, and this parallel session will be conducted, and all the informations are available in our website. And I think you will go through our website to get the information, or you can contact with us for getting them. So with these few words, I just request you to be a member of this vibrant society and to uphold the flag of industry. Thank you, sir, for giving this opportunity. Thank you.
Thank you, Professor Sinha. Now I request Professor Das to propose the vote of thanks.
Thank you, Professor Jadam. Good morning to all. I feel honored and privileged to get the opportunity to propose a vote of thanks on the special day in the inaugural program of the 58th Annual Convention of Indian Chemical Society and the International Seminar. Respected Professor Jadhav, President, Professor Mukherjee, past Presidents, Professor Sinha, Honorary Secretary of the Institutes, all the awardees, particularly Lifetime Achievement awardees, Professor Sridhar, Professor Das, Professor Hazza, and other memorial lecturers, endowment awardees, and other awardees, invited speakers, scientific in charge and their associates, honorable council members, and respected professors, and the students of different universities and colleges in India and abroad. I am grateful to Professor Mukherjee, past President. In his address, he made the tune of the convention. We are thankful also to Professor G.D. Jadhav, President, for his address. We are also thankful to Professor C.R. Sinha for his address. Now I'd like to make a small announcement that we have, on the behalf of Indian Chemical Society, we have successfully completed 2 internship courses for the students. That is, first one is process safety and environment, and second one is nanotechnology, its application, characterization. Now Indian Chemical Society decided to hold an internship program on petroleum, upstream, downstream, and feedstock for petrochemicals. These courses are meant for the students of different levels, BSc, MSc, BTech, MTech, PhD, and also for industrial personnel. So on the behalf of Indian Chemical Society, also my behalf, I convey my regards and hearty thanks to all of you present here. I also thankful to the different institutions who are organized the different days, programs, or in different subjects. So again, once again, on behalf of myself, behalf of the Indian Chemical Society, I convey my regards and heartiest thanks to all of you present here and enjoy the next 3 days. So thank you all.
So I do request our President Sir to conclude this inaugural session.
Yeah, thank you, Professor Sinha. We conclude the inaugural session now, and immediately we start with the Lifetime Achievement Awardees presentations. And the first presentation in that is by Professor Sridhar Gadre. May I request Professor Sridhar Gadre to make his presentations?
Yeah, Professor Gadre, may I present your slides? Or
Yes,
will you-
please. Yes, please. Till the slides come on, at the outset, I would like to thank the Indian Chemical Society for bestowing upon me this honor. And I also congratulate other awardees on this occasion. I greatly value this honor because this unique institution, namely Indian Chemical Society, was founded by great chemists, and it was nurtured after that by, again, stalwarts in chemistry. This was nicely summarized by Professor Mukherjee this morning. So without any further ado, can I have the slides full screen?
Yes, sir, it is full screen.
There is some trouble. I'm not getting full screen.
Yeah, it is not yet full screen.
Yeah.
Is it now?
Not yet. Not yet.
Is it beyond the screen or it is small
No,
on
no,
the
it
screen?
fits on the screen perfectly. I show this in it is just 3/4 slide that I am seeing.
Go for
Otherwise,
option.
Oh,
Use options.
okay,
view
that means it
options.
has to be.
Mr. Sinha, you click on the full screen option, F5 or the full screen.
Is it visible? Full screen?
Slide is visible, but it's not full screen, as already mentioned by Professor Gadre.
No, this is full screen in my case, but it may be bigger than that.
Anyway, it doesn't matter.
It is a full screen,
Let's
but
see.
can be still bigger. Yeah.
Yeah. You
Let
can
us
make
go for the view
slideshow
options.
mode.
Well,
Go for
I
options.
use
Full
this-
screen.
Okay, let me to stop and then.
Maybe you can go for options in the view. You understand it? Yeah.
What about now?
Same as before, but anyway, we can go on.
Acha.
Sir,
You
go
will
to the
not see
menu
my-
slideshow.
Yeah, this is in slideshow. This is in slideshow.
No, it's just you have to go to this place. Third.
Now you can see. Directly coming from its side.
Yeah, now you can open the PowerPoint.
Yes, sir.
Not yet.
Please open the PowerPoint. Now it is in the file.
Open file.
I'm showing it from laptop.
Yeah, it should work from laptop
So
also.
just click on the file. You had just brought the file. Just click on that. I think should be.
This is the ultimatum, sir.
Okay.
Let's
Sir, I'm changing the slides. Have you seen it?
Yeah, it is seen, but better than last time. It is better than
No,
last
but sir, the slides are not changing. It is
No,
in the
it
first
will
slide
be
only.
changed.
I show it every time.
Right.
Anyway, it doesn't matter.
Is it changing slide? Second slide now.
No, sir.
No,
Huh?
no,
I don't see.
no,
second.
no, Professor Sinha, no.
Okay.
Now it
Okay,
is
okay.
changing.
Now, yes, slides are changing, but it's not full screen, unfortunately.
No, it will not be.
Okay.
Then, is it okay? I
No,
think.
then,
better.
then it will go out of the window, sir. If you zoom too much,
Yes.
it will go out.
This is better. Roll it down here.
Yeah, anyway, I show the same slides and they work, but anyway, it doesn't matter.
But sir, slides are not full screen.
They are full screen on my laptop.
No, doesn't matter.
It can be at your laptop, but we are not getting full screen slide.
Anyway, okay.
This is slideshow, sir.
Try to click on the book, in the below. Try to click in that.
That below.
Yeah. There.
Next one.
Yeah, it is not changing.
Next one. You can see the book.
Is it moving? Is it moving?
No,
No, sir.
you need to click the next one. You can see the in the down, the middle one, the book form, so that it will be enlarged. Not this one. Not this one.
Is it?
No. Next one. Next to next. Next to next.
It's
From beginning,
Yes, yes.
slide.
bottom.
and custom slide.
You can
The
start
bottom.
from beginning. Or you can
Second from the right.
Second from the beginning.
Yeah, second from the right.
Yes, this one. Right or left?
Second
Right.
from the right side.
Second.
It's in book shape.
Yeah, book shape. No, down.
Down right in the corner.
Yes, that is I'm doing it.
No, next one. Next one, you can see the book. Yes, this one. Yeah,
Yeah.
Yes.
Okay.
now it's better.
Yeah, this is better than before. Yeah.
Yeah.
I think you should go ahead now. Let's go.
Yeah, can I start, please?
Yeah, and
Yes,
one
sir,
more
yes,
thing
sir.
I would like to tell everyone, you need to set this from your screen so that you can set as a full screen. Then you will be able to see it completely, right? You can see there are 3 dots are there, and go to 3 dots and then change layout, go to layout, and layout you can check this one, spotlight. So once you click in the spotlight, you can see in the full screen. Is everyone got it?
Yes, sir. Yes, sir.
Yeah. From the 3 dots, you can click and then you can go to the change layout. And from change layout, you can select either sidebar or spotlight. So then you will be able to see this slide in your full screen. Is everybody got it?
Yes, sir. Thank you, sir.
Yes, yes.
Okay, please go ahead.
Yes, yes.
Okay, can I begin?
Yes, sir.
Yeah, okay. So what I'm going to present to you today is a summary of the work done from my group. We have called it Molecular Tailoring Approach. I'll tell you the reason why we chose that title. And it enables treatment of large molecular systems, including clusters. My group has been developing this, and I'll run through briefly the history of how. Can we go to the next slide? Yeah, as I said, I am thankful to the Indian Chemical Society for bestowing upon me this honor. And it gives me further inspiration to do more work in this area. Thank you. Next. Yeah, I would like to acknowledge these 2 institutions where I could do all this work during my lifetime. On the left, you see the tower, which was not originally the university building. British built it for the summer residence of the governor, and it served as the main building of the university later. So on the left, you see my university, earlier called University of Pune. And on the right, you'll see a view of IIT Kanpur, where I did my PhD work. The fountain and the library building that you see, the fountain is non-existent now, but the library building still exists. The next one, please. Yeah, I would like to dedicate this award to 2 of my mentors. The first picture that you see is that of Professor P.T. Narasimhan, who was my thesis supervisor at IIT Kanpur. One great thing he did was he never assigned any research problem to any of his students. We are supposed to play around, dabble with instruments or computer, and choose our own research problem. So I learned a lot from my guru. The second photograph is that of Professor Robert Parr, a very well-known theoretical chemist from UNC Chapel Hill. And I learned a lot of things from these people, in particular from Robert Parr. I learned academic honesty in full swing. You know, he would strike his name off from a paper written by his colleagues or students if he felt that his contribution was not adequate to be an author. So I dedicate this talk to these 2 mentors. I was lucky to have them in my life. Next slide. Yeah, 2 quotations I would like to cite. The first one says that chemistry is so pure science that mathematics should never take any part in it. This was by Auguste Comte, 1830. And the second is a counter view to this by a Belgian mathematician, astronomer, statistician, which says that more progress the physical sciences make, the more they enter the domain of mathematics. So I leave it to you to make your own judgment. But what I feel from the progress chemistry has made, I agree with the second view that is expressed by Quetelet. Yeah. Next one, please. Next slide, please. Yeah. So today's presentation, I'll be talking of the methods for ab initio treatment of large molecules. I may use some words which are abbreviated below. I'll use molecular electron density, molecular electrostatic potential. See the line below, critical point, molecular tailoring approach, molecular orbital, density matrix, and so on. These are somewhat theoretical terms, but I hope a general chemist today learns enough theoretical chemistry during his, I say jokingly that the Schrodinger equation will really go down to class 10 very soon. Maybe it has already gone, not in full glory. So theoretical chemistry has made great progress, and it has found a place in our BSc syllabus, MSc syllabus, and so on. So talking of methods for large molecules, I'll show you a brief history of fragmentation methods, and then we'll go to our own method, which I have called molecular tailoring approach. The reason is the way tailor stitches his clothes. He or she will take a piece of cloth, cut it appropriately, and put stitches in appropriate places, overlapping the parts of the cloth. So with this analogy, we termed it a somewhat non-scientific name called molecular tailoring approach, but the name has stayed over the years. I'll show you how energy or geometry optimization is done, how the Hessian matrix is calculated, and that leads us to calculate IR and vibrational Raman spectra of very large molecules. Let me tell you that standard packages like Gaussian or GAMES or many others cannot do this job. If you try to run the job for a very large molecule, you will invariably end with an error saying out of memory or out of disk. Lastly, I'll show you the conclusions of our work. Next slide, please. Okay, here is a pictorial view of quantum chemical calculations. I have tried to put it in a somewhat popular way, not aimed at theoretical chemists. So you can see that increasing the system size, if you have a protein or a drug protein interaction, you will not be using ab initio methods. You will use force fields or somewhat empirical methods or semi-empirical methods. If you have medium-sized molecules of the order of 100 atoms, then you will be using what we call Hartree-Fock approximation. And then if the molecules are smaller, we can afford to use what we call correlated methods or highly correlated methods. And we can treat maybe 10 atom, 15 atom, or 20 atom molecules with these methods. So as you can see on the left, I have inexpensive methods. On the right, I have expensive methods. And there is something called scaling of a method, the term that I'll use in my talk. Below on the left, I have shown you simple calculations on water clusters. And you can see that if I use the simplest Hartree-Fock method, I can do calculations on maybe 25, 30 water clusters. I have water clusters as an example here. If you use a very simple correlated method called Moeller-Plesset, don't worry if you are not specialized person. It's a very simple method to go beyond Hartree-Fock. Then you can reach water 25, but see the time. The time will go up as the fifth power of the size of the cluster. And if you do what is called gold standard method, what is coupled cluster, again, don't worry about the terminology. It's a very highly accurate method, very standard method today. You can hardly do water 8 or water 10 with such methods. So the trouble is, if I want very accurate calculations, I cannot do large molecules or large clusters. So what is the way out? The way out is you can resign and say, okay, I cannot do it. Or the other way is be somewhat positive, optimistic, and say, yes, we can do. And that's how the molecular fragmentation methods were born, which I'll show you on the next slide. Yeah, so I go back to my PhD days. I used to see this paper by Christopherson and others. In 1972, he was already talking of large molecules being treated to quantum chemistry calculations using molecular fragments. But the trouble with this was he was using only one Gaussian function for electron pair. Today, possibly, people will smile because the basis sets that we use today are hundreds of Gaussians per atom, whereas he was using one Gaussian or two Gaussians per small atom. Weitao Yang wrote a very nice paper on the role of density in direct, large molecule calculations in density functional theory. And our paper came in 1994. We called it molecular tailoring approach. And we looked at electron densities in very large systems at that time. Next slide. Yeah, and then many people joined Kitaura. This method has become very popular. It was discussed by Fedorov. You will see it's given a name, fragment molecular orbitals, which enables you to do very large scale calculations, mostly biomolecule oriented. And then Zhang and Collins and Nakai and many groups, about 10, 15 groups are active. I'm happy that we have been pioneers. We started the work in 1994. And then we are going on. Next slide, please. Yeah, can we go to next slide? Yeah, here I would like to acknowledge my students, collaborators, and I start on the left, the people who developed the methods, and on the top, I have shown the way we kept doing fragments. We calculated electron densities of very large molecules. I want to take it to solids if there is a collaborator interested in this periodic systems. It can be very readily taken. I have to find a chemical society, maybe a good avenue for finding collaborations. We did automatic fragmentation. Now we can calculate the molecular electronic energy, gradients of the energy, because gradients are used for geometry optimization. So we developed geometry optimization, calculation of Hessian matrix, and then computing IR and Raman spectra of very large molecules in which a standard black box code fails. And I should say that developments of the kind that we have done very rarely happen from India, though we are very good in IT and so on. Not many good products or usable packages have come up from this country. Okay, so let me show you my collaborators. On the left bottom, you see Ajay Limaye, who I can tell you life story of them. But anyway, currently he is in Australian National University, Canberra, doing graphics, a lot of graphics work, and he has gone into virtual reality. The second one is Babu, who developed very beautifully the technique of using technique of molecular graph. We learned for the first time how to cut a molecule into fragments so that we can join them and get the idea of the whole molecule back again. Ganesh was a computer science person who also developed beautiful graphical tools for doing the methods that we were developing. Anuja had a very wonderful idea that at the background, we use a package, standard package like Gaussian or GAMES or ORCA, or some of these names who are familiar to theoretical chemists. And then our program runs in the foreground and it makes fragments, stitches the results, and gives you the final energy or spectrum and so on. Sachin developed a special approach for clusters. The next person, the second from the right, is Nityanand, who made a beautiful algorithm for calculating the Hessian and IR and Raman spectra from scratch. So today we can do, and I'll show you some examples, all these calculations on reasonably large clusters. Subodh took it even further, all these, and he has converted to a package now called MTA Spec. If you are interested in using, please let me know. We can share all the details, and it should be made available to the Indian community in the coming years. After I get Lifetime Achievement Award, I should also contribute to the community of chemists, I feel, in the coming years. So the package will be made available to the Indian chemistry or physics community in the coming years in a very usable form. Next slide, please. Yeah, so this is the way we started, and I'll show you a glimpse of it. You take a large parent molecule or cluster and make overlapping fragments. Carry out, that time we did only Hartree-Fock theory, so you do MO calculation on each of the fragments, generate the density matrices of each fragment, and then patch them together. This is something that we learned how to do. And then we have the density matrix of the parent system, so we can calculate electron density without doing, that's the beauty, without doing the calculation of the whole molecule. Okay, that was really wonderful. And we calculated such things. On the next slide, I will show you some work that we did in those years, around 2000. Next slide, please. This was our paper in which JCP in 1994, it was only one journal of physical chemistry that time, not broken into A, B, C. Next one, please. Next slide, please. Hello. Can we go to next slide? Yeah. Here are our details from our work, which has received very large attention in the chemistry community. I will show you, if I map the maxima or minima of the electron density or the electrostatic potential, how does the tailoring approach reproduce these results? Okay, and you can see on the left, I have the full calculation. On the right-hand side, I have the molecular tailoring approach results. You can compare across, and you will see a very remarkable agreement between the two. We will not see such an agreement normally, because remember that we are not doing a calculation on the full molecule at all. We are doing only calculation on the fragments. Next slide. Next slide, please. Yeah. Next slide, please. Yeah. This is the way the density matrix. No, anyway, I'll skip that if you desire. We applied our technology to a large protein. One of my biochemist friends said, why don't you map electrostatic potential for a protein which has a potassium ion channel? He had the coordinates of that protein. We could calculate the electrostatic potential of such a huge object using our method. A standard black box code, the way chemists or physicists use, will not allow you to calculate this electrostatic potential. And what you can see is the golden isosurface that you see here is the negative part, and the potassium ion would hop around in that channel. Our friends from NCL said, can you do electrostatic potential maps for zeolites? Very large molecules we could do with our tailoring approach rather easily. And the accuracy was tested out for some of these systems by doing a full calculation. Our technique resulted into huge time saving and yet retaining the accuracy of the calculation. The next slide, please. So here is the principle for calculating molecular energy and other properties via molecular tailoring approach. A mathematician would use this principle exactly. It's called cardinality or inclusion-exclusion principle, as it's called. If you have two sets and a union of those two sets, the number of elements in that union is the number of elements in set F1 plus the number of elements in the set F2 minus the number of elements in the overlap fragment F1 intersection F2. We borrow this and we use it approximately for calculating the energy, the gradients, Hessian matrix, and so on. So this is the master equation for our what we call patching. So we calculate the energies of the fragments, we patch them together, and we get the property of the whole molecule. We have benchmarked it very, very thoroughly over the last 20 years, actually. Next one, please. Next slide, please. Okay, so many of you would be curious, those who are interested. Some people I see are not interested on the slides. They are moving around. That's a trouble with this slideshow. So fragmentation process, I will take a molecule. I don't cut benzene ring. I cannot do. As I say jokingly, Herr Kekule will turn in his grave if I did that. You know, he will feel very unhappy. So we cut single bonds, weak bonds, and keep overlapping regions so that the environment of an atom is very faithfully reproduced in at least one fragment. So we wrote a small paper on fragmentation, and we titled it as a pragmatic approach for balancing accuracy and efficiency. That's a paper we wrote last year. Next one, please. Next slide, please. Yeah. So that's a kind of a pictorial view of fragmentation. This is my parent system. These are my fragments. I calculate the energies of the fragments. I put them together using the master formula that we said on the last slide, and we get the property. Same way we can do energy gradients. And as Anuja has put it, the patching is done in Python language. So she has put this nice little cartoon of Python. Anyway, so our technology has been developed for games, Gaussian or Orca at the back end. The next slide, please. The package is now ready for use. Next slide, please. Can we go to next slide? Hello. Is there one before or? Anyway, we applied it to a protein just to show our kind of muscle power. This calculation was done in around 2000 something. This is a cage protein, 20 residues, 500 atoms, and people cannot do very easily a Hartree-Fock level geometry optimization of the system. So we could show that. Don't worry about the results. If you do very small fragments, the accuracy is not very high. But if you use slightly larger fragments, our accuracy is very good. So proteins are amenable to quantum chemical calculations, at least small proteins of the order of 1,000 or atoms or 20 residues, we can subject to molecular fragmentation and calculation. Next slide, please. Yeah. It led us to very interesting calculations of geometry optimization. And then somebody asked whether you can do infrared spectrum calculations. So we did this in this work. Two are very large and weakly bound clusters, water 37, boric acid 40 nanotube, and then a large covalent molecule, alpha cyclodextrin, which has several hydrogen bonds in it. And the table, don't worry about the details in the table, but what you can see is I can calculate ab initio at very good accuracy all these methods. I can get the energy, I can optimize the geometries, and I can get spectra for these. I have shown you how accurate are the spectra and how much time saving is achieved in this table. It takes about a fifth or the 10th of the time that you will require for doing the full calculation. So it's an art of the possible, you know, something that you cannot do with a black box. And many applied theoretical chemists are using black box codes. Our algorithm and our code would enable them to do much accurate calculations on these very large systems. Next one, please. Next slide, please. Yeah, so this is a paper in maybe 8 years ago. There is a person in Pacific Northwest National Lab called Xanthias. He's, for his life, he's working on large water clusters. They're of great interest in many areas of chemistry, including atmospheric chemistry. And we could do calculations on water 20, water 25 clusters. We could investigate a lot of isomers of these clusters at MP2. Don't worry of the details, at correlated level of theory. And such a calculation was not possible for Xanthias. For so many years, we could demonstrate that we could do this on a very, very limited hardware. Next slide. Next slide. Yeah. So we could extend it to a much better correlated method called coupled cluster. Devashish Mukherjee, the recipient of Lifetime Achievement Award for last year, has pioneered this method. He has done very basic work, foundational work on coupled clusters, singles, doubles, and general methodology. What we could do here is we could do CCSD calculation, T, perturbative triples as we call them, on these clusters. And you can see how accurate are the calculations. Okay, last two columns show you that accuracy. The very last column is the full calculation result, if at all you can do it. And the second last column is our grafting method using molecular tailoring approach. You can see that the results are astounding. They're highly accurate up to 4th place of decimal. And remember, these are done on a simple i7, single machine. And, it's an art of it showed that it's an art of the possible to do such calculations on a very limited machinery available. Xanthias uses 120,000 nodes for this purpose. We could show that it could be made to work. Although approximate, you can trust the result to 4th places of the decimal. Next one. We did this study. Actually, these are technical details. Maybe you only specialized people may be interested, but I have shown you on the right top corner, Xanthias required 120,000 processors. Our calculations were done on very small number of PCs, desktop machines, good configuration. And I have shown the scaling behavior with number of processors increasing. Our method is very parallel, highly parallel method, because all the fragment calculations are independent of each other, and different processors could be doing them at the same time. The next slide. So we did vibrational spectra of these, and I will show you the results on the next slide. You can see, I'll just show you, I have several examples, I'll just show you one slide. This is water 16, what they call anti-Bort conformation. With full calculation result are shown in red, and the gray ones are molecular tailoring approach. If you correct for the basis set at lower level of theory, what we call as grafting procedure, I will not go into details of that procedure, but it's shown that a simple procedure can take care of this. And this kind of an agreement on the left leads you to a beautiful agreement on the right hand side. Actually, you can't possibly visibly see that there are two curves. The red one is a full calculation and the blue one is our MTA with grafting correction. This paper was published in Journal of Chemical Physics in 2005. So we can do things which a standard package cannot do. The next slide shows you examples of water 25 in various regions of frequencies. And you can see the impeccable agreement that you can see with the full calculation, but done now on a very, very limited hardware. Next slide. Yeah, let me show you what we are doing currently. And this is done in collaboration with a student from Kolkata, whom possibly some of you would know. His name is Apurba Nandi. He is working in Joel Bowman's group at Emory University. He came for some personal visit to India and he called me. This was about 6 months ago. He said he is generating potential energy surface for many interesting systems, such as acetylacetone, the enol form of it, and he does dynamics of the way the proton jumps from an oxygen atom to another oxygen atom. Similar calculations are being done in his group on N-methyl acetamide and tropolone, right below. I will not bore you with details of the numbers, but you can see that I can use fragmentation method to calculate the energy at a given geometry of any of these systems at very high level of theory. As I said, CCSDT. And the results are accurate. They give you a time advantage of 3, 4, or 5. So that is very, very impressive, because these people take several hundred or several thousand geometries and then they derive parameters from the potential energy surface that has thousands of geometries or at least hundreds of geometries and use it for dynamics calculations. So we are in the midst of writing a paper on this subject, which enables the construction of a potential energy surface of such systems at very high level of theory. The next one. The next slide, please. Yeah, probably you cannot read the numbers, but we could use the technology for acetone, the enol form of it, and we could calculate the energy gradients. Now, if in addition to the energy points, if you give the gradients as well, I can have very beautiful parameterization made for further dynamical calculations. So that is a very welcome addition to the methods for generating potential energy surfaces for large systems or at very high level of theory. Next one, please. Yeah, so we are almost at the end of my talk. I'll just summarize for a non-specialist person what we said. We have developed a method. We have developed an algorithm. We have converted it to a parallel program which runs, which is usable by others. And it has been tested, benchmarked on a wide variety of systems, as I tried to show you, from polypeptides to proteins to water clusters to cyclodextrins and so on. So it's ready for use by the chemistry community. We started with accurate and economical estimates of electron density. Now we have added a lot to the package, and this chemistry community, I urge you to use the package. It is a completely Indian effort, thousands of lines of code and several algorithms that have gone into it. And it will enable you to do energy calculations and calculation of vibrational IR and Raman spectra for large systems available for use. But of course, before that, the user should learn how to use it and use it meaningfully for their chemistry problem. Next slide, please. Yeah, next slide. Maybe you skipped one. There was one in between. Yeah. So, very last slide before we acknowledge. So, what are the plans for after this year? We will use MTA in conjunction with other. There are many better ab initio codes such as Orca or Psi4. They are very fast and accurate. The beauty of our code is it can be put in use with other programs like this. I didn't talk to you about use of MTA in estimating intramolecular hydrogen bond strengths. We have a method, beautiful method to calculate how strong are intramolecular hydrogen bonds using basically the same idea of molecular tailoring. And we have many, many future plans. So this award will give me, I'm sure, further strength to carry out all these things. I have a plan for using this electron density and electrostatic potential computed by our method with what a crystallographer gets and, from experiment. Some people have given it fancy name, quantum crystallography. If there are collaborators in this, I'll be happy to do some work in this area also. Next slide, please. Yeah, so finally, let me thank Indian Chemical Society, in particular, Professor G.D. Yadav and Professor Chittaranjan Sinha for giving me this opportunity to talk to you. And I would like to thank various agencies which have supported my work over the years, from my small place in University of Pune, now called Savitribai Phule Pune University. It has been funded by CSIR, DST, and now I got some funding from National Least, let me thank you all for attending my lecture online. Thank you very much.
Thank you, Professor Gadre. A wonderful lecture. We came to know about molecular tailoring approach. Incidentally, Bob Grubb, who died, was working on metathesis, stitching molecules, breaking and stitching them together. Since this is a Lifetime Achievement Award, there will not be any questions, but you can ask Professor Gadre questions by sending email to him. And we would like to go into the next lecture immediately, and that will be by Dr. R.V. Jasra. Dr. Jasra, please.
Yeah. Hello. My screen visible?
Not yet, sir.
Now?
Yeah, it is here.
Okay.
You can go to full screen if possible.
Yeah, we are trying. Yes.
Oh, that's okay. Nice. Thank you.
So, thank you, Chemical Society, Indian Chemical Society, for this encouragement, and I'm really feeling very humbled with this recognition. And in my
Only one thing before I start my talk. I will request Professor Sinha to correct my patents. I have 65 US patents granted, 119 Indian patent granted, and maybe 32 other countries. So please make this correction, because we have worked very hard for getting these patents. And I'm expecting 100 more patents which are in different stages of grant to be granted later. Now, what I'm going to speak today is something, few thoughts on opportunities for chemical researcher in this country. And then I'll also spend some time detailing few stories where we have developed some technologies in R&D and commercialized in Reliance. This is my disclaimer that whatever I say here, I'm fully responsible for that, not my country. And I would also like to dedicate this recognition to my students who worked very hard. I have around 27 PhD students and around 16 MTech students. Then my colleagues at IPCL, Bhavnagar, CSMCRA, and also Reliance, and of course my family. And two mentors, Professor J.C. Ahluwalia at IIT Delhi, who really taught me to do research and very, very independent thinking, independent way to do research, and also very meticulous way. And then next, Dr. S.C.D. Bhatt, who really opened the world of applied scientific research when I joined IPCL, and he guided me. My presentation I'll spend few slides on related to chemical industry in India and where is the scope or opportunities for all of us to really innovate and do something for this chemical industry. Then as I told, I'll spend few, not all, at least 4 or 5 stories of Reliance where we have developed technology and commercial technologies. So if we really look around, the chemical industry in modern society is very, very critical. We look last 100 years, 150 years, industry has played a big role through its boundless ingenuity and entrepreneurial spirit. Many problems which have mankind faced, it may be materials challenge, maybe energy related challenge, health and food security. It is the chemical industry and some of the brilliant chemists have come with solution to the society. And today, that is why today we have got around more than 80,000 products being traded globally. And this industry is still growing, even higher than world GDP, 1.5 times. And I don't think without the contributions from chemical industry, it is possible to sustain the way the present civilization is living. We are totally dependent on so many things from any point of view, health, food, nutrition, energy, and materials. We need chemical industry. Now, just to give you some idea, global chemical industry is around 4.7 trillion, maybe a little more now. 4 years back, it was 4.67 trillion. It is growing 5 to 6% per year. It is a big employer and employer of professionals, technically competent people really get absorbed in chemical industry. And last maybe 3 decades, we have seen China has emerged as a manufacturing hub for chemicals in the world, followed by US, then Europe, and then of course, Japan. And India, in India, we are a very tiny player as far as chemical industry is concerned. We only 3% of the world chemical market is owned by India. So there's a huge potential you can see because we are a very small player. And there is a really incentive to get into chemical research and then chemical industry, because it is a consistent value creator. If you look into the shareholders' returns over the years from 2006, globally and even within India, the chemical industry has been really doing excellent work. So it is really, there is incentive to get into chemical industry. Now, if we really look into Indian chemical industry today, we are $15 billion gap between our export and import. We export chemicals and we also import chemicals, but the gap between import and export is $15 billion. So it's a big number. So this means there is a really need to have still more chemical industry in the country. We are a large population, we are a growing population from economics point of view, and development point of view. The need for chemicals is also growing. And if you see the extreme right of my slide, this gap is the highest in petrochemicals. In petrochemicals, we are really importing, or still, I'll just go for it. Here you can see we import more than what we export. So that's where I think there's a big opportunity. And I belong to basically petrochemical industry. That's why I want to really focus on petrochemical. Of course, we have strong position as far as export is concerned in some sectors, which can further be strengthened. So if you look into petrochemicals alone, this number, this slide is very interesting. If you see this, if we talk about Atmanirbhar Bharat today, but I think if we can just be Atmanirbhar in petrochemicals, the $15 billion, there is an opportunity. And this is across all the carbon number, starting from C1, where methanol, formic acid, acetic acid, acetate, vinyl acetate, EVA, PVA, polyvinyl alcohol. Here you can see $2,000 million import is there by India. Then we go to C2, where ethylene dichloride, vinyl comonomer, and then PVC. PVC is very important. PVC, because construction activity in India is really growing big way, where PVC is used as pipes. And $2,400 million opportunity. Then we go to C6, C4. C4 is this styrene butyl rubber. Then other styrene-based polymer, ABS, SAN, and polystyrene. $2,500 million opportunities there. In C3 and C6, like phenol acetone, we have recently got one phenol plant in Gujarat, Deepak Nitrite has put. Then of course bisphenol and then polycarbonate, and MMA, PMA, polymethyl methacrylate. There are also $1,700 million opportunities there. We go to acrylic acid, oxo alcohols, and acrylates, and super absorbent polymer. 1,300. We don't have any acrylic acid plant. BPCL may put acrylic acid plant in Kochi, but so far we don't have technology. And then of course C3, POPG, polyol, polyurethane system, which are all of daily use material, but most of these materials we don't produce enough for this country. And more important to this, all these chemicals is we don't have technology in majority of these chemicals developed within India. So what I'm trying to say, this is a huge market. We're spending a lot of money in importing these chemicals, and we don't have industry to produce these chemicals within India, and we don't have our own technologies also. We have a very huge base of chemical researcher within the country. We have got history. We have got history of chemical research in this country. Unfortunately, we are not having our own technologies for some of these very, very, very vital or widely used chemical within the country. So that's why I think there is an urgency. If we really want to be Atmanirbhar, there is a really urgency to invent some new technologies in these areas or tweak the existing technologies which are available, innovate this and come up with competitive technology and then start really making those within the country. We are strong in some of the agrochemicals, dyes, pigment, and intermediates for APIs, where our share in the global share in these three sectors, like we have 49% in APIs, the global shares. But story is very sad today in APIs. See, we were very strong. We had many companies who were making this drug intermediate, chemicals for making drugs. But last decade, 2 decades, these are closed down because we started getting cheaper API intermediates from China. Now today, 65% of our drug industry is depending, 65% these chemicals intermediates, we are dependent on China. Government is really worried and they have made a task force and they are really trying to encourage Indian entrepreneurs to get back and start making our own intermediates for drug. In drug, we are very good, we are doing well. On agrochemicals, we have 69% share, and then special dyes and pigments, we have 59. Now, if you leave these three sectors, look at the bottom, plastic additives, electronic chemicals, food and food additives, nutraceuticals, rubber chemicals, flavors and fragrance. We have got some presence in flavors and fragrance, but otherwise, if you see our electronic chemicals presence is very low. And we all know how the electronics industry is growing in India and also in the globe. I don't think we do have many industries which are producing these electronic chemicals. And there is a really scope for even nutraceuticals. We are very, very poor. You can see the numbers here. Compared to China, our share is very, very low globally. And there's a huge opportunity for all of us to do some R&D, develop some technology related to electronic chemicals, nutraceuticals, and wherever there is a potential you can see. And then once we have technology, our own technology developed within India, I'm confident that we will get some entrepreneurs also who will start making these chemicals within the India. Now, this was about chemical industry. Now, second, a very important area which should attract the attention of all of us who are in science and technology is the energy or environment, sustainability and energy. I'll spend few slides on related to energy, then few slides on sustainability and what does it really mean to people who are working in chemical research. If you look the world, the way we are living today, and if we continue to live the same way, business as usual, by 2050, the world population will be somewhere around 9.1 billion. GDP will be around 280 trillion. And then we will need total energy demand will be 35.887 million tons of equivalent to oil. This is the energy we need. And if we continue to depend on fossil fuel energy, on crude oil or coal, then the numbers I have given here, crude oil daily demand will be around 247 million barrels a day we'll need. And natural gas will we need 307 trillion cubic feet annually. And then once we use fossil fuel, if we use this number, then this world is not really sustainable. You can see CO2 level and concentration will be very high. So this is unsustainable world by 2050. How we can make it sustainable? These numbers remain same. We can't afford, we can have around 450 ppm CO2 in the atmosphere. And then means by 2050, only 85 million barrels per day we can depend on crude and 150 trillion cubic feet on natural gas. rest of the energy has to come from some green resource. We can only afford to have this much energy from natural gas and crude. Rest has to come from green source or renewable source. That's why this is giving big opportunities to everybody who wants to do good science, who wants to develop some technology, hydrogen, electric vehicles, wind, solar, biomass. These are the hot areas in the world today, and these are the areas which are giving huge opportunities to all of us who are working in chemical research, because chemistry is there everywhere. We want to look at materials, we need to do chemistry. We want to do electrolysis, we need chemistry. So these are really great, exciting times for all scientists who are on the better side of the age, because it's a rare event, like we are witnessing the energy shift in the world. Energy will shift. We will not depend on fossil fuels. In next maybe 15 years from now, we'll see our dependence will be largely 60-70% will be on renewable source of energy. I don't know whether it will be hydrogen, it will be battery, or it will be electric vehicles, or combination of all, but we really don't know, solar and wind also. But this is happening, and this happens once in a while in the human history. You can see here from natural, that wood, dung, we have gone to coal, then from coal to oil, then of course we went to electricity, and now we are in renewable energy source. Short term, we'll see coal gasification, natural gas, biomass conversion to fuels, or these will become energy source. And long term and sustainable, we'll see solar photovoltaic, solar thermal, fuel cell, battery, and hydrogen. Now, this is really, one has to really look into all this area seriously, and every scientist has to see what way, depending on my competencies, my skill set, what way we can contribute to really develop this technology within India. That is the opportunity. Let's say one example I have just put here, hydrogen. Hydrogen, the issue, hydrogen is excellent fuel because it is non-polluting, energy density is high, but volumetric density is low. That's why storage is a big issue of hydrogen. And even hydrogen production today, we produce hydrogen in our own refinery and petrochemical and use it also. But that is not green hydrogen. That is a gray hydrogen or brown hydrogen. It means we produce carbon dioxide along with hydrogen, which pollutes the atmosphere. We want to have a green hydrogen where there is no pollution. Only hydrogen is produced. So water splitting, whatever way, electrolysis or any other way, it may be enzymatic route or other route, or catalytic, catalytic, electrocatalytic route for splitting water to get hydrogen. These are the opportunities available to all of us. Whether you are a physical chemist, whether you are a organic chemist, inorganic chemist, I think everybody has got some opportunity even in this area. And then hydrogen storage. How do you store this hydrogen? The way people are used to go to a gas station and get the gasoline filled or the diesel filled into their vehicle. How the similar thing can happen? The life is easy. It takes only a few minutes to get the gas and go up. So various options are being looked into. Absorption is being looked into, compression is being looked into, then LOHSE, liquid organic hydrogen carriers also are being looked into. So this is what I wanted to just show. One, hydrogen as an opportunity. Similarly, if we go into other energy sources, people are also looking into green ammonia, because ammonia can also be good hydrogen carrier. But the way we produce ammonia today, it is no longer green. So we have to really work on how to produce green hydrogen. So there is a big opportunity for all of us. Just because I talked about green hydrogen, you look, this is the ammonia. These are around 18 some chemicals which I have listed, which are 80% of the energy in chemical industry they consume, and 70%, 5% greenhouse gas emission is being done when we produce these chemicals. And ammonia is number one. That's why ammonia cannot become a and hydrogen carrier, if we don't develop a process which is more sustainable, energy efficient, and less polluting, what we use for production of ammonia today. These are the other chemicals like ethylene, propylene, methanol, styrene. A whole list is there. Xylenes, polyethylene, benzene, toluene, xylene. You can see all these processes today, whatever we are commercially doing it, there is a huge scope to improve these processes by developing more energy efficient routes or more technological route which are dependent on renewable resources, renewable feedstocks, so that these all chemicals can be produced in a more sustainable way. So these are all available. I mean, the technologies are there, we are using, but anybody comes with the better technology, which is greener and more safer, then definitely industry will lap it up. When we are talking about shift of energy from, let's say, crude oil to electric vehicle, then one big impact which we will see in the world is the first automobile industry will go under a big change. All gasoline run vehicles or diesel run vehicle later will shift to batteries or fuel cell. And this is going to impact all oil refineries in the world and also within the country, in India, because when we see the consumption of gasoline, diesel going down, what will we do with the refined naphtha or gas or even VGO from the crude? Most of the refineries will shift to petrochemicals. Today, refineries around 16% maximum is petrochemical, rest is all fuel. They produce either diesel, aviation fuel or gasoline. Now, when we shift by 2040, it is said 70% refining will shift to petrochemicals. So why I'm showing this slide to all of you? Because all this feedstock, which is being used for producing fuel, will be available for us to do chemistry and produce some good or better chemicals through better technologies. Large amount of crude will be available for production of petrochemicals and new chemicals. So there's a huge potential. That's why almost all world companies, it is Aramco, it is Reliance, it is Indian Oil, or it is SEBIC, whatever you say, they're all trying to look into new technology like O2C, oil to chemical, crude to chemical. We are hearing these terms because all of them are focusing, developing new. This is an area which is also pregnant with a lot of opportunities for developing new technology and doing some new chemistry. Of course, renewable feedstock for chemical synthesis is the future. Carbon dioxide or biomass, we will see becoming, and we are seeing very large number of efforts by almost all the researchers worldwide who are focusing on how to convert carbon dioxide to acetic acid, formic acid, methanol. Once you get methanol, you can get all types of compounds made from methanol by doing dehydration. Then you go to ethylene and then you can produce chemicals. Sustainability also have given a big boost to this polymer recycling technology. Whatever we use polymers, we have to recycle them. Now, this is very amazing whenever I think about it. See, we have done excellent chemistry where crude has been converted to some useful chemicals, which is much more complicated. Whereas this polymer, rather than crude, they're much simpler carbon source today, if you see. They're available to us. Only thing is some logistics has to be thought about how do you collect this spent polymer and then convert it back to either some useful chemical or to monomer. Huge quantity of spent polymer is available in the world, around 435 million metric tons in 2020, and it is supposed to be 1 million metric ton by 2050. Now, we have to really start doing some good chemistry so that we can convert these polymers, spent polymers, back to some useful chemical. They're excellent source of carbon and very rich source of carbon. If you compare with crude and coal, they're also very good source of carbon. And this source today is lost. $100 billion carbon is lost when we don't do anything to the spent polymers. So here, I think people have not looked into it seriously. Only last maybe 10, 12, 15 years, people have started looking into this, how to convert these polymers back to chemicals. I believe this should be much easier than whatever petrochemistry we have seen from spent polymer to this thing. That's why we see now pyrolysis, catalytic pyrolysis, hydrocracking, alkane metathesis on polyethylene, oxidative depolymerization, catalytic depolymerations. These are the things which have become now seen in the literature. And that's why even the hydrothermal liquefaction of this polymer, waste polymer, rubber, which can back. I mean, if we start viewing it as a carbon source, not as a waste polymer, I think everything changed, mindset changed, then we can really do some good chemistry with this polymer which is available to us. And we did some work on this hydrothermal liquefaction where we have shown the rubber or the polymer spent can be converted to bio-oil almost 55 to 96%. In some polymers, waxes which we collected from industry, we could convert to 96% conversion. In some cases, electronic waste, other thing we studied, we could convert it to 55% to bio-oil, other thing. There's a really scope. There are technologies which are available. As I said, pyrolysis is available, catalytic pyrolysis is available, metathesis is known, depolymerization technologies are known, and even hydrothermal liquefaction is known. If we use them to convert the spent polymers, I think we will be doing good business. In fact, in our Reliance industry, people may not know, we are the big conversion of spent polyester back to its monomer through glycolysis. We have got 60,000 ton per annum plant running in Hazira, where we collect this spent polyester and convert back to monoethylene glycol and other monomer, and then again produce PET from using this spent monomer. We are putting another equally big plant for this polyester recycling. This is this circular economy which was already practiced. Same thing now should happen to polyethylene, this polyvinyl chloride, polystyrene, polyurethane, how we can convert back to those things. So my belief is the way awareness on among the scientists have happened. Short term, we'll see recycling of these polymers back to monomers or useful chemicals. But long term, we are going to see totally new chemistry. We will be seeing there is going to be shift in the way we make chemicals or the way we make products. And I think the focus will be how we can do chemistry for producing this product, like we do esterification to produce this polyester, then we do hydrolysis to produce back the monomers. So the reversible chemistry using two reversible things for producing product will become more common. Dehydrogenation and then hydrogenation. If I do dehydrogenation, I can produce a product. If I can do hydrogenation, I go back to monomer. Transfer hydrogenation, carbonylation, decarbonylation, supramolecular chemistry. So this is going to be totally new chemistry because of this concept of sustainability is becoming. In long term, people will start developing products where the chemistry is such when we make those products that it can be reversed back when it is no longer required to be used for that application, that product. So this is the long term, and this is again going to give rise to new chemistry. And there are huge opportunities available to all of us if we really start looking into these things. Right, these are some thoughts I thought I will share with you, but I want to quickly go through some of the developments we did in recent times in Reliance and also commercialized. This is one catalyst in our aromatics plant. We are one of the largest producer of paraxylene in the world. And that is a whole aromatic complex really centered around production of paraxylene. All our unit operations are how to maximize paraxylene from naphtha. And in one of the unit operation, we use PARAX process, like paraxylene separation from C8 aromatics. And then the C8 aromatics feed, when it goes to the adsorbent or any other catalyst downstream, it should not have olefins into it. If it has olefin into it, it spoils or it affects the selectivity and the conversion yields of our catalyst, even the adsorbent which we use for separation of paraxylene. So this olefins we were removing by using acid-treated clay, acid-activated clays. And then very large quantity of clays has to be used, because then life of this clay is 3 to 6 months. Within 3 months, they will be spent, and then you have to throw it. You cannot regenerate. So, and also some styrene breakthrough we were facing. Then this was becoming a big issue, dumping of the clay and then removing clay, putting every 3 to 6 months. 10 years back, I joined Reliance 2008. Then 2010, we started working on can we develop an alternative regenerable catalyst rather than clay, which has a higher life and higher capacity. And last year, we have commercialized this catalyst in our Patalganga plant. We produce around 8.5 metric ton catalyst, and this is put in the reactor. It is doing excellent job. It is working very well. And our estimates about whatever work we did on pellet plant and the laboratory shows it should have around 10 to 15 years life, this catalyst, compared to 3 to 6 months clay. So this, even if this is costly catalyst compared to clay are very inexpensive material, but because of its long life, it will make up for that cost. And now, after having seen the success of this catalyst at plant, Patalganga plant, which is a smaller plant, our next step is to produce around 100 ton of this material for our Jamnagar plant, where very large quantity of clay is used. This was very, very exciting work. It almost took us, you can see, around 9 to 10 years for starting from the first experiment in the lab and then putting and seeing in the reactor. But innovations involved, very excellent innovation. The zeolite is the base material which is for this catalyst. And then we have, this is not a zeolite which is produced in India by anybody. We developed the whole know-how of making this zeolite in India with less cost. And also we have commercialized this process on a large scale. So we have that competency of making that zeolite on our own. Now this zeolite can be used for many other applications. Second was this is a liquid phase process. The diffusional problems are there. Molecules have to diffuse at temperatures are around 170 to 180. So this diffusion issue means your pellet, catalyst pellet, has to be properly made. Mesoporosity, macroporosity in the pellet also has to be tuned. So that's where we did some innovation, and some specific morphology of the catalyst pellet is made, so diffusional resistance are not there. It was very exciting work. We have got, I don't know how many patents we have got on this development, and our now dream is to make clays, acid-treated clays, history in aromatics plants in the world. There are many units in the world which use these clays. We believe they will eventually will all be replaced. And another very important point, anything we do in Reliance, they don't want to disturb the existing plant configuration. It has to be drop-in catalyst. It is just like you remove the clay and put our catalyst. Nothing else you have to change. No additional reactor, no additional pumps, same conditions, same size. That's what we have done. That is why this is very exciting development. Another catalyst which we did, again related to our polyester. Paraxylene is also goes for PTA and then polyester. So here also polyester. In polyester, when we produce these PET bottles, polyester material per bottle, the polyester PET bottles, here we do solid state polymerization at high temperature in the presence of nitrogen to go to higher IV, high intrinsic viscosity of the polymer, higher molecular weight. Now this nitrogen gets contaminated because some VOC, some small molecules are generated, hydrocarbons generated, aldehydes and some oxygen containing molecules, and they come back when we recycle this nitrogen. And then when you go do the polymerization next cycle, the polymer properties get affected, like color and other thing comes to the polymer, which is not acceptable. So you have to purify this nitrogen. We have done this by developing a catalyst. Earlier we were importing from UOP and others, and they were having this costly catalyst, platinum based catalyst. We have made our own catalyst, which is better, which gives 40% higher conversion compared to a reference catalyst. And what we have done, basically, we have put precious metal in this catalyst on alumina, but we have gone to very, very controlled nano size platinum with controlled morphology, so that activity is high in this case. So this is already now in use in 3 plants. 2 more plants we are going to put in, one in Dahej. Hazira we have already supplied. Dahej we are already making around 1.8 metric ton catalyst. So this is also very, very interesting, exciting development on oxidation catalyst, basically hydrocarbon oxidation catalyst. Now the potential of this development within the country, this catalyst can be used for VOC control, volatile organic compound. If we want to destroy those chemicals. If there are toxic chemicals, we don't want to absorb those chemicals and recycle. Then this is a very good technology, because our catalyst can destroy or oxidize these hydrocarbons. So we are also now trying to expand the utility of this catalyst. Having developed the know-how, we want to get into VOC control with our catalytic VOC control within our own plant in styrene, butane and rubber plant. We are trying to really get rid of styrene, which goes into the atmosphere through emission, by putting this our catalyst. So this has huge potential. This development also has a huge potential. Now I'll show you one another technology which we developed, is again related to polyester. It is adsorption technology. I've talked about catalytic technology. This is adsorption technology. Here, this also again has happened because of our plant issues. See, sometimes some problem happens in the plant, and we from R&D get engaged, and we come up and try, lucky to develop some new technology. This is what happened in this case. One of our polyester plant, which is 1 million ton per year production, there was an issue. We use thermic fluid for controlling the temperature of the reactor. A huge quantity of thermic fluid is used, so that polymerization temperature is under stable condition. Now, these thermic fluids do get some impurities developed because of oxidation, because of some air ingress with the time and thermal stress on the thermal. And some cases, some leak also happened from acidic impurity from the reactor to the thermic fluid. This has happened in one of our plants, and we were approached. Online, you have to purify, because we can't stop the production of the unit. It will huge loss. So November we were given the problem. By February we have provided a solution, adsorption solution. We have put the adsorption column online, which was really cleaning this thermic fluid continuously, so that there is no effect on the reactor. Because if pH goes down, acidic impurities come, there is a corrosion problem to the pumps, and the lines can happen. We have put it, and we have used very commercially available adsorbent, which was cheap, but this was not reasonable, and also its life was low. But that time we have used that adsorbent. We just wanted to provide the solution. But within a year, we have come up with a totally new, first time in the world developed adsorbent, which has got much higher life, and also already put in our commercial units, that new adsorbent which we developed. And nobody has used that material as adsorbent material. No, it's working more than a year and a half without any issue. Excellent results. So this development involved providing technical solution to the plant's operations on this spot, and also coming up with a totally new material. which nobody has thought. And that new material now is we can use for many other applications. We are already done for solvent purification, sulfurline purification. We are putting in one public sector company. We have licensed that technology. And in our own Jamnagar, we have put for NMP, N-methyl pyrrolidine purification for removing chloride, similar adsorbent we have put. So this is what I want to say, one small development which happens and which can have a huge impact. So this is adsorption. This is the online adsorption technology for purification of thermic fluid. Thermic fluids are very, very important in chemical industry. And also if we want to have the solar thermal technologies, there also these thermic fluids are used for recovering of heat from the system. So there also, this is also very, very important. And we are now trying to even licensing this technology to others. We are in touch with some companies, international companies who are keen to take our technology and license to others. So this is another very, very interesting this thing. Now I'll come to another technology where we have ethylene to 1-hexene. 1-hexene is a co-monomer in polyethylene. We use, when you go to metallocene based catalyst, 1-hexene is used as a co-monomer. So we developed this ethylene trimerization catalyst, homogeneous catalyst, and then scaled it up in our pilot plant, 90-liter reactor pilot plant demonstrated. Now we have about 18,000 metric ton plant we have put in Nagothane, where our technology, where our catalyst and whole technology developed by Reliance, our engineering team and R&D together has commercialized this catalyst. Our catalyst is different, superior to other like Chevron and other companies, and we are the third company in the world now who are having this technology. Our purity is 99.4 and per pass conversion is 80% and better than all others, and all again patented technology. See, interesting thing is here, I just want to share with you particularly this. When we were working in the lab, our yields of hexene was 20%. You see, when we went to commercial, how it improved. Every stage, pilot to demo to commercial, there has been improvement because of engineering inputs. Very close working of engineering team and R&D chemistry team together really has helped to make this technology very, very, very economical technology. This was also very, very interesting journey to conceive a catalyst in the lab, work with 100 ml reactor autoclave, then go to this very big reactor in commercial scale. This is a very, very interesting development, and I feel very proud to be part of this particular. See, the ultra high molecular weight polyethylene is engineering polymer. You can produce sheets from this and do machining out of this. You can make these gears and all those things. It's a very strong material. When I say ultra high molecular, means the molecular weight is more than 2 million. It can be 6 million to 7 million, 5 million, like that. Now the problem with we were producing this ultra high molecular weight polyethylene in our Dahej plant, but the catalyst which we were using was giving a lot of fouling. Every few months or so, a lot of fouling used to happen. Then you have to open the reactor and clean, which was not acceptable. So what R&D did was we developed our own catalyst, which was giving no fouling. We changed the co-catalyst. Co-catalyst is normally alkyl aluminum use. We changed the alkyl aluminum, and titanium-based catalyst is the main active catalyst. And we commercially put in the reactor, and there was no problem with the fouling of this case. No, ultra high molecular weight polyethylene is very, very important material because worldwide now there are only 2 companies who are making bullet resistance products based on ultra high molecular weight polymer fiber in the world. So we were very keen to get into this production of this material because in India nobody was producing. Unfortunately, because of very small volume that time, this plant got closed. Our company thought this is not very, very economical to run such a small plant. And also the UHMWP has got one processing channel. When you want to do injection molding or any processing technique you want to use to make sheets or fibers or any other product, you can't do rotomolding and injection molding because these chains get entangled. Because this is a very large polymer chain, because of high molecular weight, chains get disentangled. When they are getting disentangled, then processing becomes very difficult. So this was the issue with this. That's why this ultra molecular weight polyethylene is not as much commercially used as we have got HDPE and LDPE in the world. Because this 1 milligram polymer particle will have around 1 million molecular weight. If we have 1 milligram polymer with 1 milligram molecular weight, 10 to the power 14 entangled chains are there. So entanglement is so bad. So that is why, so that time when we were working for the catalyst and we have developed competency in making the catalyst, the challenge was, can we develop a ultra high molecular polyethylene? There are no entangled chain or very less entangled chain, so the processability becomes easier. That was the challenge we have given to ourselves, and I'm very pleased to share with you. We don't have one, we have got 4 catalysts, our own catalyst, proprietary catalyst for this disentangled ultra high molecular weight polyethylene today with us. And we are producing this regularly on our pilot plant, this material. And this material we have also used for producing high strength tape, solid state processing of this powder, polymer powder, to high strength tape. So easy, which was so difficult when it was entangled. Now with disentangled polymer chains, we are able to produce anything from the solid state. We have produced fibers, we have produced tapes, high strength tape. When I say high strength tape, very, very high GPA and very high tensile strength. So then from that tapes, we have produced bullet resistant panel, which have been tested for even AK-47. We have worked with some defense labs. We have given the laminates to them. There's a lab in Chandigarh, TBRL. They tested for and different shots from AK-47 to normal pistol also. This material has passed all those tests. So today in India, our company with our own developed, totally our own catalyst, our own polymer technology, and our own solid state processing for converting to high strength tapes, then converting the tapes to bullet resistant panels. We have complete technology developed with this. And around this particular development, we have got more than 30 patents we have filed. Around 15 or so already granted around this material. This is very, very interesting development, and I'm very, very proud of part of this work in Reliance. The last story which I want to tell is also a little interesting, because in Jamnagar refinery we produce today 1.7 million ton elemental sulfur. 1.7 million ton element sulfur, most of which we are selling it abroad and exporting, and it goes largely for sulfuric acid production. That time when we were asked, this is very low cost application. We don't get much money by selling this sulfur. So we started looking, can we value add this sulfur? Can we produce something which is more valuable from this sulfur? And very, very, really sad to say, when we try to look around within India, are there any groups which are doing sulfur chemistry? We didn't find it. We didn't find any. So we thought we would start our own sulfur.
Yeah, Dr. Jasra.
Yeah, last
Dr.
slide.
Jasra, please.
Yeah,
We are behind the schedule.
And this is the last slide.
Please, sir.
Yeah. Then we started working on it. We identified 2 applications. One of them was sulfur as a soil nutrient. And we developed a formulation using this sulfur, which first as a soil nutrient, and we have tested it for 40 crops across India. in different regions of the India, and we have shown 15 to 40% yield can be improved by applying this sulfur as a soil nutrient. And then we also applied this as a sodic soil which has high pH, that can be converted to fertile soil, which is not producing much today. We can convert by applying this material, which we call Reliance Farm Sulfur. And this also we have taken 20 trials across UP, Madhya Pradesh, Punjab, Haryana, and shown a different variety of crops. We have shown that you can convert this barren land to fertile land. This is also very, very interesting development, which impacts the agriculture produce of the country, and really, which we've taken on a large scale, it can bring a paradigm shift to agriculture productivity of India. So I think these were the few stories I thought I will share with you, in which we have been working in Reliance through R&D, technology, and then implementation. So in summary, I just want to tell you, I brought to your attention the status of chemical industry, and then what are the big shifts, energy shift happening in the world, and how it is giving opportunities to all the people involved in chemical research to really do innovation and come up with some good technology. And then, of course, I talked about few interesting things which we have done. Before I end, I really want to express my sincere thanks to Professor Yadav, Professor Sinha, and all ICS members for recognizing my contributions and bestowing this award on me. And I'm really grateful. And I'm also thankful to all of you for your patient listening. Thank you very much.
Thank you, Dr. Jasra, for a wonderful lecture, giving a glimpse of the chemical and allied industry, petrochemical industry to the audience. I'm sure they got rich knowledge. I also would like to mention that Dr. Jasra is the first, Lifetime Achievement Award winner from industry. So if I recollect it properly, and henceforth this award which we have, it will be given to three different categories. So Dr. Jasra, congratulations for winning this award. And with this, I conclude this particular session and we go to the next. Thank you very much.
Thank you. Thank you.
So thank you, our Honorable President, Professor Yadav, for sharing this Lifetime Achievement Award session. Now I request Professor D.C. Mukherjee to chair the very important endowment session. Professor Mukherjee, please. Professor Mukherjee, please. Professor D.C. Mukherjee.
Yes. Okay, thank you, Professor Sinha. Without spending any further time, because we are running much behind schedule, this is my immense pleasure to chair this important endowment session where Professor Amitabh Chattopadhyay is the speaker. I can justify actually my position as the chairman here, not because of the expert of the subject, but only on the consideration that if Professor Chattopadhyay chose to read in Calcutta University, then he could have been my student. That is the only justification I can provide. I have heard his name since his college days. Some of his teachers had been my good friends, and his name was very famous since that time. It is customary to introduce the speaker before the audience. I am sure he is much more known to anybody else than myself. But still it is customary, and that's why I read out the material which I have about him. Professor Amitabh Chattopadhyay is a global leader in membrane and receptor biology and biophysics, and is a CSIR Bhatnagar Fellow at the Center for Cellular and Molecular Biology, CCMB, in Hyderabad. In addition, he is a distinguished visiting professor at the Indian Institute of Technology, Bombay, adjunct professor at the Jawaharlal Nehru University, New Delhi, Tata Institute of Fundamental Research, Indian Institute of Science, Education and Research, Kolkata, Swinburne University of Technology, Australia, and honorary professor at the Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. He served as the first Dean of Biological Sciences at the Academy of Scientific and Innovative Research. Professor Chattopadhyay received BSc with honors in chemistry from St. Xavier's College, Kolkata, and MSc in chemistry from IIT Kanpur. He obtained his PhD from the State University of New York at Stony Brook and was a postdoctoral fellow at the University of California at Davis prior to joining CCMB. His work is focused on monitoring organization, dynamics, and function of biological membranes in healthy and diseased conditions. His group has developed and applied novel, innovative, and sensitive techniques based on fluorescence spectroscopy for monitoring solvent relaxation in membranes, membrane mimic media, and proteins. These insightful studies have led to a better understanding of the dynamics of hydration in membranes and proteins. A seminal contribution of Professor Chattopadhyay's group focuses on the role of membrane cholesterol in regulating the organization's dynamics and function of G protein coupled receptors, GPC. Which are important cellular macro mechanics that act as drug targets in a majority of human diseases. Pioneering work from the group showed that membrane cholesterol is necessary for the function and organization of GPCRs. In addition, his work has proved novel insight in the role of membrane cholesterol in the entry of pathogens into host cells. And Chattopadhyay has used fluorescence-based microscopic approaches such as fluorescence recovery after photo bleaching, fluorescence correlation spectroscopy, and fluorescent resonance energy transfer, to provide useful insight into organization, dynamics, and function of membrane receptors. Overall, his work has contributed significantly to the understanding of membrane recognition and dynamics and the interplay between membrane lipids and proteins, especially in neuronal membranes, and its implications in healthy and diseased states. Professor Chattopadhyay's pioneering contribution in membrane and receptors biology and biophysics have been recognized by several awards and prizes. These include the World Academy of Sciences, Third World Academy of Sciences Prize, Shanti Swarup Bhatnagar Award, Ranbaxy Research Award, Professor G.N. Ramachandran Gold Medal, ACRB Distinguished Fellowship, Professor G.N. Ramachandran 60th Birthday Medal, and J.C. Bose Fellowship. He is an elected fellow of the World Academy of Sciences, Royal Society of Biology, Royal Society of Chemistry, and all the Indian Academies of Sciences. Professor Chattopadhyay has served on the editorial boards of a large number of journals that include Biophysical Journal, the Journal of Physical Chemistry, Biophysical Reviews, Journal of Neurochemistry, BPA, Biomembranes, Journal of Membrane Biology, APBS Letters, IUBMB, Life, and ACS Chemical Neurosciences. He has mentioned, he has mentored a number of PhD students and has authored close to 300 research publications, mostly as a first or senior corresponding author. Total citation is more than 14,600, H index 65, Item index 220, 2 monographs, and national and international patents. He has delivered more than 600 invited lectures all over the world, including keynote, plenary, colloquium, and award lectures. Professor Chattopadhyay has organized a number of successful international conferences. He is a popular teacher and has distinguished and has designed and taught courses on biomembranes and fluorescence spectroscopy for PhD students in India and abroad. Professor Chattopadhyay is involved with science awareness and popularization programs among high school and college students in India, and national level workshops on manuscript and grant writing intended for students and junior faculty. So this is the material I had. I'm sorry that I could not read very fluently because some problem with my eye. Anyway, this introduction was necessary just to have a feeling how great is our today's speaker. So with this brief introduction, I invite Professor Chattopadhyay to deliver a very important endowment lecture of the Indian Chemical Society, Acharya P.C. Rai endowment lecture. With this, Professor Chattopadhyay, please.
Thank you, Professor Mukherjee. And thank you, the organizers, for this award. It's a very humbling award because it's a very prestigious award. Professor P.C. Ray was not only a pioneering scientist in India, I should say in Asia, and but he was also a nationalist and an entrepreneur in an age and time when there was no entrepreneur really from science in India. If I remember correctly, he started Bengal Chemical as far as back, probably something in 1890s, 1892. And when I was a school child, I used to use some of the products of Bengal Chemical. So now I understand what kind of foresight, vision, and boldness is needed, along with good science, excellent science, to have this kind of in those days under British rule. So I'm humbled and thank Professor Mukherjee for chairing the session, the organizers of the award, and also Secretary Professor Sinha and others for conducting this meeting in these difficult times in this kind of a mode. Okay, so I'm going to talk to you about, well, I chose a topic which also, is the right topic for Professor for Acharya Prafulla Chandra Roy, because I'm going to talk about a set of proteins called G protein coupled receptors, GPCRs, which is most drug targets. About 40% of drugs target this. So there's an application-oriented biology. I think a person really would have liked it. You know that we are working on not blue sky science, but also something that can be utilized. Okay. Now, just a brief introduction. Protein coupled receptors are very predominant membrane proteins, integral on the plasma membrane of the receptor. Mute other mics, please. Please mute all the mics because there's some disturbance coming. Thanks. So what is the function of GPCRs? They broadly connect the outside of the cell to inside of the cell. Our body is made up of small cells of micron size, tens of micron size, I should say, and signaling has to happen for us to feel healthy. And if signaling doesn't happen, you feel sick. Like you feel sick when you have COVID. Something happens in the signaling at that time. So GPCRs are big nanomachines which actually support that function. They are among the superfamily of membrane proteins. But most important, as I said, the 40% of the drug targets are GPCRs, and that's very important. 25 of the top 100 best-selling drugs globally are G protein coupled receptors. So I told you this. I'll show you some data to support this. So you can see that 36% of drugs approved by FDA today, Food and Drug Administration in USA has approved GPCRs as drug targets. Even before GPCRs were discovered, they were discovered in the 70s. They were drug targets, but people did not know those molecules are actually GPCRs. So I'll tell you what is our research with these molecules. And there is more. Although today 40% of GPCRs represent current drug targets, actually there are more than 800 GPCRs in your body. And the only small percent, about 15% of those GPCRs are actually drug targets. So there is this hope that the other 85% will also be drug targets at some point in time. So there are potential drug targets for diseases that are difficult to treat by currently available drugs that could be treated by GPCRs that are not drug targets today. There are drugs that cannot be, there are diseases that cannot be treated by presently available drugs, and there's intense research going on all around the world to find out new drug targets for GPCRs. So if I give this talk a few years from now, maybe 60, 70, 80% of drug targets will be GPCRs. And that's an exciting thought, not only as a GPCR biologist, also for younger students and postdocs, younger scientists who are working on GPCRs. Because it's nice to work with something that's very good for basic science, but also has translational potential. In addition, there is a feeling now that up till now, all the drugs that we use are already targeted by GPCRs are, based on GPCR's function in the plasma membrane, it's the outermost membrane. But now we know that GPCRs can signal or function even when they are going inside the cell. There are nucleus, there are endosomes. So the possibilities just become more, that more and more GPCRs in the coming years could be accepted as drug targets. Okay. So we work with a G protein coupled receptor, a serotonin receptor. This is serotonin, the structure is shown in the left. And this is, as you can see, is an analog of tryptophan. Actually, it's a very closely analog of tryptophan. It acts as a neurotransmitter in the brain. And it is present in a variety of organisms, ranging from early organisms to very like fruit fly and nematodes to humans. And what is the job? It basically keeps you happy. So serotonin is low in your synaptic cleft, you'll be unhappy. A lot of talk about antidepressants these days. Most of these antidepressant drugs are based on serotonin function. Signaling involves modulation of cognition and behavioral function. So naturally, when the signaling is not right, you get into disease like depression, anxiety, schizophrenia, obsessive compulsive disorders, and others. Now that we are going through this horrible pandemic for the last 2 years, a lot of people around us are mentally not happy because of this unusual time we are going through, and many of them have problems. So it's a very, very, practical signaling pathway in us. And if the signaling is right, we are happy. Signaling is not right, unfortunately, we are not happy. Now, when we started the work, we realized this is a close analog of tryptophan, and tryptophan is actually a very nice amino acid which is also fluorescent. And in our, I also did a lot of biophysics, especially in my early years, and we used to work on tryptophan biophysics to find out more about membrane protein structure, function, organization. So is serotonin fluorescent because it's so closely related to tryptophan? Interestingly, neurobiologists who used to work with serotonin at that point didn't seem to know much about it. So we thought it was worthwhile to look up whether tryptophan is fluorescent. We did those experiments and found out it's not only fluorescent, its fluorescence is very different than tryptophan in terms of nature. And actually that fluorescence can be used for finding out more about serotonin receptors. So that's the paper we published at that time by Physical Journal. Now serotonin, like many other neurotransmitters, bind to a bunch of receptors in our body, depending on the signaling that subtype of receptor carries out. So as of now, there are 16 or 17 different types of serotonin receptors shown here. We work with serotonin 1A receptor, so it's highlighted. The 5-HT3 or serotonin 3 receptors are ion channels, so they are not G-protein coupled receptors. They are actually different class of family. But the others are all G-protein coupled receptors. Without going into much detail, I will tell you this because I know this audience also has a lot of students and younger colleagues. You know, up till today, none of the G-protein coupled serotonin receptors has been purified from natural sources. Now you may ask the question, why? Protein purification is not proteins are purified. Membrane protein purification is slightly difficult, but that also has been purified. Problem is the amount of serotonin 1 receptor you find in, for example, the brain tissue which has it, let's say hippocampus, is so small that you don't get enough after purification. So people clone these genes into cells and then make it, but that's not the natural proteins. And that's a challenge we have. I want to tell this because people have this myth that everything can be solved by omics, proteomics, lipidomics. No. In some cases, biology could be difficult, and we need different technologies to address this. Okay, so where is serotonin 1 localized in the brain? In hippocampus. Hippocampus is that part of your brain that stops and storage of memory. So if there's some kind of accident, auto accident or motor accident, you will get hurt in the hippocampus. You could lose memory temporarily or permanently. So all our initial work done by my first student, Thomas Pocodil and others, was done by hippocampal membranes having purified pure serotonin receptors active. They are not biochemically pure, but they're pure in terms of the localization membrane. Now let me tell you what is the big question that you're asking. GPCR is a big field even when we started, and we had a small lab in CCM. What can you do that is novel? So that's where I want to introduce this slide. GPCRs were discovered in the 1970s by Robert Lefkowitz's group in Duke University in North Carolina. And at the same time, Govind Khurana, our own Govind Khurana, after getting his first Nobel Prize in nucleic acids and gene synthesis, he started working on membrane proteins, and he also started to look at, so these are the two pioneering laboratories in India. We're working on two aspects. One is signaling. With GPCR signal, different G proteins get either inhibitory or stimulatory, and then cyclic AMP or MAP kinase, all kinds of signaling assays you can measure, and they depend on which cell type you are used, or pharmacology, because the doctor is right. But we argue that this membrane, this protein goes through the membrane not one, not twice, not thrice, but 7 times. So they cross the membrane 7 times, and we knew from the experience with other proteins and peptides that proteins that are bound to membrane integrally interact with the membrane, meaning the lipids around them affect the behavioral function of the protein, just like people around us influence our behavior, right? Good friends make us good, not so good friends, change their behavior. So the question we asked at that point, that can the lipids around GPCRs affect their function, and somebody must have done it. So we looked at the literature. Fortunately for us, unfortunately for them, we found out nobody has really looked into this. Now what is the big question here? The big question is if you look at soluble proteins, and about 67% of human proteins are soluble proteins, are global protein. If you know sequence, temperature, pH, ionic strength, presence or absence of denatures, you can predict their folding at least in vitro. In vivo, of course, there are chaperones, which, because cell is a very crowded place, they guide the protein to fold right. But we know enough about them. We know a lot about them actually. What about membrane proteins? They're also polymers and amino acids. They also need sequence. You need to know these issues, but this is not enough. These are necessary but not sufficient for predicting folding and hence function of membrane proteins. What do you need to know? What is missing element here? What is so-called substance X factor? Close contact with the protein. So the nature of lipids in the close contact with the protein could change even if the composition of the membrane may not change. And that is not easy to find out by conventional biochemical techniques. And hence this really took time. So we asked the question, so membrane protein folding and their function depends on closely spaced surrounding lipids. So two questions we asked. One is, which class of lipids interact with GPCRs for maintaining their function? What are the good lipids for GPCRs? And if we can find them, this is the basic biology question, then what happens to human health if the biosynthesis of such lipids is defective? Lipids are made in your body by a series of enzymes, by catalysis, enzyme catalysis. And those enzymes are coded by genes, of course. So if there is a mutation in the gene, that enzyme will not be, correctly folded. So it will not do its job right. Then you get that lipid in less amount. What happens to human health? These are the two questions. So I'll tell you today that fortunately we have progress in both, and we'll talk about it today in this talk. So first lipid that we found after a lot of try actually, because there's no literature to follow, there's nobody in the West who has done this before us, was cholesterol. Let me tell you a little bit about cholesterol. Now this is cholesterol molecule. Chemically is an interesting molecule for three reasons. One is cholesterol has these three parts of the one is the flexible alkyl chain, very floppy. This one double bond, but it's amazingly almost planar. Now we all know from school chemistry that benzene is planar, cyclohexane is not planar, sp2, sp3 hybridization. This molecule has a very interesting stereochemistry, and this planarity, semi-planarity, not exactly planar, adds function to the cholesterol. If you put one double bond or take one double bond away, it is no more cholesterol, and the difference in biology or medicine can be life and death. Every lipid has to have a polar group, a water-loving and a water-hating group. Water-loving group for cholesterol is OH group, which is one of the smallest water-loving group. It doesn't have a big head group like phosphatidylcholine. All these is reflected in biology of cholesterol. I'll come back to that. Okay, on the top of it, our receptors in brain, and the brain cholesterol has a very interesting role. Only 2% of your body weight is in brain, but 2% of the body mass is in the brain, but about quarter of your cholesterol in the body is in the brain. That means that most of the cholesterol in your body, a quarter, is actually in the brain, in spite of the fact 2% of the body mass is in the brain. Brain cholesterol is present mainly as an unesterified form. Cholesterol can be present in two forms and is made for making synapses, the contact between nerves, which makes you, the nervous system work. Cholesterol does not cross blood-brain barrier. Cholesterol in the blood or in the body is made with a different, in the place than cholesterol in the brain. That's interesting, and that's why broad defects in cholesterol metabolism can give rise to very interesting diseases called Smith-Lemke syndrome, where people don't live too long and they don't have cognition. And we work with this disease in our laboratory. Now, cortical cholesterol content has been shown to be lowered in mood disorders from post-mortem samples. Many of you know that people take statins, a drug called statin, if your cholesterol is high. And there are lots of people these days, even in India and mostly in America and other countries, where people take statin to lower cholesterol. But all is not well with statin, although it's a very good drug. So symptoms of anxiety and major depression are apparent in humans upon long-term statin treatment. These are medical results, of course, not our result. So putting it all together, brain cholesterol dynamics and the role of cholesterol in brain dynamics is not well understood. So how do we change cholesterol in hippocampal membranes? So this is what Thomas did, and again chemistry came to our help. This is a heptamer, methyl beta cyclodextrin, right? It's a polymer, it's a heptamer, and it is basically something that's polar out, it's inside, and you can see it can complex cholesterol, the 2-to-1 ratio, first postulated by Ronald Breslow in Columbia University, 1986 in the JACS paper. And you can remove cholesterol from the membrane this way. And if you want to put back cholesterol, enrich cholesterol, you can make the complex in a test tube or a Pindorf, and then incubate. And depending on how much cholesterol you use, you can enrich the cholesterol. And then there are ways to measure this cholesterol in the membrane. Now, because this is polar and this is non-polar, it's very easy to separate them by a centrifuge. Okay. So Thomas Puckeri, who is now the chairperson of biology department in ISAR Pune, and a couple of years back at Bhatnagar Award, was my student who started this work. Thomas showed that if you take hippocampal membranes, having active serotonin 1 receptor, and you deplete cholesterol by methyl beta cyclodextrin increasing amounts, your cholesterol goes down, but also activity of the receptor goes down 50%. What is the activity here? Activity means ligand binding. So this was published in this journal that time. It was the first paper where it was comprehensively shown that our receptor, serotonin 1 receptor, needs cholesterol for function, ligand binding and G-protein coupling. Now, at that point, we only knew our receptor. I'll tell you a little later how many other receptors have been discovered by us and others. So we are very happy about this. And then Thomas also showed if you can put back cholesterol by the method I showed you, and we can only put back 70% because hippocampal membranes are very lipid rich, difficult to put back more. We get 70% activity back. So it is reversible. It's not a covalent damage that you do. It's not an insult to the protein. So once we did that and we published this paper, there are a lot of curiosities around in our lab and other labs around the world. What is the mechanism? Now, when you change cholesterol of membrane fluidity or dynamic changes, we quickly found out that was not the reason we are getting this activity, because the other agents like alcohol, for example, that changes membrane fluidity, but the functional loss is not that much. So we predicted that the mechanism is local interaction, specific interaction, that cholesterol interacts chemically, non-covalently with certain portions of the protein, and I'll tell you which portions are in the later part of my talk, and that changes local conformation of the protein, not global. It's not denaturation or something, and that gives rise to this change in function. However, it's the unpurified protein. How do you prove it? How do you prove such a mechanism? You can say a mechanism, but it doesn't stand, scrutiny unless you can prove it. So we wanted to at least validate it whichever way we can. So that is where good students came. Thomas and then Yamuna and then Sandeep did a lot of work to prove this hypothesis is right. The major element is we are saying cholesterol interacts with the receptor, changes local conformation, and that makes it inactive. If we do not allow cholesterol to interact with the receptor, can we achieve this change in function, ligand binding? So no physical depletion. We can do it chemically by using a molecule called cholesterol oxidase, which is an enzyme. It converts hydroxyl group to keto group in cholesterol. Cholesterol is formed. Cholesterol doesn't have the same property as cholesterol. So we did this and found out ligand binding, doesn't change in that case. Similarly, we could compress cholesterol by agents like antifungal agents, nystatin or detergents like digitonin. They compress cholesterol. They don't physically remove it, but that if we complex it prior to incubation with the ligand, then that cholesterol is already bound to something. It cannot interact with your receptor. And yes, our results are same. Ligand binding goes down. Then finally, we also were able to put this receptor, express this receptor in various kinds of cells. And we showed that if you inhibit cholesterol biosynthesis, inhibit the enzymes, various enzymes that make cholesterol, and we showed two pathways here. One enzyme is statin. That is the enzyme that is the very good, very blockbuster drug. It's called proximal inhibitor, which is the first step. It inhibits HMG-CoA reactase. But you can also inhibit the last enzyme. There are 22 enzymes needed to make cholesterol. It's called 7-HCl. our work showed that whichever way you make cholesterol inhibit, the activity of the receptor goes down. Doesn't matter, first step or last step. So taken together, this slide means the membrane cholesterol is necessary for receptor function, irrespective of the way you set up the experiment. You can set up the experiment differently, how not to interact, how to prevent interaction of the receptor with the cholesterol, but your result will be the same. Okay, now let me tell you a little bit about where we are now. That was early 2005, 2010. So where are we now? Well, our group has shown in collaboration with other groups that adrenaline receptors and T2R4 beta test receptors also shows cholesterol dependence of function. So one group is in JNU, Georgia University, another group is in Canada. We have shown in collaboration with them. But others in the world has picked up now. And if you look at the literature now, about 60 GPCRs, geopolitical receptors, have been shown to exhibit cholesterol dependent signaling and function. And we are very happy that we showed the first one in 2004. And this list keeps growing. Now, however, it is not a rule that GPCRs have to inhibit cholesterol. The receptors like cannabinoid receptors, neurotransmitter receptors, which do not exhibit cholesterol dependence. If you deplete cholesterol or don't deplete cholesterol, their function doesn't change. Now, what decides some function of some GPCRs depend on cholesterol, membrane cholesterol, and some GPCRs don't show any dependence is $1 million question. That's not still known, but I'll tell you some possible clues to it in today's talk. Let me tell you a little bit about GPCR structural biology, how we have advanced in recent years. So I told you that membrane proteins are difficult to purify. They are even more difficult to crystallize because it's very difficult to get structures. And G protein coupled receptors are very flexible molecules. Just like it's difficult to take a picture of a person who is moving constantly, similarly, it's difficult to get a crystal structure of a very flexible protein. But so up to 2000, there's only one structure. First structure GPCRs came in 2000 from Cleveland, by Chris Palczewski of Rodopsin. Up to 2007, there was only that. Then there are two structures in 2007. Then there's a huge, gain because we have more technology. Now, 2007 was an important year for us because that was the year we found out beta-2 adrenaline receptor, the receptor that Robert Lefkowitz, who discovered GPCRs and got Nobel Prize for it in 2012, was to work in, and his postdoc, and who also shared Nobel Prize with him, Brian Kobilka, showed in a Nature, in a science paper, that cholesterol is bound between two GPCR monomers. We cholesterol affect function, but we did not have this kind of pictures to show. These people have pictures to show, but they don't have functional data. So if we put our data with their data, which is what we did when we contacted them, then it makes perfect sense. Not only that, there are series of GPCRs after that Ray Stevens showed, which he also collaborated in this structure, that there are beta-2 receptor, adenosine receptor, glutamate receptor. Many of the GPCRs show bound cholesterol structure. It has become very popular now. So then we realized that cholesterol binding is quite a common property of GPCR. I'll show you some statistical data on this. So statistical data shown here, very recent data. This shows that 40% of unique, this is from protein data bank, about 40% of unique GPCRs display bound cholesterol molecules, and about 27% of PDB structures show bound cholesterol molecules. So 40% or 30%, depending on whether you go for PDB, because each molecule they are various PDB. This is the growth of GPCR structure. You can see from 2010 or 11, there are a lot of structures. The green ones are cryo-EM microscopy. So cryo-EM is taking over, and it's much more than blue, which is the crystallography. So now, as you know, cryo-EM is very accurate. It also can give you very nice structures of flexible molecules. But about 1/3 or so percent shows bound cholesterol. So it's a fairly, robust and statistically important characteristic of these structures. Now, if you say how many cholesterols are there in this structure that I showed you, it varies from 1 to 10, and then there's 16. But this is actually misnomer because 16 is for a dimer, so actually per monomer is 8. So 10 is here, only one molecule, and that molecule happens to be serotonin 1 receptor. This this year in March in Nature. So I'll show you the structure. But when this structure started coming in 2007, we in our lab thought, if cholesterol binds to GPCR for function, does it bind anywhere? GPCR is a protein of about 420 amino acids or some specific places. So we found out this sequence called CRACK sequence, cholesterol recognition interaction amino acids consensus, tyrosine in the middle, leucine, valine, or arginine and lysine, and there are some other amino acids. And these traditionally is supposed to be cholesterol binding in some cases like gavioli, but these are soluble proteins. Do membrane proteins in general and GPCRs in particular has the sequence? Looked up literature, there's no reference. So we did our own thing. And how does CRACK help? Well, CRACK binds valine and leucine. I showed you it binds to, so that binds to cholesterol. I showed you the structure of cholesterol, this part. Then the tyrosine ring interacts with the double bond here, the ring structure. Okay, and then the polar hydroxyl group can interact with the arginine or lysine, which are charged at pH 7. Now, we found out that the other CRACK motifs in GPCRs which show cholesterol sensitivity, we did in 2010 or 11, rhodopsin, beta-adenine, or serotonin. Now, CRACK motif can be as long as 13 residues or as short as 5 residues. Our receptor, we thought there are 12 residue CRACK motifs, transmembrane helix 2, 5, and 7. The trouble with bioinformatics is, statistical thing is, it will tell you where can cholesterol bind, but it's not sure. You have to do experiments. You cannot learn all this by doing computer simulation only or computer search. So we need to find out which one of these are responsible for our cholesterol binding. Okay, so we have been doing this two approach. One is experiment, one is simulation. Simulation we do in collaboration, a tight collaboration with Dulbas and Gupta, who is a physical chemist at National Chemical Laboratory, Pune. And we have been doing so-called coarse-grained simulation because you can do long time scales, which is very good for GPCRs. Also, our computation power at that time, at least even now, is not so great to do atomistic simulation for a long time for a big protein with water, metal ions, and lipids. So we have done a lot of work. I'll only show you the summary in 2 slides because my time is 5-6 minutes to finish my talk. We have shown that cholesterol binds to GPCRs and is on and off. So it's on rate, off rate, and its microsecond time scale is dynamic, weak, but crucial. Some are slow exchange, some are fast exchange, and at any given point in time, there will be some cholesterol molecules bound, and that decides the function. So but it's a dynamic, it's not static. It's not that once it binds, it binds. So in terms of physical chemistry, it's a, this is the energy level diagram. This is KT, at room temperature. So it is not very deep minima. It's the energy landscape that corresponds to a series of shallow minima integrated by low energy barrier. So things can flip out with little change of pH, little change of temperature, some change of ion exchange, things can flip out. So like in biology, there's a major difference in biology and chemistry. Very small change in pH or ion exchange can change in biology very big things. And that's also shown here. So we also found out how to quantitate how much cholesterol is binding there. So these are the CRACK motifs, the green ones, and these are the amino acid residues. We found out something called maximum occupancy. If 3 microsecond simulation, we find a cholesterol molecule always near a particular portion of the G protein receptors, we'll call it 100%. So in 3 microsecond, cholesterol molecule is always in that residue. Now you see, transmembrane helix 2, there is CRACK motif and cholesterol is bound there. But there are also places in the protein where cholesterol binds, like here, which doesn't have a CRACK motif. And there are CRACK motifs where cholesterol, is not binding that much. So it is not all or nothing. It's shades of gray. So we have to be careful. Okay, it's good to speculate this, but we need to find out specific cases for which we need to do experiments. Okay, so these are the CRACK motifs for the experiments. What can we do? Well, we can do mutations, right? And this is quite difficult to do for membrane proteins, but we did tyrosine to serine, lysine to alanine. We did series of single and double mutations shown here. This was done in collaboration with Dr. Panikkar, National NCBS, National Center for Biological Science in Bangalore. And we could create these mutants, express them in cells, make sure we are not overexpressing, so the physiology is right. All this we did and express them in CHO cells. Now, I'll show you the results. Let me show you what is the function we are measuring here. The serotonin receptor is a GPCR, right? So GPCR interact with the G protein, trimeric G protein. Now this receptor interacts with inhibitory G protein. That means upon binding by agonists like serotonin, it reduces cyclic AMP levels because it is negatively coupled to adenylyl cyclase. And so when you measure cyclic AMP, it is less F signaling is happened than normal. That's our assay. And it's the best assay to do because it's a very close step near the membrane. If you do further downstream assays, you may miss the connection with the membrane. So this is the assay we have set up in our lab quite some time back. So this one was done by Aditya, who just left early this year for a postdoc in Michigan, Parijat, who has finished his PhD and is just finishing up a few more things. So we did these mutations and then we did the cyclic AMP assay. Now let me carefully go through this. You see, if you take the wild type shows inhibition of decrease in cyclic AMP, which is what we expect. Wild type is acting, but in depleted cholesterol it doesn't show that. So wild type is sensitive to cholesterol. Interestingly, cholesterol sensitivity signaling is retained in all these mutations, like when tyrosine to serine or. And again, only two cases where we found cholesterol sensitivity is knocked off or not there is where we have replaced K101, lysine 101, transporter helix 1. So in both single and double mutants, lysine means you touch the lysine and the membrane doesn't even know, the protein doesn't even know whether cholesterol is depleted or not. So the signaling doesn't change at all in the mutant and the normal. You can see this. We have done significance analysis. So our conclusion from there is lysine 101 in transporter helix 2 confers cholesterol sensitivity to serotonin receptor function. That's a very, very interesting fact because although there are 60 or so GPCRs whose cholesterol sensitivity has been shown, nobody has shown till now what could be the molecular mechanism. So we are happy about this. This was published in Science Advance early this year, maybe in June. So recent cryo structure of this receptor come out in Nature, I told you in March, and this one of the structure shows 10 cholesterol molecules bound. You can show the blue ones are cholesterol molecules. The APO receptor, the receptor without the ligand, displays 10 bound cholesterol molecules. This is the maximum number of bound cholesterol in GPCRs till date. This was structured by a Chinese group which published in Nature early this year. And we did coarse-grain simulation, of this in collaboration with Yana Serent of Barcelona. And our simulation shows amazingly. So this is our simulation. This is cryo-EM structure. This K101, lysine 101. This is the cryo, the location from the cryo-EM. We show a very tightly bound cholesterol in the position almost identical to the one observed in recent cryo structure. That is there because of different forces that we know it interacts with lysine. So our simulation is very realistic because and we think that is the one that gives cholesterol sensitivity. So both experiment and theory and simulation we did, and that kind of hand in hand went. So I'll just end by, so this is probably the first example of GPCRs showing molecular mechanism of their cholesterol sensitivity. This is my group. One or two people have left recently. We haven't taken a picture yet because it's not fun to take picture with your mask on. These are my, some of the older people who have left long time back. Thomas is there, Yamuna, and but people keep. Our collaborators, we cannot live without them. So this is Durba, this is Dr. Panika, this is Lawrence Salome from Toulouse. We have a grant with her. And this is our money. We get money from different sources. We're very fortunate. We're very privileged. Thank them. This is CCMB, which is a laboratory of biology, but we know biology is nothing but, it's a mixture of chemistry, physics, and biology. So our biology is based on is mixing issues and addressing a problem using all knowledge, not only compartmentalized biology. Hyderabad, for those of you who don't know, is a nice city. It's a twin city. Hyderabad is separated by a lake with a statue of Buddha, which is supposed to be the tallest monolithic one-stone statue of Buddha. It's a local stone from somewhere about 100 kilometers away from Hyderabad. I will end my slide with this, then with permission of chair, with a slightly advertising slide. I just got a Bharatiya fellowship and some grant with it. So I'm recruiting some students. We have fellowships for students and postdoc. If somebody is interested, can write to me, and I'll be happy to respond. Thank you very much. And again, thanks for this honor, and thanks Professor Mukherjee for chairing this session. Thank you.
Okay. So, on behalf of Indian Chemical Society, I offer my heartfelt thanks to the distinguished speaker today, Professor Amitabh Chattopadhyay, for giving a very brilliant lecture befitting to the name of Acharya P.C. Ray. Since this is an endowment lecture, there is no question answer session, but I am sure that this will generate much curiosity. So if you have anything, so you may correspond with him you can write to us, we can forward your queries to them, or you can directly contact him. So I declare this session closed, and I hand over the charge to Professor Sinha.
Sir, just to declare with us, I
Yes.
will hand over the medal of Acharya Prafulla Chandra Rai Memorial Lecture.
Okay, sure.
Yes.
Yes, Sobaresh might say something.
No. I just congratulate him on receiving this medal.
Okay.
So nice.
Thank you.
Amitabh,
Thank you.
I shall be meeting you soon.
Thank you.
Okay, Chitto, do the needful.
Thank you, sir. Thank you for chairing, sir. Chemical Society. Thank you, Professor Chattopadhyay, for giving your lecture. And now I request Professor Ashutosh Ghosh. Professor Ashutosh Ghosh, one of the members of the Indian Chemical Society, as well as former scientist in charge. And now he is the Vice Chancellor of Indian University, Rani Rajiv Gandhi University, Erasmus University, and now also the former Vice Chancellor of Calcutta University, Professor Ashutosh Ghosh, to chair the next session of the Priyaranjan Rai Memorial Lecture by Professor Ghosh. Professor Ghosh,
Okay, thank you, Professor Sinha. So, our next lecture will be delivered by Professor Pradhyut Ghosh. I think he needs no introduction, as all of you know him. So just briefly, I will say something about you. As all of you know, he is now the professor at the Indian Association for the Cultivation of Science, Kolkata. He did his BSc Chemistry Honours from Calcutta University and also MSc from Calcutta University. He did his PhD from IIT Kanpur under the supervision of Professor Porimal Bharadwaj. After his PhD, he had several postdoc with a Humboldt Fellow in Germany and then also in the Texas A&M University, USA. And then after just completing his postdoc assignments, he joined in the Central Salt and Marine Chemical Research Institute at Bhavnagar in 2001, and he was there from 2001 to 2007. Then he joined at Indian Association for the Cultivation of Science. He was the professor from, he was associate professor. In fact, he joined as associate professor. Then he became professor in 2011, then senior professor in 2016, and then head from 2012 to 2015, associated dean, and now he's the school chairman of the Indian Association for the Cultivation of Science. And Professor Ghosh has several awards, many awards. I will mention only few. He got the Swarno Jayanti Fellowship Award in 2009. Then he became He got the Chemical Research Society of India Bronze Medal in 2012. Then he was awarded Shanti Swarup Bhatnagar Award in 2015. He became fellow of Indian Academy of Science, Bangalore, 2016, and this year in 2021. 2021, he became the fellow of Indian National Science Academy. So he is one of the leading scientists, especially in the field of inorganic chemistry in India. And now I request Professor Ghosh to deliver his lecture. Professor Ghosh, please.
Yeah, thank you, Professor Ghosh, again, so for your kind introduction. And good afternoon, everybody. And this is very difficult time. I'm just in between you and your lunch. So I'll try my best. So I will finish within 30 minutes time slot. So let me go to my slides. Yeah, at the outset, I would like to thank the Indian Chemical Society for considering me for this Professor Priyadaranjan Ray Memorial Award lecture. And I'm extremely honored to receive this recognition. Today I'll be talking on anion and ion pair recognition towards environmental and industrial applications. So before going to this lecture, I would like to pay my humble tribute to one of the great inorganic chemists of our country, Professor Priyadaranjan Ray. Professor Priyadaranjan Ray actually, he's famous for his seminal work on rhombic twist mechanism and popularly known as Ray-Duff twist, coordination chemistry, stabilization of metal ions in unusual oxidation state, magnetochemistry, and so many things. And he served as the director of IACS from 1956 to 1958, 2 years, just after demises of Professor C.V. Raman, Professor Meghnad Saha. And after that, actually, he joined IACS, I think, sometime 52. So most importantly, he's the person who built Department of Inorganic Chemistry at IACS in 1953. And we are very happy that we are now in, actually I joined in that department as an associate professor, but now this is School of Chemical Science, and just I would like to rectify that present chair is Professor Abhishek Dey. So just recently I have completed my tenure. So that correction I am making. And before that, Professor Priyadaranjan Ray served Calcutta University from 1919 to 1952. And yes, again, I was a MSc student from that university. And most importantly, again, so he started his professional career, independent career in City College, Kolkata, from 1914 to 1919. And again, I did my BSc from City College. So all three places, so this is really a great honor to me. And I really enjoying this particular recognition. And in this respect, I would also like to mention this following quote from this, like Indian National Science Academy biographical memoirs of Professor Priyadaranjan Ray. He is aptly considered a doyen of inorganic chemistry in India. Neither glamour nor publicity had any attraction to him, even though they followed at his heels. So this is Professor Priyadaranjan Ray. So I'm very happy that I'm giving this award lecture. At IACS, we are particularly working in different areas. Sorry. I'll make it full screen. Yeah. So these are the 5 different areas we have been working at IACS. This is anion and ion pair recognition. This is from the beginning of my career I'm doing. Chemical sensing of ions, molecular self-assembly, interlocked molecular systems, and recently we have started supramolecular catalysis. But today, I'll be talking on this anion and ion pair recognition. And here we are focusing both basic science, that is coordination chemistry of anions. Along with that, from that knowledge, we are trying to develop selective receptors to address some of the issues in chemical separation, clean environment, safe water, this kind of thing. But this is, I don't want to go in detail, but it is sure that anion chemistry is very important to address many of the issues we are facing today. So say, for example, say if we want to really want something like a fluoride-free water selectively, or arsenic-free water, or nitrate and sulfate, definitely we need like a real chemistry that, okay, it is selective. Otherwise, membrane technology and all these things, whatever we see, that is actually that it rejects all kinds of ions and all those. So for selective removal, we need to develop the right chemistry. There are many industries, so they are producing a lot of industrial wastewater, and it contains a lot of ions and these which are carcinogenic sometimes. And say, for example, in steel industries, this cyanide is a big problem. And this is obvious that phosphates in agriculture, so that is just the eutrophication of river takes place, rivers and lakes, so which disturbs aquatic plants and all aquatic environment. So therefore, there are many lists. Even say salt extraction from natural, a lot of interest in chemical industries. So if you want to have very purest form of the potassium fluoride or potassium chloride. So if we have some kind of receptor which can capture potassium, but we need that for fluoride, otherwise it will not be separated. So, and there are other like a nuclear waste reprocessing. All these things are very important thing. So which anion chemistry is associated. But these factors that complicate this anion chemistry is many. So something like that, these anions, they have high solvation energy. So, one can bind those things through weak interactions. So this is now difficult. The high solvation energy you have to overcome with weak interactions, because through hydrogen bond or this kind of thing, there will not be any coordinate covalent bond like metal ion. They are different size. Their size is larger than normal cation, and they are not like one size is spherical for metal, and this is spherical, linear anion, planar, tetrahedral, octahedral, all kinds of shapes you can think of. They are very much pH dependent. Suppose you are targeting phosphate. So phosphate PO4 3-, just by you have a receptor for PO4 3-, suddenly this pH changes, you will get, it will convert it to HPO4 to 2- or H2PO4-. It's very sensitive. So all these things are that complicate this anion chemistry. So in nature also, if we see that sulfate binding protein or this chloride channel, all these things, they are recognized within a klepton cavity. So our approach is to make like a capsular assembly or a cavity type of molecule, like this is C3b symmetric cleft, or from their covalent capsules, or dimeric assembly of this C3b symmetric molecule to make dimeric capsules and all kinds of things, which will generate proper the enclosed space, size, and required functionalities. If we can put, we can bind selectively some of the ions. So what we have been doing, like say, we are basically using different kinds of platforms. Like here you can see that this platform we use, and then to construct different kinds of receptor. And recognition element means, as I mentioned, that this is through hydrogen bonding interaction. So ammonium, amide, urea, thiourea, all these recognition elements we use for hydrogen bonding purpose. And these are the weak interaction, like a NH anion interaction, or CH anion interaction, anion pi interactions. Recently, some kind of halogen bonding and like chalcogen bonding, all these interactions all are weak. Through that only we have to recognize them. And to control this acidity of these, say for example, NH group, we use different kinds of attached units. So that it will give you the proper acidity so that it can bind the proper anionic species towards base. And using this kind of all units or building blocks, like playing with Lego, so we construct various kind of receptor framework, like as I mentioned, like a covalent capsule, 3-dimensional cage, or tripodal receptor, which will have C3b symmetric plate, or these two tripodal can make dimeric assembly to get like a capsular form, so that you can dissociate it, or like a higher generation, the hexapodal receptor, some kind of thing. So we have developed many such kind of receptor molecules, but anyway, I'm not going to talk all of this, but what I will focus is that some of these, some of the works, here I mentioned 4 works that which have some kind of potential applications towards of the basic science. So one is that the trapping of cyanide from steel plant wastewater, and then extraction of alkali metal salts, so that is for chemical industries, and capturing of carbon dioxide for environmental point of view using molecular capsules, and using that carbonated capsule you would like to extract sulfate or chromate, which makes water hard or some other problem in nuclear waste reprocessing processes, or extraction of parenate. This is basically to removal of pertechnetate, that is in radioactive waste, we get it, and that they are both are the same, this surrogate. I will come to that point. So if we can address that renate recognition, so that can be used for pertechnetate also. So that is the latest work we have been doing at the moment. So this for cyanide one, you can see that cyanide actually in steel industry, whatever after processing, they throw the water, so that contains 6 to 10 ppm of cyanide. And not only cyanide, it is actually this is contaminated with high content of chloride, sulfate, ammonia, nitrate. That means you need a receptor which can selectively trap cyanide of such low level, 6 to 10 ppm, in presence of higher concentration of sulfate, ammonium nitrate, or this kind of thing. And this toxicity level of cyanide in human is at 0.4 ppm, and these whatever these for cylinders is if you throw total water, then that is the wastage of water. So one can reduce, if you can reduce the cyanide level, that can be reused also. And this is from the Central Pollution Control Board. The discharge limit of free cyanide to the environment is 0.2 ppm. So there are different existing technologies for cyanide removal. This is like alkaline chlorination, sodium hypochlorite treatment, or chlorine dioxide, ozone treatment, photolysis, membrane technologies coming newly, and phytological kind of thing. And for this, actually, I'm not going to individual drawbacks of this treatment, but these are associated, like some of them just generate toxic byproducts, or high operating cost, or it increases total dissolved solid in your discharge water, or generation of chlorine gas and organic halogens, or some kind of, some takes longer time. So these are the many problems. So therefore, the steel industries, they are looking for alternative path or treatment for cyanide removal. So we are working like this kind of macro bicyclic octamino cage for anion binding. So this problem came from on steel industries to solve, to attempt. So we are working in this, like using this receptor to trap different kind of anion, and those are all protonated state. And we are doing, like say, by changing the degree of protonation, different kinds of selectivity and all these things. So I'm not going to, this is not relevant to this work right now. But this kind of protonated species cannot trap cyanide. So in that case, actually we are also working like say dicopper complex, binuclear complex. This is a N4 cavity, and N4 cavity copper can bind, and here you will get say copper, and copper generally prefer TPP structure, but it is getting 4 nitrogen and 4 nitrogen. So if it binds, so copper binds here and there, and then distance between two copper is around, from the crystal structure, it is 6.2 angstrom. So that 6.2 angstrom can be used like a cascade to trap smaller ion like azide or cyanide or this. So we showed that like a trapping of azide in between two coppers, and this is perfect linear structure. This is nitrogen copper, the nitrogen bridged, then copper, and this azide 3 nitrogen, copper and nitrogen. And other group also are working, like one group from UK, they showed that cyanide trapping. So we thought that we can use this kind of approach for treatment of cyanide contaminated water from still wastewater. And we picked up this particular dicopper complex. And from this laboratory experiment shows, like say, if you have 10 ppm cyanide standard solution we prepare using 2 millimole solution, we can see that we can remove 95% of the cyanide. And this is for standard, there is no interference. But this is a blast furnace water from steel industries, it shows like around 70% reduction of the cyanide. So that was kind of exciting result to them also, because this approach is new and this doesn't need any kind of modification in their setup for treatment. So this is kind of using like a dosing. You just put these chemicals and it will just purify the cyanide. It will complex the cyanide, free cyanide to complex cyanide. So after demonstrating this, they were interested to more amount of. So this is a compound, the supramolecular cage compound. Their demand was like that to produce 1.5 kilogram. So for bench scale studies. So what we did, so we did a short time period, we prepared 1.5 kilogram of that complex, and we gave them, and they analyzed it, and they showed that yes, this synthetic water is large scale, bench scale. They showed yes, it can remove like a more than 90% cyanide. But again, if you take industry wastewater, it is again like say. Depending upon the dosing concentration, you can 40 to 77% removal of cyanide from the wastewater, industrial wastewater. But again, say this is very good result to them, and because we showed that cyanide removal, that flocculant, we can recycle it also. That means whatever solid, because this is like a suspension we are using, it's not a purely soluble compound. So that unused thing we can further use, and from there we have done so many other studies like a ICP mass to see that how total dissolved solid is changing after treating with these chemicals and all these things. So it is showing that it is working fine. So and then we try to do this, what exactly is happening, that if you take this one and you put cyanide, one equivalent, it shows that trapping of cyanide inside the cavity. But if we put excess cyanide, this color is changing to colorless, and EPR also showing, yes, this is this copper first complex is forming, but again, that it is getting EPR silent, that is a copper 2 to copper 1 is converting. And this is reflected in your UV visible spectral data also. And then this is from the other group from UK, they showed that yes, the cyanide is one equivalent is trapped inside the thing, but if you put excess cyanide, actually it is forming copper 1 CN, this Cu6 CN12 kind of cluster kind of thing, and that is actually this now cyanide is trapping in this way. So we demonstrated that okay, this is happening. Now this is fine. So they, this industry, this whatever, this data still, they were interested to use these things. So they wanted to apply these things in their, like say, your large scale, like a pilot scale. And for that, whatever technology we develop or that procedure, that high scale production of this compound, so that we basically gave it to them, and they, from using like a help of third party, they prepare 500 kilogram of this compound, and they tried like their plant trial performed at each blast furnace, which they have different leveling. So when they are placed, and this 40 meter cube per hour, this water is going through that pipe, and that is treated with these our chemicals. That is from blast furnace, from coke plant also they have tried, and they have another unit in Odisha, that is Kalinganagar, that is 80 meter cube per hour, this plant. And all these things, they showed that again this is working, and that the merits of our compound is that the moderate to high removal efficiency of free cyanide, no sludge generation, no toxicity or low risk, and negligible change in TDS and negligible color formation, but challenges still remain the relatively high cost at this point of time. So, and this work is appreciated in their company also. This Tata Steel, they bag most innovative environmental project award, and this is from this fourth edition of CII Environmental Best Practice Award 2017. It was the Tata Steel owned the anion complex for the removal of cyanide from wastewater. So this is one application up to the pilot scale. One can we have demonstrated this compound work. So then, second point, I will quickly go that this kind of chemistry can be used to extract like a potassium alkali metal halides. So that is very important, like in separation technology, common living materials or medicine and maintenance or osmotic, all kinds of things. And challenges is that you have to get the selective receptor and all to overcome all this problem which I have mentioned. For example, if you target potassium fluoride, so potassium we know that crown ether is there, but fluoride we have to develop the receptor, and we have used two strategies. One is ditopic receptor strategy, like a single ditopic receptor with cation and anion binding sites. So both will be there, they integrated. And another is like a dual host strategy, to separate anion and cation host. So in this case, so from this we have modified how you can see. This I showed for the cyanide one. So we thought that let's make it a acyclic one, this tripodal thing. But this one, some other book they published that when it binds with protonated species, it forms C2B symmetric cleft. But by some using this like a quadruple moment of like benzene versus hexafluorobenzene, where you can see that is a minus 8.48 Buckingham is that benzene, and this is plus 9.50 for C6F6. So we thought we replace this phenyl with pentafluorophenyl group, and you can see that this magic like a pentafluoro, it's a capture bromide like C3B symmetric cleft. So C2B symmetric to C3B symmetric we can make by changing this chemistry. And that one was like a ammonium. So we this neutral version, the triamide, we prepare, and it shows that it just forms C3B symmetric cleft for chloride, and this is fluoride and water. So hydrated fluoride is trapped inside this cleft, and this is with chloride and chloroform, this kind of. So that means this tris amide can be used as like a anion, as your halide binding. So we took these two, crown ether for potassium and this tris amide for anionic part. So if we take this thing and do liquid extraction, like using chloroform layer, you take this, your one of these receptor, and in water you take the salt, try to extract. One of the components cannot extract, no extraction takes place. So L1 and L2, this nil. But if you put L1 and L2 together, you can see around 50% extraction of the salt. And we have done like a pH dependent extraction also. You can see that 4.5 and 6.3. So basic medium it cannot extract, but this pH below 7 it can extract around 50%. And we have finally crystallized. You can see that free receptor which was trapping fluoride and water, say in the complex, whatever extracted mass we have crystallized, we have shown that fluoride is binding and water, and this is potassium is binding with crown ether, and one of the carbonyl, this amide oxygen is forming coordinate covalent bond with potassium, and this is basically making this is like a polymeric chain, and we are extracting the potassium fluoride from the water. And we have established how it is going on, this mechanism, by extensive NMR studies and 2Z and all these things. There you can see that this is a 2 receptor, say KF6, if you put potassium is binding, and this oxygen, this carbonyl oxygen is forming coordinate covalent bond, and then this fluoride or fluoride is binding. So this is like a dual host approach. And another approach we use, this is called like say a ditopic. We have integrated this anion binding receptor here, and this is cation binding. And using these things, we have also shown that it can act cooperative effect towards anion binding. So from this, your binding constant, using tetrabutyl ammonium chloride or bromide salt, this is the association constant, and binding constant in presence of potassium. You can see this is a manifold, or many means at least 3 to 4 times. But this K value is increasing, and that is due to cooperative binding of potassium as well as your halide. But if you have tetrabutyl ammonium group, that cannot be done. So using this, you can demonstrate that this potassium, bromide, and other salt you can extract. And we have also done like a isothermal titration calorimetric study for this kind of binding and cooperativity effect. And then we move to this other one, like this linear cyanide I have shown, then spherical. But if we want to trap this oxyanion, this is like a transition metal coordination versus inner transition lanthanide metal ions. So it requires higher number of hydrogen bonding. So we moved from this amide to urea. So here you get 3 hydrogen bonding center. So when you are putting urea, so 2, 2, 2, 6, and actually this particular receptor from dimeric capsular assembly. So, and 12 hydrogen bond, they are centering towards the cavity, and which can trap different kinds of oxyanions. And this is the different anions. I'm not going in details. So this is showing that carbonate, phosphate, sulfate, you can trap inside the dimeric capsular assembly, all the crystal structure. And so this coordination number, this corresponds to hydrogen bond like 18, 15, 14, and 16, compared to 6, 7 for halides and all kinds of things. So now, once we established this thing, we thought, like, use this one, and it just dissolve it in organic solvent, put base. You can see that it is trapping this carbonate from air, carbon dioxide to carbonate, and the carbonate capsules. And overnight, you can see they're trapped inside, and you can just dissolve it in methanol and put some water and sonicate. You can separate out your ligand 1 second and recycle it again. So this is the thing. You can bigger picture. You can see that this way you can trap aerial carbon dioxide in the form of carbonate. And now using that carbonate capsule, we actually use for sulfate removal from like a extreme condition, like a pH 14, which is like a nuclear waste reprocessing, because this yellow study you see, that is basically from sulfur and sulfate, thiosulfate. During vitrification, they just dissociate and they just stop the process. So that's what say it is very important to remove this sulfate, phosphate before reprocessing. And this is a huge cost. They have, the process is estimated to take 70 years and cost 227 billion. This is for in America, whatever their nuclear waste they have for reprocessing, they have estimated this kind of cost. But before that, they have to tackle all these problems. And another problem is the TCO4 minus. So this just I will quickly go. And this carbonate capsule, we have shown that if you dissolve it in organic solvent and just this sulfate in water, it just remove quantitatively sulfate from water. So what it is doing, that carbonate is going to the water layer, and sulfate is like a metathesis. Sulfate is going inside the capsule. So that is, we have demonstrated, and that is actually in this receptor we have shown that it can trap carbonate, and you can dissociate by dissolving it, and you can trap again sulfate. So like metathesis, so carbonate is coming out, sulfate is getting in. So this is possible, and using that different kinds of receptor we have shown, like instead of pentafluoro, the metacyano, is chromate extraction. So chromate, sulfate can be extracted from water very nicely, and we have shown like that working pH for this system. Some of the things like a pentafluoro, it can work 7 pH to 13 pH extraction of sulfate. So this is about this. But the last part I'm going to go, that TCO4 minus and rennet. So this is like a technetium-99 is hazardous and radioactive pollutant of uranium and plutonium nuclear fission. T half is 2.1 into the 5 years. So but in lab we cannot work TCO4 minus, but rennet is the surrogate of TCO4 minus. So therefore we are working on a rennet recognition, and for that but both the TCO4 and rennet are important, different respect. So like a radio contrast agent or some kind of other applications, many applications are there. So that is obvious. So if we can extract those things, so here we have used like a hexapodal receptor, but imidazolium receptor, because rennet generally doesn't bind with this kind of amide urea kind of receptor. So we have developed like a imidazolium receptor, and you can see that with NMR with all kinds of ions, only rennet it shows that this triazole, the imidazole CH shift, so it is binding with rennet, and this is very interesting. It's water soluble, and if you put rennet, it will precipitate out, and if you crystallize it, you can get the structure that rennet is bound within in the pocket of this hexapodal receptor, and this is well characterized thing. And we have done this TEM, XRD, and FTIR, and removal efficiency in presence of other ions also very good. And finally, that like a pH stability, because definitely these are most important point for the application purpose. So both the thing that whatever product is forming and that our beer salt, that water soluble, those are pH resistant, and at various pH you can extract it. But for this particular one, challenges is here. So the initial concentration of rennet, if it is like a 500 ppm, we can get more than 80% extraction. A 400, when we are getting, it reduced from 84% to 75%. But 400 is too high. So for application purpose, it has to be like less than 100 ppm. And receptor should extract rennet where concentration is less than 100 ppm with higher removal efficiency. So for that, we have again designed that instead of that, here we had like a CH2 CH3, we have just replaced with vinyl group. And vinyl, when you get the monomer, this one behaves like the previous one, but we can easily polymerize it. So we now we have in presence of AIBN, we have made polymer out of it, and this polymer, you can see this now effect. This everything is fine. You see the last one, this initial concentration of rhenium 95.3 ppm. In this monomer, it shows 9.6% removal, whereas this polymer shows 99.1%. So based on that, actually, we have overcome that also, that polymer overcomes the drawbacks of this monomer in terms of higher removal efficiency of rennet at lower anion concentration of less than around 100 ppm, along with excellent radiation resistivity we have tested, I will show you, and reusability within a wide range of pH and which implies its potential towards practical application. So these are the different studies we have done, and this is that removal efficiency before and after irradiation of 1000 kg by gamma rays. So we have exposed our material with by gamma rays, and we have tested this. So radioactive element, so it works. So find there is no loss. So all these things. So now this polymeric thing can be used properly. So now I think I am within time. This summary. So I have shown this that steel wastewater removal using like a dicopper cryptate complex through cascade complexation and followed by cluster formation. I've shown like extraction of potassium fluoride, potassium chloride, even we have done potassium bromide also. And I've shown that carbon dioxide fixation using this cycle, and then again extraction of sulfate. And that again I have not explained, did not get time, so you can do recycling also. And finally I've shown that polymeric, this thing which can remove rennet, and it will work with a permanganate with high selectivity, radiation resistivity, pH stability, and recyclability. And I must thank all my students who have worked in this area. And actually, in the paper, I've mentioned that whoever they have worked. So some of the like Rajiv, he's working on rennet, permanganate, and here Vidyut and Saurabh worked on cyanide, and Rajiv also worked. Vidyut on that sulfate extraction and this. And I must thank these funding agencies, Swarna Jayanti Fellowship, SCRB, CSIR, Tata Steel, and ISS. And thank you all for your kind attention. Thank you.
So thank you, Professor Ghosh, for your very nice lecture. Especially, you know, I am really very happy to see the applications of your research, which is basic research, but the application side is also notable. You know, one should mention the application side. It's really very nice to see that part also.
Okay.
And I would like to also thank the Chemical Society for awarding this this year P-Day award to Professor Ghosh. I think he is now one of the leading scientists. So Chemical Society choose the very good scientist for the award of P-Day award of this year. So now we are already late, Professor Ghosh.
Yeah.
So I don't know whether we will have time to take one or two questions. So what about Professor Sinha? Should we take some questions, or you will have that questions after lunch?
No. In endowment award there will be no question.
Okay.
There will be no queries in endowment award, sir.
Okay. So thank you. So thank you, Professor Ghosh, again.
Both the Ghoshes, Professor Ashutosh for sharing this.
Thank you so much.
Professor Pradyut Ghosh for receiving this endowment award and we will hand over our mission to Professor Ghosh personally. And thank you, Professor Ghosh, for contributing your research in this podium. And now we will switch over to our next session, which is only a few minutes late. And this is being dedicated to the memory of Professor Asima Chatterjee and Professor Asima Chatterjee scientific session that is being conducted by Professor Kasturi Mukhopadhyay from Jawaharlal Nehru University, Professor Chanda Mukhopadhyay from Calcutta University, and Professor Bimlesh Locha from Srinagar University. Professor Chanda Mukhopadhyay, please you take over the charges of this program and we start this program quickly.
Thank you, Professor Chittaranjan Sinha, for your nice introduction. So we now start Professor Asima Chatterjee's special session. To all delegates, scientists, faculty members, chairpersons, awardees, research scholars, students, and friends, it gives me immense pleasure to welcome you all in Professor Asima Chatterjee's special session on behalf of myself, Professor Chanda Mukhopadhyay, University of Calcutta, Professor Kasturi Mukhopadhyay, Jawaharlal Nehru University, and Professor Bimlesh Locha, Shiv Nadar University. it is needless to say why this special session has been attributed to Professor Mrs. Ashima Chatterjee. She was also my teacher in the fag end of her career. What fascinated me was her methodology of teaching, slowly but steadily, all relevant points that were important for that particular lecture. I want to mention that the room where my research scholars work and I sit is just next to her sitting room in the first floor of Enashan Building, Rajabazar Science College. In this session, the chairperson is Professor Reena Ghosh of the Department of Chemistry, Jadavpur University, and there are 4 invited lectures. We shall start with the talk by Dr. Kali Prasanna Dhara, Calcutta University, who was also my teacher. Dr. Dhara will give a lifetime talk of Mrs. Ashima Chatterjee session, as he was both an MSc student and a PhD student of hers. This will be followed by the invited lecture by Professor Akhilesh Verma of University of Delhi. Invited lecture 2 will be delivered by Dr. Rakeshwar Bandichar, Vice President and Head of Chemistry, Dr. Professor Jyotirmoy Das of IACS Kolkata shall deliver invited lecture 3. One of our favorite teachers, Professor Mrs. Bani Talapatra, shall deliver invited lecture 4, and she is also the recipient of Ashima Chatterjee Memorial Award. I now request Professor Kosturi Mukhopadhyay to show a glimpse of the medal that will be awarded to Professor Mrs. Bani Talapatra. Kosturi, please.
Yeah, thank you, Professor Chanda. It is really great pleasure for me. Let me share the medal first. I think you can see the everyone can see the medal. It is indeed a great honor for me from the behalf of Indian Chemical Society to present Ashima Chatterjee Memorial Award medal to Professor Bani Talapatra to acknowledge her tremendous contribution and dedicated work in the field of natural products chemistry. She will be delivering lecture, as Professor Chanda already mentioned, and her contribution and achievement will be then elaborated by the chairperson, Professor Reena Ghosh. So I now like to request Professor Chanda just to give, give this platform to the Professor Reena Ghosh like that. Okay. So I'm just...
Thank you, Professor Kosturi Mukhopadhyay. Okay. So now it's my pleasant duty to introduce Professor Reena Ghosh of Jadavpur University. Dr. Reena Ghosh is affiliated to Jadavpur University, Kolkata as a professor of chemistry. She is actually my Reena Di, as I call her. She did her BSc and MSc from Jadavpur University. She got her PhD degree from the same university in 1986 under late Professor Amolendu Das. And this was followed by 2 years postdoctoral research with Professor Nirmalendu Rai at IACS Kolkata on synthetic carbohydrates. She then continued her research career as a CSIR pool officer at Jadavpur University. She joined as lecturer in chemistry at Bolpur College, West Bengal in 1992, and then in 1995 to Tripura University as a faculty of chemistry, from where she came back to Jadavpur University in Kolkata in 1998 to join as a faculty of chemistry. And she has contributed in several research areas of organic chemistry, like one-pot multi-component reactions, synthesis of heterocycles, studies on sugar-derived matters, etc. She was the recipient of Professor ASR Anjaneyulu 60th birthday commemoration award for the year 2018 by Indian Chemical Society during November 14 to 16, 2019. With these few words, I request Professor Reena Ghosh to chair this session, and Reena Di, you can start. Yeah, your microphone is muted. Your microphone is muted.
Okay, thank you. Yeah. So thank you, Professor Chanda, and also Professor Kosturi Mukhopadhyay. Whether the first lecture will be delivered by Professor Talapatra or by Professor Dhara?
No. Professor Dhara. Professor Dhara.
Okay.
Yes.
Okay. So
please follow the schedule. Please follow the schedule.
Okay.
Yeah.
Okay. Thank you. Okay. Thank you. So actually, I feel very happy and honored to chair this special session that is dedicated to Professor Ashima Chatterjee. And at the outset, I would like to pay my heartfelt respect to her. Although I was not a direct student of Professor Ashima Chatterjee, but like many others, throughout my academic career, she has been an inspiration to me. And I also would like to thank Professor Chanda Mukhopadhyay and Professor Kosturi Mukhopadhyay, the conveners of this symposium, along with the organizers, for giving me the opportunity to chair this special session. So the first lecture, as Professor Mukhopadhyay mentioned, the first lecture will be delivered by Professor Kaliprasanna Dhara, as customary. At first, let me say some few words about his brief bio sketch. Professor Dhara did his MSc and PhD from Calcutta University, and his special area of specialization was natural products chemistry, and his research interest was reaction methodology and mechanism in organic chemistry. He started his career in Department of Chemistry, Kolkata University in 1978 after his PhD, and then he moved to Calcutta University in 1982, and where he continued till his retirement till 2017. And in between, during 1987 to 1989, he went to USA for postdoctoral research in the Virginia Polytechnic Institute, and he altogether he guided 4 students. With these few words, I am requesting Professor Dhara to start his lecture. Professor Dhara, please. Professor Dhara, are you there? Hello?
Yeah, okay. I'm audible?
Yes, you are
Okay,
audible.
I'm sorry. Thank you, Professor Ghosh, for this kind introduction. At the outset, I would like to thank the organizers of this program, especially Indian Chemical Society and Professor Chanda Mukhopadhyay and Professor Kosturi Mukhopadhyay, for giving me an opportunity to talk about the lifetime work of Professor Ashima Chatterjee, who was my favorite teacher. Let me show the slides, please. Oh, I'm sorry. I'm sorry.
Good morning, Akhilesh. Good morning. Manidi, good morning. Good afternoon, Manidi.
Is it so? Is it all?
Yeah, it is,
seen
yeah,
by
it is
everyone?
coming. It is coming.
Yes,
it is coming.
visible.
Yeah.
Okay.
Yeah.
So,
Sir, can you please make it full screen?
I may have some problem for changing the slides. That's why I'm keeping it here. Is it visible?
Okay.
No problem.
Please,
It is visible. It is visible. Yeah, please proceed. Okay.
Now, I have obtained this photograph of Professor Ashima Chatterjee from the biographical memoirs of INSA fellows, and with the signature drawn there. On her birth centenary day, that is 23rd September 2017, Google changed their usual logo and put this doodle on their homepage, which shows Professor Chatterjee's face in center of hexagons and leaves to signify her breakthrough work with chemistry and plants. This way, Google honored this great lady. Family, Professor Chatterjee was the elder of 2 children of Dr. Indranarayan Mukherjee and Srimati Kamala Devi. Her younger brother, Professor Saraswaranjan Mukherjee, was a reputed physician and Bhatnagar awardee in medical science. She was married to Professor Borodananda Chatterjee, a renowned physical chemist and authority on soil science and corrosion. Her only child, Professor Julie Banerjee and son-in-law, Professor Rohit Banerjee, both are former heads of the chemistry department, Calcutta University. All her family were with her for her endeavor in her research in natural product chemistry, especially Professor Borodananda Chatterjee, her husband, was always inspired her to continue her research on this field. Professor Chatterjee used to speak about some persons, these 4 persons, from whom she got inspiration in her academic pursuit, and also she was influenced in her personal life. They are Acharya Prafulla Chandra Ray, Professor Linus Pauling, Professor Satyendranath Bose, and Swami Abhayananda, popularly known as Bharat Maharaja Ramakrishna Math and Mission. In fact, one could write separate chapters, discuss her association with these great personalities. Her academic career was always very brilliant, even from her school days. I've given only the MSc examination results. And she was awarded DSc in 1944, first lady DSc from any Indian university. And the title of the thesis I've given here, and the examiners were none other than Sir Alexander Todd, Professor R.D. Howard, and Professor George Clement. In her DSc thesis, she worked on Rauwolfia canescens, and she named the compound Rauwolfin and published it in 1941. Even at the same time, 3 different laboratories in Europe were working on the same compound with 3 different names. Professor Chatterjee was the first person to establish the structure of this Rauwolfin. It's a gross structure, of course, in 1954. The actual structure and stereochemistry was confirmed in 1959 in a JSCS paper entitled The Stereochemistry of Reserpine, Desirpidine, and Related Alkaloids. It was a contribution of 17 authors comprising 4 laboratories of Europe and USA. The second compound in her DSc thesis was a luvangatin, and that was published by Professor Chatterjee in 1940 with the co-authors Professor Ernest Speth and Professor Hans Schmidt. Incidentally, xanthiletin, which was known earlier to the 1940, was a demethoxylated derivative of this luvangatin, and it was also obtained from the same plant by Professor Chatterjee. Her professional career started as a teaching in Lady Brabourne College, and that continued till 1954 when she joined the Department of Chemistry, Calcutta University as reader. In between period 1944 to 54, she was honorary lecturer in the department, having laboratory facilities for continuing her research. She was promoted to Khoira Professor of Chemistry in 1962. She continued her association with the department as an honorary program coordinator, Center of Advanced Studies, and also as advisor till her death. She worked postdoctoral work with Professor L.M. Pars on iridoid glycoside from 1947 to 48, Professor L. Seckmeister on carotenoids and provitamin A between 1948 to 49, and then with Professor Paul Carrer on biologically active indole alkaloids 1949 to 1950. This subject became her lifelong interest. With Paul Carrer, she worked on corinanthine. She did detailed UV spectral analysis of this compound and published this paper in 1950. This compound was isolated by Paul Carrer in 1926, but the stereochemistry was confirmed by Professor Van Tamerlan in 1957. What I want to say here, that the elucidation of stereochemistries of natural products were achievable only around 1955 because the spectral instruments like IR, NMR, and mass spectrometer were available to organic chemists only on the first part of the 1950s. She had 350 research publications, including 1 for MSc thesis, and 11 for DSc thesis, and 6 publications for her postdoctoral work. She has guided 62 research students. Of them, 3 got DSc and 59 got their PhD. About 100 plant species were investigated in her laboratory, and more than 40 new compounds were characterized. Regarding the instrumental facilities, till 1970, only UV-based spectrometer and CH analyzer were available in the department. The teachers of the organic chemistry section had to work hard to obtain their spectral data from different laboratories in India and abroad. However, their hard work bore the fruit, and UGC sanctioned the Department of Special Assistance Program on Natural Product Chemistry in 1972 and thus a Beckman IR20 spectrometer and polarimeter were procured. In 1975, UNESCO UNDP assistance came to organic chemistry section, which helped to get CFT20 NMR spectrometer and an HPLC machine. The program was upgraded to Center of Advanced Studies on Natural Product in 1985, and from that fund, in 1986, the 300 mega Supercon NMR spectrometer were acquired during that time. In 1976, she procured funds from UGC to construct 3 floors on a ground floor building, which is just said by Professor Chanda Mukherjee, that's the Enersen building in Science College, to accommodate sophisticated instruments and space for research laboratories and expansion of departmental library. About her research topics, almost all types of natural product compounds have been worked in her laboratory. I've given all the names here, but the 3 main classes are alkaloids, terpenoids, and oxygen heterosides. Along with this work, they have studied the transformation reactions of some of the natural products and studied their mechanisms also. And later part of her career, she did some synthetic work on some synthesis of natural products. As because Professor Chatterjee was well known and internationally acclaimed for her research in indole alkaloids, I have restricted myself for discussing some of the important features of her work on indole alkaloids. And the first compound I need to discuss is strictamine. It was Trojanek obtained in this compound from Vinca minor in 1960. Professor Chatterjee obtained it from Regia stricta in 1966. Later, and in 1966, with Professor Klaus Biemann, she arrived at the structure and stereochemistry of the compound and published it in JOC. Ataur Rahman in 1977, doing the crystallographic analysis, established and confirmed this structure. Regine, incidentally, was isolated by Professor Chatterjee in 1961, and she derived the structure in 1962. However, Professor Henry in 1932 obtained a compound named, he named this as aquamidine from a Picrolima species. Professor M.M. Janot of France established the structure of the aquamidine in 1961. Silvers in 1962 procured both samples from 2 laboratories and did the crystal structures and found the identity of these 2 compounds. The copsin was an important compound isolated by Gressop in 1890 from a Copsia species. In Professor Chatterjee's laboratory in 1949, the compound was isolated from Copsia fruticosa. Spitaler and Chatterjee group worked hard. Also, Professor Battersby's group also worked hard, but they could not arrive at the correct structure. However, the correct structure was arrived by Professor T.R. Govindachari and Professor Hans Mead in a series of publications in Helvetica Chemica Acta, but with the structure and stereochemistry, which was later confirmed by crystal structure analysis. Now, the 4th compound is acetamine, which was obtained by Hesse, the well-known natural product chemist, in 1875. Professor Chatterjee isolated it from the Alstonea species, Alstonea solaris. Professor Chatterjee's group and Professor Bartsch groups worked on this sample, on this compound, but could not arrive this structure. If you look at this structure, generally it is the C ring is 5-membered, you see, and the D ring is 7-membered. This is very different from the other types of alkaloids. This actual structure and stereochemistry was determined only from the exoscopist analysis from Professor Hamilton in 1962. After the department has procured the instruments, she did structural elucidation of 2 important compounds. One is norelin, obtained from Alstonea solaris. She did all types of spectral studies, but the complexity of this structure could not be solved, and that can only be solved with the collaboration with Professor Hans Mead and from the crystallographic analysis. The paper was published in 1977, Helvetica Chemica Acta. From Raulfia reflexa, she isolated this dimeric indole alkaloid, flexicorin. Here also, if you see, one part of the compound has a 5-membered ring C and 7-membered ring D. Now the structure of this compound was established from detailed C13 NMR analysis and in collaboration with Professor Hagemann in 1982 GOC paper, it was confirmed and published. She was like any natural product chemist. Professor Chatterjee was also interested for biosynthesis of natural products. And I have taken the two examples from her work. One is diisokizine. This compound was known to be the intermediate of biosynthetic pathway of indole alkaloids. Battersby isolated the compound from Vinca Rose in 1969, and Professor Chatterjee isolated this compound from Regia stricta in 1970. So isolation of this compound from two different plants confirmed the biosynthetic intermediacy of the, and from this compound, indole alkaloids of various structural features could be arrived at. For a pentacyclic triterpene, the biosynthesis starts from squalene epoxide, and there was a missing link to have a double bond between 9 and 11. And Professor Chatterjee's group isolated valsurenol from Valsura tabulata, and it had 9-11 double bond, and this structure was established by the Professor Chatterjee's group only in 1968 and published in Chemical Communications. She did transformation reaction, as I've just mentioned. Here I'm given a very simple transformation reactions, hydramine fission. She published this in 1961 JCS. And it is a simple reaction. The ephedrine has been the nitrogen CN bond cleavage in presence of concentrated hydrochloric acid to propionophenol and methylamine. Since this mechanism is so simple that it was incorporated in the textbook literature by I.L. Finner in Organic Chemistry, Volume 2. She did the transformation reactions with the taraxaryl derivative. And in both the cases, when I've given the references, in both the cases, she obtained beta-amylene acetate. The question was that if the BF3 iterate or the epoxy here are alpha oriented, then the methyl group at C13 position will migrate in the same phase with the leaving group. Now, the elucidation of the structure was there is no problem, but the mechanism is really a questionable. That how this possible. This was explained by Professor E.J. Corey in her work on the energies of triterpene cations with the Hardy-Fruck method calculation, and she showed that oleonyl cation with the carbocation cation at C13 position is the most stable among all the triterpene cations. That means that the stability of the oleonyl cation drives the movement of C13 methyl alpha-oriented methyl group to in the same phase of the leaving group, and that was the case in Professor Chatterjee's work. She did the synthetic work, and she synthesized isochromanone as a intermediate for all types of synthetic work she did, and from this compound, diazoketone. She did lot of very different structure of isochromanone and utilized one of them with this amine to obtain the simple isoquinosyl alkaloids. She did number of isoquinosyl alkaloids. I have given only the two references. And finally, she also did the synthesis of Rawelsin by reacting with tryptamine and isochromanone, this isochromanone, and through a series of reactions which I am not going to detail. And she published this paper in completing the synthesis. She published in Pure and Applied Chemistry in 1986. But still more to come from her. Since she is very much interested in Indian medicinal plants, she did Ayurvedic preparation for treatment of epilepsy, which is coded at IUS 56, and for anti-malarial IUS 64, and both were patented. Not only that, she built the Central Research Institute Ayurveda with hospital facility. That was her dream project, with a donation from 3 acres of land in Salt Lake from then Chief Minister Mr. Jyoti Basu, and a grant of ₹4 crores from the government of India. She did also editorial work, publishing 2 books, Bharater Banaushadhi in volumes 6 volumes, and from Calcutta University publisher, and the treatise on Indian medicinal plants 6 volumes. Publisher was CSR, New Delhi. Definitely, awards and recognitions came to her. And the list is endless. I have selected a few. Fellow FNA in 1960, Bhatnagar Award in 1961, P.C. Rai Award in 1974, First Lady General President of Indian Science Congress 1975, Sir C.V. Raman Award by the University Grants Commission in 1982, Eminent Teacher Award by the University of Calcutta 1997, and so on. She believed in social commitments. She was the architect for a win of Bengal Chemical in the legal battle against Hex Pharmaceuticals in 1968 and not accepting any remuneration. She was also involved in popularization of science through Bengali language and was associated with Bangio Vigyan Parishad. In recognition of her contributions in phytomedicine research and in public life, she was awarded civilian honor Padma Bhushan and nominated as member of Rajya Sabha. With students, students were always her priorities, even during busiest moments. Whenever any students approached her for any academic discussion, she set aside all work and get into the conversation. She always encouraged students for oral presentations of their own research works in seminars and symposia. Her students reverentially called her master. She was both teacher and preceptor to them. I pay my homage to Professor Chatterjee for showing this commemorative stamp, which was released by Indian Post to honor Professor Chatterjee in our 5th death anniversary in 2011 at the behest of Indian Council of Medical Research. With this, I conclude my talk and thanks once again for the Indian Chemical Society for giving me the opportunity this opportunity to talk about Professor Chatterjee's lifetime work. At the end of my talk, I have given the list of the research students, which I'm not going to discuss, and thank you very much.
So thank you, Professor Dhada, for your nice and informative talk on Professor Ashima Chatterjee, who made tremendous contribution for the advancement of natural product chemistry, and it shows and why the entire talk, from the entire talk, it is once again evident why people like us get so inspiration from hard life, from hard academic achievements. Okay, thank you again, Professor Dhada. Now the next talk is an invited talk and will be delivered by Professor Akhilesh Pharma. He is a professor of Department of Chemistry, University of Delhi. He will be talking on copper catalyzed synthesis of indoloisoquinolines via intramolecular hydroamination, mechanistic insights using online MS. Now, before I invite him to deliver his lecture, a brief introduction about him. Professor Pharma did his PhD from University of Delhi in 2000, in the year 2000, and then after 2 postdoctoral research experience, first under Professor Kartiski from University of Florida, USA, and the second one with Professor Laddock in the University of Iowa State University. I think then he joined University of Delhi, most probably. Anyway, his research area includes super-base promoted catalytic organic transformations or transition metal catalyzed organic transformation, application of mass spectrometry and medicinal chemistry. He has more than 23 years of teaching experience and more than 21 years of research experience. So far, he has guided 32 PhD students, and he has many honors and awards Since 2007 to 2021, he has got several of those, which include UGC Mid-Career Award, member governing body, CRUM, Ministry of Ayush, expert member. He was an expert member of Chemical Science PMRF, expert member of CRB PAC committee, senior fellow Institute of Eminence IOE, University of Delhi, elected fellow Royal Society of Chemistry FRSC, and he got bronze medal of CRSI in 2021, and he is an FNA and INSA awardee, and he has published 132 papers and in several reputed journals or international journals, some of which are UChem, Council of Chemical Research, Organic Letter, ChemCom, JOC, and others. And with these few words, I am inviting Professor Verma to start his lecture.
Thank you, Professor Ghosh, for your very kind introduction. And it's my privilege and it's my honor to give a talk in a session of a legend of this country and who has significantly contributed in the field of natural product, Professor Ashima Chatterjee. And in the beginning, I would like to thank organizers, Professor Kasturi, Professor Chanda, Professor Bimlesh, and all the Indian Chemical Society committee members. And I was associated with this Indian Society since a long time. And I was scientist in charge for 3 years, so I can understand. And I can see how this Indian Chemical Society has improved in the last few years. And it is good sign for all of us, like the Indian Chemical Society has revived again, and I am sure this ICS will get height in the coming near future time. So let me share my window. Are you able to see it?
Not yet. Yes, now it is coming. Yes, it is visible now.
So is it now?
Yes, it is visible.
Okay. So today what I'm going to share something, a different chemistry, which is some advancement in the field of mechanistic investigations. So what we are going to share here along with this some synthetic chemistry, like how we can use this mass spectrometry in characterizing the intermediate reaction intermediate, so that we can prove it which is the right path for the proposed reaction. So this is you can see here. Is my slide is moving?
Yes, it is moving.
Okay. So this is the word. Preposterist is an honor. Is always used for honor of the people who have made a significant contribution in their field. So it's really an honor to speak in the session of Professor Ashima Chatterjee. And beside this, I would like to show some other two ligands. You can see Professor S.S. Bhatnagar and Professor T.R. Seshadri, who have significantly contributed in the field of science, especially in the chemistry. Professor Bhatnagar was here in this department from 1941 to 43, and Professor T.R. Seshadri, he was here from 1949 to 65. And I think all we know these two ligands because of their significant contribution in the field of chemistry, especially organic chemistry. So first, let me introduce like some of research activity, what we are doing in our lab and how we have come up to this stage so that we have developed this hydroemission chemistry. And this is the work you can see here. We have started in 2009. From there, this hydroemission chemistry have developed. So this is the one area where we are working actively since 2009 onwards. And then we have summarized this work in 2017 in accounts of chemical research. The another area where we are actively working is a cascade chemistry. You can see one bullet more than 100 target. So this is the another area where we have done a lot of, we have developed several synthetic methods for the synthesis of useful small molecules. And then you can see we have developed a triple successive oxidative Higgs chemistry starting from indole to carbazole that can be constructed directly starting with the indole. And then we have also contributed in the 3+2 annulation of internal alkynes and use that chemistry for making like a fuse kind of compounds with the 2 carbonyl groups, and that can be further used for making another fuse carbazole pyrrole compound. And then if you look the work of my laboratory, we have made a significant contribution using KOH and DMSO. It's a very simple, useful, and sustainable chemistry. And so this, you can see the first one is a metal and protection free 4+2 cycloaddition of alkynes. Then we have used that chemistry KOH DMSO for making a substituted pyrroles, and then we have extended for the construction of a natural product. Then further base promoted, we have synthesized the isoquinolines and then aminoindinones. So this is all the chemistry you can see. What we have used is simply KOH and DMSO. So that is one of the major work we are doing in our lab. And then this orthoalkyne and aldehyde we have extended with alkyne with orthophase at a cyno group, and then variety of the heterocycle with the amino group we have constructed. And this is the beauty of this work is one can directly introduce the amino group along with all other functionality. Then we have changed alkyne with the alkene, and we have done like base mediated anti-Markovnikov hydroamination with vinyl arene and arylamide. And this is a very recent work where we have shown like a anomalous Deakin kind of reactions where like alkynyl aldehyde we have changed into some useful furoquinolines. And then another one you can see a transition metal free construction from using orthoformyl ketones. Then we have developed this chemistry for variety of compounds. And then again, the base mediated chemistry, KOH DMSO, or we can use potassium tertiary oxide for the direct synthesis of 4 aminoquinolines from vinones. And another chemistry which you can see the sustainable is carbonyl assisted regioselective hydration of alkynes. So this slide shows like we have done some work in the field of base mediated super base KOH and DMSO and with the alkyne, and we have used this method for making a variety of useful molecules. And this is a recent work which we have started in 2009 using a direct online mass spectrometry, and that I will show you later on. And some other recent chemistry which you can see here, one can directly change this this aldehyde into amine using NFSI and the condition which we have developed. And another one, and the end you can see here at the last is a chemoselective oxidative esterification of aldehyde. Actually, this is the chemistry is a very, very useful and simple chemistry which we have introduced in the master spectacle. And this is the chemistry which we have developed, and this practicals can be done for the graduate level, undergraduate level, because what one can need only any aldehyde, iodine, and potassium carbonate and alcohol, which is easily available in each and every lab benchtop chemicals. So this is a practically useful chemistry which we have developed. And very recently, we are using PCDA, polydiasterenes, substituted polydiasterene for a medical application. This is some work is still going on, and some part of that we are about to patent. And now coming to the today's work, what I am going to discuss is a study of reaction intermediate through online mass spectrometry. And this is what we have started in 2018, and then 2019 we have published one paper in ChemCom where we have shown the proof of two reductive elimination pathways for the reaction in direct elimination using this directing groups. So what there we have shown copper 3 to copper 1 and copper 2 to copper 0 that we have detected through online mass spectrometry. So now this is the work which we have published in 2009. The background of this work is 2009, where you can see R1 and R3. These were the two limitations on the developed chemistry. And the chemistry was through intermolecular hydroamination and followed by intramolecular C2 annihilation. So because of these two limitations, we thought, can we have a different and simple chemistry by which we can overcome these two limitations. So this is a well-known and well-understood chemistry. Like if you have a tosyl hydrozones with the copper carbines can be easily generated. So based on this, what we have designed the chemistry, you can look here. So what we thought, if we take amino tosyl hydrozones and when we react with this ortho-alkynyl aldehyde using copper iodide, so indolo isoquinolines with a wide variation can be developed. So this is what is the pathway which we have in the beginning. We thought, like, first it will generate the copper carbinoid, and this copper carbinoid in C2 will form an indole intermediate with the alkyne at the aryl ring, and then subsequently this NH free indole will attack on alkyne which is activated by the copper, and this is how we can generate this kind of fuse construction, fuse molecules like indoloquinolines, which are also a core nucleus of cryptocholine natural product. So, and after this, we have standardized the reaction condition. We have done several experiment, and the copper 10 mole percent DMSO 110 degree and 30 minutes we got the product. And this we have further confirmed by the single crystal X-ray. So actually for standardizing this condition, we have more than 50 reactions we have performed, and then we come to this standardized condition, 10 moles of copper iodide, DMSO 110 degrees centigrade and 30 minutes. And more interestingly, one very interesting result we have found in between, when the reaction was conducted without copper, no copper, DMSO 110 degrees centigrade, and when we run the reaction for 5 hours, we did not observe any indolo 2,1 quinolines. Rather than very interesting compound, the aminopyrazoles was obtained. This was further confirmed by the single crystal. So this is a very beautiful chemistry has come out during this, but this I will discuss later, because first I'll describe this thing. To confirm the mechanism how this reaction is going, we thought first we perform the reaction with this isolated alkyne aminopyrazole. We thought maybe this could be a one intermediate, but with this we did not get the desired product. And then we have prepared the indolo alkyne, indolo 2-aryl alkyne, and which we have proposed as a reaction intermediate. And when we perform this reaction using a standard reaction condition, the indolo alkyne was converted into desired product. So the second reaction supports like reaction is going through in situ formation of this indole intermediate. And when we perform the reaction with amino hydrazones and with aldehyde having no alkynes. So interestingly, we did not observe the desired product. Even though we did not get this is the indole which we were thinking the intermediate that should be formed without alkyne. But we were failed to get this alkyne, so that made the question like how the reaction is going. So then we propose first reaction pathway, you can see here. But we thought maybe in presence in this tosyl hydrazones, the copper forms the copper carbene and then indole, and then it in situ hydroamination, it forming this through intramolecular hydroamination is giving giving this NC bond and forming the desired product. Then in between we came across some one paper in ACS catalysis where they have shown they have used this tosyl hydrazones, and so based on that we propose might be this tosyl hydrazone, the in presence of copper and this high temperature DMSO is forming a diazo intermediate. This diazo intermediate was reported in this ACS catalysis paper. So based on that, we propose this mechanism, like after diazo intermediate, this amine and aldehyde is forming this imine, and then the intramolecular this attack on iminium carbon, and then with the extrusion of the nitrogen, the indole intermediate is generated, and already copper is present in the system, so we'll activate the alkyne, then intramolecular hydroamination of indole with alkyne will give this. So this is what we have proposed based on one paper that we look in ACS catalysis. Then it's very interesting when we perform the reaction with simply with the phenyl in absence of like a tosyl group. So we were thinking, let's see whether what happens when we use this simply with the hydrazone. There is no tosyl group in that, because in that and other reports it were reported only with the tosyl. So we thought, let's see what happens when we use this. It's very interesting. Without tosyl also, we got the compound in 75% yield. Then we thought how it is possible, because tosyl was required for as a leaving, so that we can get the diazo intermediate. Then we perform the experiment. One experiment now you can see here, and this is called online mass spectrometry, and this is the first experiment we have performed, and this is you can see we have set up the reaction just near to the mass and connected with the fine capillaries with the mass instrument, and we have used 5 psi pressure using with the nitrogen cylinder, and through this this LC we have removed, and directly in the screen you can see each and every second what is happening in the reaction that can be monitored through this online mass spectrometry experiment. So here you can see here is the mixing. This is called a pressure pump, where we have methanol in that mixes along with this at the T junction, and through T junction it goes inside. So when we perform this experiment, then we have a some very interesting results. Now you can see here each and every in the beginning what we got, a DMSO with the Na, DMSO with the H, DMSO, and now you can see what we got here with all intermediate we observed in online mass spectrometry along with time, at what time which intermediate is formed. So both we could see here. Now you will see in that next one. So this was observed. Now you can see here within less than 2 minutes, immediately we got this starting substrate that with the mass of this, and then this B, this is compound B, that is orthoalkynyl aldehyde, that was also in the reaction mixture. So that was also detected immediately. You can see, because reaction was started at 110 degree. We have maintained the temperature, and then after, you can see here, after some time, this after 1 and 2 minutes, what we could observe is I2 and I3. So I2, see how fast this reaction is started. Immediately there is a formation of imine, and the imine is coordinated with the copper, nitrogen, and alkyne. So this is why this alkyne was required, right? Without that, we did not observe this one. So now you can see after that what happens is, after that, next one is this attack of intramolecular, the carbon bond formation, which lead to the formation of this I3. So that was also detected, I2 and I3, after some time. So both are isomeric, but there is a difference in the time. First you can see one intermediate, and after some time you will see the intermediate 3. So this is the beauty of this this chemistry. Like sometime when you have a same molecular mass, then it is very difficult, but with a different time we can say this is the intermediate, and this is this intermediate, this is this intermediate. And then after some time, what happens, intermediate this I4 was detected, and that is with the different in the time, I4, and then after cyclization, intramolecular cyclization, I5 was observed. You can see here I5 and I4 both are at different time, and then we observe the product. And the most interestingly, what we could observe is the phenyl diazine, because now if you see this one,
Professor Verma.
Yeah.
Professor Verma.
Yes, maybe
Time
2
is
to 3
already-
more minutes.
Yeah.
So now you can see here what we have shown here from I3, there is a removal of phenyl diazine. So phenyl diazine was detected, and that was the confirming, like the reaction goes through what we have proposed now in this way, the third pathway. So third pathway is proposed based on this, what we have got through this online mass spectrometry is first formation of imine, then coordination with the copper, and then intramolecular this carbon-carbon bond formation, which lead to the formation of this dihydroindole, and then that gives with the removal of phenyl diazine, that gives the indole, and immediately that indole is alkyne is coordinated by this copper, and then intramolecular hydroamination, and then there is the formation of intermediate 5, and then after proper workup, it gives the final product. The most importantly, none of these intermediate which we were thinking in the beginning, copper and the diazo, and this was detected. And then we extended the chemistry for making a wide variety of this compound. So it's a very simple, robust, all variety, all the sites variation can be done. So that limitation has overcome. Now you can see here the methyl, ethyl, cyclopropyl, all phenyl, CD3 can be substituted at the indole at C3 position, and all such kind of molecules can be done. And finally, I would like, I have to thank my students who really work hard. So now you can see these are the 3 students Tripti, who got selected for 64th Lindo Nobel laureate meet in Germany. And the Monica, then after 3 years, she was selected for Lindo Nobel laureate meet. These two have worked for hydroammunition chemistry. And the Rakesh was involved in the base mediated chemistry. And he did postdoc with Claydon and also got a Marie Curie fellowship. And then he moved to recently, he's moved to US. And now other people who are contributor on some other work. And you can see here continuously 2020, 2019, 18, 17, the NOS Best Thesis Award. And finally, I would like to thank Indian Chemical Society for inviting me to share some of my chemistry, and Department of Chemistry who provided me the space. And without funding, it is not possible to do any work. SCRB, DST, UGC, DRDO, and CSIR for their generous funding. And thanks for all for your patience and listening my lecture. I'll be happy if you have any questions. I'm happy to answer.
Thank you, Professor Verma, for your excellent illuminating talk. Since time is already exhausted, I can take only one question from the audience. Only one question. Okay. Since there is no question, I will move to the next lecture. The third lecture is also an invited lecture. It will be delivered by Dr. Rakesh Bandichar, who is Vice President and Head of Chemistry, API, PR&D, Dr. Reddy's Lab. He will be delivering his lecture on chemistry at Epicenter in pharmaceutical industry. Now, a brief bio-sketch of Professor Bandichar. He did his MSc, PhD from not only MSc and MSc Tech from University of Lucknow, and then he did his PhD degree from CDRI Lucknow with three professors, Professor Rastogi, Professor Tandon, and Professor Oliver, from where he moved to do his postdoctoral work to Germany, University of Rosenberg, and then after other two postdocs in USA, he started his professional career at Reddy's Lab, where he is now as head and vice president in the R&D section, API. His research interest includes asymmetric synthesis, heterocyclic chemistry, synthesis of complex molecules, green chemistry, new methodologies involving organometallic, organocatalytic and biocatalytic approaches, process chemistry involving AI, PAT, and flow technology for API synthesis. So far, he has got several honors and awards, among which a few I am mentioning: Chairman Excellent Award in 2012, 2010, ISCB Award, then Green Innovation Award, CRSI Bronze Medal Award, STE Green Excellence Award. And so far he has made more than 160 publications and more than 25 patents. With these few words, I am requesting Professor Bandichar to start his lecture.
So thank you, Chairman, for kind introduction. So I feel honored and privileged to give an invited talk and Professor Ashima Chatterjee's session. And thank you so much for the session administrators. So with this brief comments, I would like to present my talk. And the title of the talk is Chemistry at Epicenter in Pharmaceutical Industry. So I just compared, if there is a word epicenter, it means there is some problem associated with it, right? Epicenter is being used when there is an earthquake. So I compare the problem that we face in pharmaceutical industry as an earthquake. So, but when you move down into the kind of a problem analysis, what you find out that every problem is associated with, chemistry at molecular level. So can you see my presentation?
Yes.
Press to be in a
We
presentation
can
mode.
see.
Yeah, just hold on. Where is it? I have to share it once again. Is it fine now?
No, not yet. It is coming.
Okay,
Okay. We can see it.
great. So, to start with, I think we had a privilege to host this year's Nobel laureate, Professor Benjamin List, who shared the Nobel Prize with Professor David Macmillan, and we had previous Nobel laureate Professor Nigisi. I think he passed away early this year, and we had a couple of other legendary figures in organic chemistry, and we had a very great conference in Dr. Reddy's. And today's discussion point, we will discuss about chemistry in pharmaceutical industry, and then significance of chemistry in different elite areas, for example, medicine, artificial intelligence, process development, green process, analytical R&D, process engineering, case studies, and we also talk about how chemistry helps to address the deficiencies that we face from regulatory agencies, and then what would be the future of chemistry in pharma industry. So chemistry is everywhere, be it intellectual property, safety, green chemistry, analytical formulation, engineering. So it connects the dot of the pharmaceutical activities with each and every branch of sciences that we make use of. So as I mentioned, if you look at the earthquake, right, there's impact. So when there is a problem, we get to know in pharma industry, we start digging down what is the root cause. So eventually we find out that the chemistry at molecular level is causing the problem and creating an impact. If you are, what does it mean? If you are not good at chemistry and working in pharma industry, you won't be able to solve the critical problems. So hence the title has come up in my mind, and we are discussing today. In chemistry in pharmaceutical industry has a critical role to play in health and well-being, in environmental sustainability and resilience, and then it also offers avenues to employ different futuristic technologies. And there are three key pillars where chemistry plays a role: synthesis and medicinal chemistry. That is where chemistry has subtle interplay factors, and also chemistry helps to have supramolecular soft smart materials, and catalysis and mechanistic physical organic chemistry, all kind of things also play critical role. Previous speaker, Professor Achilles, has beautifully presented mechanistic understanding of the reaction. He came up with the third mechanistic understanding, which has added value to his work. So the chemistry is everywhere, and you can see here a lot of things are written: asymmetric synthesis, organometallic, organocatalysis, and everything is boiling down today to automation, robotics, and flow technology, and artificial intelligence and machine learning that we'll talk about in a couple of slides from now. Is these two things are giving organic chemist an edge to devise shortest route of a molecule that you intend to make. So complex chemistry and complex assets. If you look at the first structure, it has 19 chiral centers. Now you can imagine how many diastereomeric impurities you can think of. The Dr. Reddy is the only company that has completed entire synthesis, and we filed drug master file in US, which is the toughest thing that any company, either it is innovator or generic company, can think of. So we have successfully accomplished this, and this is the trademark of Dr. Reddy's innovation and the skill set that we have. So this is for the audience. This is very general slide, but when you buy a medicine, what is there in the medicine, which is active component? which is nothing but active pharmaceutical ingredient. Along with that, you have got set of excipients. And what is that active pharmaceutical ingredient? It is nothing but a decorated, designed organic molecule, which is well studied by the innovator. What generic company does, once the patent gets expired, they start looking at the synthetic landscape and come up with the more smarter synthetic route, more shorter synthetic route, and increase the process efficiency in such a way that we can make exactly same molecule without compromising on quality and other factors that is inbuilt in the medicine, and start putting same drug product in the market. So if you have a choice to buy a generic medicine, do not hesitate, because we as a generic company, we never compromise with the quality it is given. And if you look at the entire efforts that innovator company has put in, it's humongous. We do most of the activities that innovator does, but the most arduous activity that innovator does, we don't do, but we buy the studies that they have already conducted and create a bioequivalence and have a generic version of medicine being marketed and used by the end user. So see, there is a revolution in organic synthesis today. Everybody, at least in top-notch academics and industries, everybody is moving from classical synthesis to fully automated robotic lab-driven synthesis. You can do route selection by using AI and AI/ML approaches. You can do process development based on a specified module, and you can do reaction manipulation by using robots, right? And this is being this entire assembly has been developed by MIT professor. There is a group in MIT. They have developed this, and it is successfully demonstrated, and it is quite handy. And we'll talk about a kind of a cassette, which is nothing but a module for a specific reaction that has also been developed. Look at this, is almost like a video cassette player. Each and every cassette is loaded with a specific reagents and all the attributes that helps you to get the reaction done. And you can just put that and add the substrate, your reaction gets over and product comes out from the end. So you can design a number of these modules depending on what kind of reactions you want to do. But this is the level of sophistication and advancement that are being accomplished in academic lab as well as in industry, and we are poised to adopt such kind of advancement, and we are heading towards that so that we become sophisticated and take up the complex synthesis. So there is another thing that we have adopted, which is based on the AI/ML data analytics, and we are doing route selection by using such kind of a software, which is based on AI/ML, and this is called Cynthia, being marketed by the Merck Millipore. It helps us to reduce the timeline, and it provides you the comprehensive coverage of different ideas. And we can get more by putting less efforts, and we can reduce the raw material cost, and the scope is such that you can have non-infringing synthetic routes and have your IP on the synthetic route. So we are using it day in and out and coming up with the more smarter synthesis that anybody can have. It does not mean that if you have this software, you can have, best synthetic route in the world. You have to couple with the natural intelligence and pick the best out of the recommended ones by this tool, and then do kind of a literature search whether something is known along that line. And if somebody has done similar kind of things in open source or in publication or in patent, and then design the synthetic route based on the recommendation provided by this tool. So what we found out, it works pretty well, and we can shorten the time for selecting the best synthetic route having lowest raw material cost. So this is very important slide. If you look at the chronology from 2009 to 2019, there is a one factor at a time optimization people used to do when they make small molecules, and then we start getting into the understanding of polymorph complexity. Then we do design of experiment, and there are automated reactors, and we start handling complex chemistry in industry, and we started working on peptides, iron nanoparticles, and we understand what is the process safety, process analytical tools, macrocyclic molecules, semi-synthetics, and we have parallel synthesizers, high throughput screening, and complex oncology molecules, separation science, and electronic lab notebook, and we have advanced characterizations and co-crystals, and start introducing engineering optimization of unit operations, modeling, and we know how to make oligonucleotides. And now 2 years back, we ramped up our efforts to do manufacturing by using continuous technology. By using such tools and technologies, we reduce the failure rate by 7%. What would be the next 2019 beyond? We are getting into predictive sciences, 3D printing, and sustainable R&D and manufacturing in absolute sense, microwave assisted synthesis, electrolysis, photocatalysis, continuous technology based approaches. Trust me, coming era is going to be of artificial intelligence based approaches, and it is pretty much there to help organic chemists to make new molecules or newer way of making new molecules. Coming to the chemistry in process development. So this process development is an art which cannot be de-linked with chemistry. Look at this synthesis, which is of Januvia sitagliptin. It is blockbuster molecule to manage the diabetes. Look at in the bottom side, there is a imine synthesis followed by asymmetric hydrogenation by using organometallic approach. And a set of process chemists in the same company has come up with the biocatalytic route, and where catalyst loading is minimal, and you get enantiomer selectivity in the tune of 99.9%. Because if you, in such transformations, if you have only enantiomers to deal with, the purification becomes challenging, because you have to deal with the racemate. 90% enantiomeric excess means you have to purify this material without losing too much of a right isomer, enantiomer. You have to sacrifice around 6% of the racemate. And if you have to do this, then you have to compromise significantly on the cost, because you are letting 6% of your final product go into waste. So green chemistry comes in the picture. Green chemistry is a very serious science. It is not a huckwash or kind of baked down. For example, a group of scientists, when they put experiment, what is their expectation? I should use minimum amount of reactants, reagents, solvents, and get the maximum product out, right? That is what the green chemistry is, because your process mass intensity is going to be high, atom economy is going to be high, and do the reaction in safer solvent, use catalyst instead of reagents, and switch from stoichiometric version of reactions to catalysis, right? And try using renewable raw materials. This is all about green chemistry, which is nothing but a excellent way of doing organic chemistry if you are dealing with organic molecules, right? So how to define green chemistry, how to quantify, there should be a metric, right? So we have implemented reaction mass efficiency, process mass intensity, atom efficiency, and how much effluent we are generating, how much hazardous waste we are generating, and we are putting metric and classifying by giving some grades and trying to control the waste material, thereby increasing the process efficiency to get more material and reduce the raw material cost. That is how we make generic products and make medicines cheaper for the people in the society, by kind of practicing chemistry at a molecular level. To compare with, there's one API that we have done in batch and in continuous, and we have seen substantial advantage in terms of reaction mass efficiency. We have process mass intensity reduced from 146 to 67 kg per unit kg of the product. Atom efficiency is also increased. Effluent water is also decreased from 112 to 53 liters. So that's how, if you want to do serious green chemistry, is challenging, and we do it now. So chemistry plays important role in analytical sciences. To me, they're like a cousin brothers, right? So it plays role from material receipt to final product, because everything has to be analyzed. Everything you need to know what you are making, how you are making, what is intermediate, and what is the mechanistic profile that reaction is being operated. A lot of things are there, and there is a specific analytical techniques at each and every stage that you have to employ. For example, Raman, and then you have to have calorimetry, polarimetry, NMR, chromatography, and then the FERM, and then you have got mass spectroscopy, and similar kind of tools like near IR, Raman, and mid IR we have to use to kind of analyze finished product and other materials at different stages. Process engineering. Do you know today there is a unit which has been developed in collaboration with Novartis and MIT? You just put the raw material and get the formulated product out. And this has been demonstrated in one of the medicines called Aliskiren. This is pretty much highlighted in CNE News long back, and now people are trying similar modules just to have a kind of a instrument ready, put the raw material, get the final product out. Long way to go to have similar setup at commercial production, but at least there is something which is already there, which can be further improvised. So coming up with some of the case studies, our group has reported first enantiomer selective Grignard addition to nitroolefins, and this is the catalytic cycle. So our aim is to make enantiomer selective synthesis of naproxen. However, we made significant progress, but the enantiomeric ratio for naproxen was not that great. But what we found out, the tertiary butyl version of naproxen has excellent enantiomeric ratio, and since the selectivity was not that great, however, we published and patented, we started looking at how we can make enantiomer selective,
Professor Bamdecha, 2 minutes left.
Okay, ma'am, I'll finish it up. So we made the substrate, and we started looking at different enzymes, and we found enzyme which does excellent transformation, and we got 99 plus enantiomer selectivity, and yield is also near quantitative. That's excellent piece of work that we have done, and it's a synthetic evolution right from chemocatalysis to biocatalysis. And there is a lot of chemistry involved in nitrosamine impurities, which is genotoxic, recently found in all the sartans. But at the very basic fundamental, we need to understand chemistry, and based on the chemistry understanding, we can avoid the formation of these nitrosamines and make your sartan products safer or these safe for the consumption by the patients. And if you don't control, it produces a carbocation, which is a DNA alkylating agent and leading to mutation and eventually cancer. So what is the future perspective? Last 50 years we did leverage existing synthetic methods. Today what we do, biocatalysis, editing, bioconjugations, high throughput screening, directed evolution. What next 50 years we are going to do? Molecular editing in machine learning. So by sincere advice to all the synthetic organic chemistry professors, scientists, everyone, start switching as the time is moving and start looking at machine learning, artificial intelligence, and molecular editing. And I tell you, the potential of chemical industry today, it implies close to 800,000 people across the world, and it is significant percentage of the any country's economy. So pharmaceutical industry is very attractive if you are serious about understanding science and contributing to the medicines and make a difference. Thank you so much for hearing my talk. This is what I wanted to communicate to you.
Thank you, Professor Bandichur, for your illuminating lecture, particularly for giving us an overall idea about the chemistry going on in industry, along with some future direction also. And I can take only one question from the audience, since time is not much. Okay, since there is no question,
there is
then,
a question, Professor Rina, there is a question from Manosi Das.
Oh, okay. Okay. Hello?
Yes.
Someone is asking some question, I think.
Please go ahead.
Who is asking some question? Who raised?
Manosi Das, please unmute yourself and ask your question.
Can you hear me?
Yes.
This is Anju Chadda from IIT Jammu. Dr. Rakeshwar, I just want to know if there is an environmental index when you talk of green chemistry, impact on the environment. How green is green?
Right. So there is a process mass intensity which is nothing but a E factor, right? So without water, process mass intensity is E factor, right? So E factor is being defined in order to make 1 kg of required material. How many kgs of waste that you are generating? It is being quantified, and we are putting in our sustainability report, and that becomes like a rider how bad we are and how much we should improve.
But that is only generating data on the waste produced. What is the impact on the environment would mean life cycle analysis and stuff like that.
So we are not there at life cycle management, but one thing we do, we ensure that we have a zero liquid discharge. We don't allow anything hazardous, anything which is not healthy to the atmosphere going to the water stream.
Thank you.
Okay, thank you, Professor Bandichur, for your nice lecture. And now the next lecture will be delivered by, it is also an invited lecture. It will be delivered by Professor Jyotirmoy Das, who will be talking on construction of nitrogen containing heterocycles by olefin metathesis. Now, before starting his lecture, a brief bio sketch about her. Dr. Jyotirmoy Das has obtained her PhD degree in organic synthesis from IIT Kanpur under the supervision of Professor F.A. Khan. She then continued her postdoctoral research first at Freie University Berlin as an Humboldt Fellow under Professor Reisig, and then at ESPCI Paris with Professor Cozy, which was followed by her postdoctoral research with Professor Shankar Balasubramaniam at University of Cambridge with a Marie Curie Fellowship. She then joined as assistant professor at the IISER, Calcutta, and she is currently working as a senior professor at Indian Association for the Cultivation of Science. She has made significant contributions in the structure and function of nucleic acids. Her research interests include new organic transformations, self-assembly of nucleobases, and the design and construction of biomolecular devices and artificial ion channels. She has supervised more than 15 PhD scholars and published more than 100 publications in reputed journals of high, she has a high H index 35. Professor Das has a recipient of DST Shaunajanti Fellowship, DBT Wellcome Trust IA Fellowship, CRSI Bronze Medal, and Shanti Swarup Bhatnagar Prize. She has been an editorial advisory board member of ACS Omega Asian Journal of Organic Chemistry and Chemical Communications during 2020 and 2021. With these few words, I am inviting Professor Das to start her lecture. Professor Das, please.
Yeah. Good afternoon to all of you. And I'd also like to thank Professor Rina Kos for her kind introduction. And I'd like to thank all the organizers, especially Professor Kasturi Mukhopadhyay, for inviting me to this Professor Ashima Chatterjee scientific special session in SEC 2021. And it's indeed a great honor to give a talk in this special session. I would first like to pay homage to Professor Chatterjee, a legendary organic chemist, and she is also a guiding star for women in science in our country. And her life needs to be told and retold through these scientific activities to encourage all of us to motivate the younger generation. So with this, I'd like to start my talk. And as Professor Chatterjee has significantly contributed to alkaloids, in the field of alkaloids, as a tribute to her, today I would like to give a talk on construction of nitrogen-containing heterocycles by olefin metathesis. I would begin with my talk by giving a brief outline of our research activities. One of the major areas of research in our group is targeting nucleic acids by small molecules, and I have been giving this talk on different platforms. But today, for a switch, I would like to talk briefly about our work on synthesizing nitrogen-containing heterocyclic compounds like carbazoles and other ring systems. So I would just give in 2 minutes about our work on DNA secondary structures. That when we talk about DNA, we always think it's a double helical, but DNA can also adopt other higher-ordered secondary structures. For instance, this G-rich DNA sequence can adopt a quadruplex structure, and its complementary series DNA sequence can also adopt a 4-stranded I-motif structure. And these structures are present in the promoter regions of several oncogenes. And it has been shown these molecules can bind and stabilize this.
Professor Dash, we can see it in full screen. Please.
You can see in full screen?
No.
Your slides are not visible.
But I could see actually. I don't know. Check again.
Yeah, I could see the.
Okay, in that case, move on. Please move on.
Yeah, go ahead, Jyoti.
Yeah, this is fine.
Okay.
Yeah. Okay. Yeah, so we have been it has been shown small molecules can bind and stabilize these structures and can modulate gene expression in cancer cells. So in this slide, I just summarized our work. Like, we design and synthesize small molecules. We study their binding interactions using a series of biophysical techniques. And we have also identified molecules that can fold these unstructured compounds to quadruplexes and I-motif structures. And these small molecule and DNA interactions we have been using in therapeutic applications, as well as devising biomolecular devices. Like, for instance, we have used a DNA and small molecule to devise artificial ion channel for transportation of metal ions across the biological membranes, including cellular membranes. And we have also used DNA and RNA bases to build biomimetic systems. And in our lab, we also developed new synthetic methods to synthesize small molecule heterocycles. And today I'd like to give a brief overview of a part of it. So as I said, like my title that we have been using Yeah.
Excuse me.
Yes, please.
Jyoti, this
Yes.
is Subrata Ghosh.
Yeah.
I cannot see your slide.
Now you
Can
please
you
see
make
the
it?
presentation. I think I have. Okay, let me.
Yeah,
just...
I am seeing the presentation, but it is not visible.
We can see.
I
We
mean,
can see it.
But Subrata, we can
We can
see.
see. We can. It is fine.
It is showing up in a small icon. You click on that and it will get enlarged.
Which icon?
That
No,
pin, that
showing
pin.
up in a small icon, okay? Small window. And you click on that and then it will expand.
Okay, okay. Okay.
Ma'am,
Any-
rather you can represent it.
Yeah.
Anyway, still I cannot see it. I can
Yes,
see
it
it
is not
is
visible
very
to
small,
everyone.
very small.
Huh.
Anyway, go ahead, go ahead.
Yeah. Mm.
No, it's
Now can
visible
you-
properly. It's
Now
visible.
can you see?
Yes, yes. This
Yes,
is
go ahead,
visible.
go ahead.
Yeah. So as my title, we have been using olefin metathesis to synthesize small molecules heterocycles. So olefin metathesis is a very powerful tool. I don't have to give an introduction. Only I am putting this slide to pay a tribute to Professor Grafs, whom we lost just 2 days before. So this is a Nobel Prize winning reaction. It's in one word we can say it's just like a partner swapping chemical dance. So we have been using ring closing metathesis, cross metathesis, ring opening and cross metathesis, and also sequential transformations to synthesize and functionalize heterocyclic compounds. Actually, our first project began with olefin metathesis to synthesize and functionalize heterocyclic ring systems. This is my first PhD student who joined at ISEP Kolkata. So we started with a simple 5-member ring system like thiazolidinedione, and we synthesized pyrocyclic ring system by using Graf's second generation or Graf's second generation catalyst. And we have also used a one-pot ring closing metathesis, cross metathesis to functionalize them. So just to show this in brief, that we have used this hydantoins and it was treated with allyl bromide and in the presence of base to obtain this triallyl compound, which was treated with Graf's first and second generation catalyst to obtain spirocyclic, this N-allylic compound. We have also detected the formation of this dimer, which was obtained by self-metathesis of this N-allylic compound. And we could also isolate and exclusively prepare this dimeric compound, and this dimeric compound underwent smooth cross metathesis with olefins, and by this we could functionalize the spirocyclic system. And this compound was also obtained by cross metathesis of N-allyl spirocyclic system. And we have also developed a relay ring closing metathesis and cross metathesis in a single pot using a single catalyst, that is Hoveda-Graf's catalyst. By treating this N-allylic compound and then adding this different olefins, we could synthesize this functionalized spirocyclic compounds. So then we have extended the scope to the nitrogen analog, that is Heidenreich ring system, and these could be used as a building block for diversity oriented synthesis, because we could make use of all the 4 positions of this Heidenreich building block. So by using different bases, we could synthesize diallylic like N and C diallyl compounds. For instance, we have used this 5,5 disubstituted Heidenreich to obtain spirocyclic Heidenreich, and we have also shown an application that this spirocyclic compound could be cleaved to give unnatural amino acids. Next, we have used 1,5 disubstituted allylic system to obtain 6, 7, and 8 membered ring systems. We could also make use of N3 and C4 positions to prepare these bicyclic fused ring systems. And then we have also used the C4 and C5 diallyl compounds to synthesize this hexahydroimidazolone ring systems, and the trans stereochemistry was confirmed by the X-ray crystal structure. So I have shown in brief that we could use, we have taken these small heterocyclic systems like thiazolidinediones and Heidenreichs, and we could build different compounds like spirocyclic.
Professor Das, are you showing any slide?
Yeah.
Or you are speaking only?
I'm showing slide.
We have not seen your any slide. No slide is visible. Only your face is, I am at least looking. I am not sure whether others what they are seeing.
No. Actually, in some cases.
Oh, it is better you close your slide and re-enter from the side.
That will be better. I
It will be
think.
better.
No, this is third time I have done it.
Actually, it is coming as a small window, and when you
Yeah.
pin it, it is becoming a big
Yes.
one.
Have you joined
You need to pin it.
Now could you see it?
Yes, now it is
Yeah,
visible.
yeah,
It is
So
visible.
last time also said that it is clear.
yeah.
Okay, anyway, yeah, so by using this simple Heidenreichs and thiazolidinediones, we could synthesize different classes of compounds like spirocyclic and fused ring systems, and these building blocks could also be used to synthesize the cyclic amino acids. So next, we have extended it to Isatin ring system, and it was first started with Kalyan, and then Tirtha Mandal at ISCS has taken over and has done remarkably well. And we have recently published a perspective where we have shown that these isatins can be used as building blocks to obtain both indole fused heterocyclic systems like carbajols and pyridoindoles. So for carbajols, there are many synthetic methods are known, and one of the commonly used method in the lab is oxidative cyclization of this diaryl amines, and these diaryl amines can be obtained by Buchwald-Hartwig coupling reactions. We envision to synthesize these carbajols by using a ring rearrangement aromatization of these spirocyclic compounds, and these spirocyclic compounds can be obtained by ring closing metathesis of these allylic compounds, and this could be obtained by isatins. But theoretically, the allyl metal addition would provide this dihydroxydiallyl compound. Ring closing metathesis followed by dehydration should give the carbajols. So with this plan, we have carried out allyl metal addition to isatins, and we have observed this formation of this diallyl oxyindoles, and these dihydroxydiallyl compounds were not obtained. So this is possibly due to the allyl metal addition to both keto and amide carbonyl, then removal of this ONGBr group and the formation of this indolinium ion, then 1,2 allylic shift provided this 2-diallyl 3-oxyindoles. So then we have carried out sequential allyl metal addition. First, allyl metal addition by using indium metal, which is quite chemoselective. We could selectively obtain this hydroxyallyl compounds. Then we have carried out sequential allyl metal addition, and we could see the shift of this allyl group to this position. For instance, this internal phenyl group was transferred to the terminal group. So thus we could synthesize this metathesis precursors, that is this diallyl oxyindoles, by using sequential allyl metal additions, and then ring closing metathesis using Graf's second generation catalyst provided a new synthetic route to spirocyclic 3 oxyindoles. Mostly spirocyclic 2 oxyindoles are known. The synthesis there's a number of methods to synthesize spirocyclic 2 oxyindoles, but we could establish a new route to its regioisomeric spirocyclic 3 oxyindoles. Then as per our plan, we have used these compounds with paratoluene sulfonic acid, which provided the carbazole derivatives by first via protonation of the C3 carbonyl group, then ring expansion by this 1,2 allylic shape, followed by dehydration and aromatization provided the carbazoles. So then we thought of developing an orthogonal tandem catalysis by combining both ring closing metathesis and ring rearrangement aromatization in one pot. So we have taken these diallyl compounds and treated with Graf's second generation catalyst and acid catalyst at the same time, and we could exclusively obtain the carbazoles via the formation of this spirocyclic compound. Both paratoluene sulfonic acid and trifluoroacetic acid worked well. So thus we could synthesize carbazoles from lecithins in just 2 steps, that is allyl metal addition followed by orthogonal tandem catalysis combining HCl and a ring rearrangement aromatization in one pot. So next we have used this method to synthesize different carbazole alkaloids. First, we have synthesized this 3-hydroxy 4-methyl carbazole. First, we have synthesized this lecithin by using a Sandmeyer's method. And then we have followed our sequence, that is allyl metal addition followed by ring closing metathesis and ring rearrangement aromatization to obtain carbazoles. Then removal of this benzyl group provided the compound which could be used for the synthesis of a range of carbazole alkaloids like DDQ mediated oxidation provided muconal, then copper to catalyzed dimerization provided this bis-2-hydroxy 3-methyl carbazole. This is also naturally occurring bis carbazole compound, and then C alkylation using prenyl bromide and an organic base like diisopropyl ethylamine provided giri-nimbylyl, then DDQ mediated aromatization, DDQ mediated oxidation of this methyl group provided this heptafilin. And we could also synthesize giri-nimbine by titanium isopropoxide mediated cyclization, and then this methyl group was oxidized to give muriacin, and palladium catalyzed Walker's oxidation provided eucrestipholin. So thus by using a simple synthetic state, so we could make a carbazole ring system and a series of carbazole natural products. So in our synthesis, we have obtained this diallyl compound, and this dihydroxydiallyl compound was not obtained. So we thought to eliminate, to remove this dihydroxy compound and synthesize this diallyl indole derivatives. And for that, like we have developed a new synthetic route to synthesize indole derivatives, and as we really did not find many synthetic methods to synthesize this diallyl indole derivatives. So our synthetic step involves dehydrative aromatization of these 3-allyl 2-oxyindole building blocks, and which could be obtained from the lecithins. So when we look at the literature, we find many methods are known to synthesize 3-allyl indoles, and also there are few methods to synthesize regio-specific synthesis of 3-allyl substituted indoles. So in order to synthesize a practical and scalable synthesis of 2-allyl indoles, 2,3-diallyl indoles, we thought of developing new methods to synthesize these allyl substituted indoles. So in the literature, we find like for the 2-allyl systems, 3 methods are known, and that involve transition metal catalyzed reactions and donating group like 2-pyrimidine group or directed synthesis of these two allyl indoles. And again, there are two synthetic methods are known for these 2,3-diallyl indoles. And we have also found out that estatins have been used to synthesize 2,3-disubstituted indoles, but this method cannot be used to synthesize 2-allyl or 2,3-diallyl indoles due to the shift that we have observed, that is this indolinium ion mediated allylic shift. So our approach was to synthesize these indoles via this Grignard addition of these oxyindoles, and this could be just obtained from these hydroxy oxyindoles, and which we have already shown that by a chemoselective alkyl or aryl metal addition we can synthesize these hydroxy compounds. Removal of this hydroxyl would give these 3 substituted oxyindoles, and then Grignard addition would provide this disubstituted compounds. So this method could be effectively used like allyl metal addition and tin chloride mediated removal of this hydroxyl group. We have synthesized a range of these 3 substituted 2 oxyindoles, and we have also synthesized these 3 allyl substituted 2 oxyindoles, and then a Grignard addition provided.
So sir, there's only 1 minute left.
Yeah, so diallyl indoles. So this the mechanism is simple, like this is Grignard addition and removal of this OMGBr gave these 2 allyl compounds, and this method was used for the synthesis of a microtubulin inhibitor, and we have also extended this method to synthesize 2 aryl and 2 allyl indole derivatives, and finally by using this method we have synthesized these 2,3-diallyl and 1,2-diallyl ring systems, and this could be used for the synthesis of carbajols and pyridoindole derivatives. Thus, we could establish an orthogonal synthetic approach to synthesize pyridoindoles and carbajols from oxyindoles, and we have also developed 2 new synthetic routes to synthesize carbajols from estatins through oxyindole building blocks. So I have already shown you these 2,3-diallyl indoles and diallyl oxyindoles. Next, we thought of to extend this scope of olefin metathesis and to do some cascade metathesis. We have synthesized triallyl precursors like triallyl indoles and triallyl oxyindoles. So I'll show you one example. Like we have taken this triallyl oxyindoles by the AA mode of ring closure would give this pyrocyclic compound, and this AB mode of ring closure would give this tricyclic compound. Quite interestingly, so this would be thermodynamic product, the AB mode of closure, and AA mode of closure would be a kinetic control. Quite interestingly, by using Avogadro's catalyst, we have obtained first this pyrocyclic compound via this AA mode of ring closure, and then by heating this compound for 3 days, and we obtained this compound. So which is a series of reactions took place in one pot. That is first ring closing metathesis, then ring opening metathesis, again ring closing metathesis, and cross metathesis to obtain these compounds. So thus I have shown you that by simple Heidenstein's thiazolidine ions can be used to obtain spirocyclic and fused ring systems, and esatin derivatives can be used to synthesize indole fused ring systems. And this method was also extended by Shilpi to synthesize orthoterpenols and fused aromatic compounds, not only olefin metathesis. We have also developed a 3-step sequence to synthesize many acridone family of alkaloids without using any expensive catalyst. And I'll just show this slide and conclude my talk. So here we have used anthralinic acid and this phenol derivatives. By condensation, we could obtain this acridone ring system, and then cyclization, the reduo-selective annulation by using titanium isopropoxide gave this F4 tetracyclic ring system of acridone family of natural product, and then by protection deprotection we we have synthesized acronization, noracronization, the synthetic steps remain same, and just changing the substituents, atalophylidine, 5-hydroxy noracronosine, and we, for the first time, we have also synthesized oxan thia analogs of the acronosine. With this, I'd like to thank all of you for giving me an opportunity, and I'm also sorry that I could not see my slides. I'd like to thank my students for their hard work, and also funding agencies for financial support. Thank you.
Thank you, Professor Das, for your nice and scintillating lecture. Since the session is running behind schedule, so I can take only one question from the audience. Any question from the audience? Okay.
Yes, I have one question.
Okay.
Jyoti, can you go back to you slide number 13 or 14 regarding this synthesis of Spiro, where you have used ring closing as well as cross metathesis?
This one.
Yeah, see, you have 3 alkene units.
Yes.
Okay, and then you have one cross metathesis partner. And what is the reaction path actually taking place?
Yes, what we have done is
First ring?
first ring closing metathesis, then cross metathesis, because this reaction is very fast. And if we use so what we have done is we first used for some time, 8 hours, we leave it. This is obtained, and then we have added the other olefin. But this did not undergo any ring opening metathesis under these conditions. So this was the product, very stable and efficiently we have isolated this compound.
Okay, but you can think of it the other way, that since you are adding as well as this one together and then the catalyst, then maybe first all the 3 are undergoing cross metathesis, and after that these 2 after cross metathesis undergoing ring closing metathesis. Did you follow me? First
Yes,
cross
I
metathesis.
understood. I understood, but since there are different substituents like this, we did not isolate any of this. So that's why we have just shown it as an intermediate step for this.
So did you try the reaction without these things, whether this is first, this reaction, ring closing metathesis is going too fast? Because you mentioned this, since
Yes,
they are...
ring closing metathesis is going very fast because of this ring system, spirocyclic to this. So this is very fast. Then metathesis takes little time because this is room temperature. This takes like 40 degrees some time. So cross metathesis fast is not possible. And also ring opening also we have to heat it and clean it.
Okay, thank you.
So thank you, Professor Das, again for your nice lecture. I'm moving to the next lecture. It is again an invited lecture, and it is an award lecture, Professor Ashima Chatterjee Memorial Award lecture, to be delivered by Professor Mrs. Bani Talapatro. She will be talking on, or her talk is entitled "A Tribute to My Teacher, Professor Mrs. Ashima Chatterjee." Now, I am really happy and honored to chair a session where I have the opportunity to introduce Professor Mrs. Bani Talapatro, our respected beloved Banidi, who actually needs no introduction. Still, as a customary, I would like to say a few words on her. Professor Talapatro her latest affiliation is INSA Council member, ICS Life member, former Council member. Professor Talapatro taught natural product chemistry at Calcutta University for more than 3 decades, and in some other universities of West Bengal and Tripura as guest lecturer for more than a decade and lectured in many universities as a resource person of UGC refresher course. She taught general chemistry in Victoria Institution for several years during her early career. She obtained her DSc degree, which was actually the second lady. She was actually the second lady DSc from Calcutta University. Worked with Professor Mrs. Ashima Chatterjee, and then joined as a postdoctoral fellow at the microbiology department, Vanderbilt University, with a renowned microbiologist Professor V. Nancher. She there she had the opportunity to learn much about organic chemistry mechanism, which was in its infancy at that period of time, from Professor C.K. Ingold, who was actually the visiting professor at that time in that university. After more than 3 years of her return, she joined the chemistry department of Calcutta University as lecturer and eventually became professor and head of the department. As a UNESCO senior visiting scientist in 1976 and 83, she was briefly associated with about 2 dozens of outstanding scientists, professors of major universities of USA, UK, Germany, and Japan. She also participated in more than 25 international conferences in USA, Europe, Southeast Asia, and India. Her research interest includes various aspects of natural products chemistry, including terpenoids, alkaloids, phenolics, reaction mechanism, and stereochemistry. She published more than 130 research papers in reputed international journals, and she co-authored with her husband, Professor Sunil Talapatro, a unique text from reference book titled Chemistry of Plant Natural Products, where Professor C.K. Nicolaou actually wrote the foreword of the book, which was published from Springer Verlag in 2015. With these few words, I am requesting Professor Talapatro to deliver lecture. Professor Talapatro, please.
Thank you, Professor Ghosh, for your very kind introduction. And you said so many things, whether I don't know I'm fit for those, and you made my task quite difficult in that sense.
Just a minute, ma'am. Just a minute. Professor Das, please remove your presentation. Professor Das.
Professor Das, remove your invitation. I'm calling him.
Yeah.
So with visiting memory, I have to search for words while talking. So I would like to read out what I want to say. I'm thankful to the organizers of the symposium, especially to Kasturi Mukherjee, Department of Chemistry, JNU, New Delhi, to Professor Chanda Mukhopadhyay, the immediate past head of the Department of Chemistry, Calcutta University, and to Professor Chittaranjan Sinha, Honorary Secretary, Indian Chemical Society, for kindly asking me to recollect my experience with my revered teacher, Professor Mrs. Ashima Chatterjee. And I consider it to be a special privilege and an honor to me. I beg prior apology in case I get emotional. I begin by offering my salutation at the feet of my teacher, Professor Mrs. Ashima Chatterjee, and my mother, who were responsible for whatever little I could achieve till death. The shining light of the life tale of Professor Mrs. Ashima Chatterjee finds an expression in the deathless lines of Tagore, which I now quote. Bipode more rokha koro, inohe mor prarthona, bipode ami na jano kori bhoy. In English, also by Tagore, it is not my prayer that you save me from all perils. I pray that I shall not fear when faced with odds. In fact, Professor Mrs. Chatterjee faced many difficult situations in her life, but her self-confidence and close association with Ramakrishna Mission helped her to overcome the difficulties and allowed her to hope, and her natural confidence began to reassert itself. Professor Mrs. Ashima Chatterjee, one of the enormous contributors in science from India, was an indomitable, incontestable, courageous, and academically adventurous scientific personality with indestructible spirit, screaming dedication, and considerable resilience. She was born as Ashima Mukhopadhyay on 23rd September 1917 to an enlightened family. Incidentally, 1917 was also the year of birth of the crowning prince of organic synthetic chemistry, Professor Robert Burne Woodward. Her father, Dr. Indubhushan Mukhopadhyay, was a medical man who also used to teach at Bangabasi College, Calcutta. Her mother, Srimati Kamala Devi, was a housewife, and she was a very well-read woman. This is indeed a very unique family in which both the sister and the brother, Dr. Saraswati Ranjan Mukhopadhyay, were the recipients of the Bhatnagar Award, the highest academic award in India, in their respective fields. Their parents affectionately used to call them by their nicknames Tuti and Tota, respectively. Professor Ashima Chatterjee was an iconic personality in the Indian science scenario. Her name commands admiration, honor, and reverence. Generally, the big people are more respected than loved, but Mrs. Chatterjee was equally loved and respected by all who came in contact with her closely. She was the owner of many firsts in her stellar academic career. She was the first woman president of Indian Science Congress Association, considered to be the crowning attainment for any scientist in India. Statistics suggest that as the people go up the pyramid of success, the women are filtered out. But Professor Ashima Chatterjee stands as an exception to this common bywords derived from the social statistical data. She attained the towering height in the exceptional assembly of Indian scientists. I first met her when I entered the Lady Brahman College in 1951 as a student of intermediate science. A few characteristic traits of her attracted me most. Her immaculate dress in bordered white sari, simple parting of her hair, a pair of bright eyes behind her thick glass, an unalloyed, welcoming smile on her face that reached her eyes and stayed there, and a unique delivery of the subject matter with distinctly clean pronunciation. All this inspired me and became an all-enveloping issue in my career, and I found chemistry as the subject of my choice. In fact, I was so much in love with her teaching that every day when I came back home from Lady Brahman College, I used to stand in front of a big mirror in my house and copied her way of teaching. My mother watched me every day and appreciated my endeavor. Professor Mrs. Chatterjee was a possessor of a distinguished academic career. She studied in Bethune Collegiate School and Bethune College and received government scholarships in both the matriculation and high school examinations. Additionally, she obtained Hemoprabha Bose Memorial Medal of Sadharan Brahmo Samaj on her intermediate exam results. She then joined the Scottish Church College for studying chemistry honors. It was a co-education college. It is still now the same. Some objections she faced against her admission by some conservative members of the family, but her mother emotionally supported her and she got admitted. Scottish Church College was a famous college at that time because it produced students like Swami Vivekananda and Netaji Subhash Chandra Bose, the two world-famous personalities. Ashima Chatterjee also added her personal academic grace to this college. In front of the college, a shop was there selling telebhaja. Subhash Bose enjoyed eating telebhaja sitting on bench. The bench is still there. The present students eating telebhaja there want to sit on that particular bench to feel the divine touch of that great man, perhaps the greatest leader of our country. I am fortunate to be the student of the college, and I remember the first day I entered the college. I took the little dust from the stairs leading to the foyer of the hall and put that on my head, imagining those to be the dust of the shoes of those great men. Now coming back to Oshimagi, she passed the MSc examination with organic chemistry special from Calcutta University and stood second in the first class and received the university gold medal. She then joined the research group of Professor Prafulla Kumar Bose, a Germany-trained organic chemist and a pioneer in the field of natural product chemists of India. She got her DSc degree of the Calcutta University and was the first female recipient of the same and from an Indian university. Prior to those, she received Premchand Roy's scholarship, Nagarjuna Prize, etc. from the university. After obtaining a MSc degree with organic chemistry special, I joined Professor Mr. Chatterjee's research group as a part-timer as I was serving Victoria Institution as a teacher. My college, my residence, my college and the science college were within a short walking distance, and so I could afford to devote adequate hours each day for research and also could stay beyond the evening hours. I didn't have to waste time in walking a distance. I remember I stayed overnight at Science College one day when one of our research colleagues, Dr. Sharolnath Ghosh, was submitting his thesis. I was helping him in drawing structure. In those days, there were terms for the submission of the thesis. If not submitted within certain time, it will be shifted for the next term. Oshimagi used to stay at BE College campus at Shibpur near Botanical Garden. Since her husband, Professor Baradananda Chatterjee, was the professor and head department of chemistry and metallurgy at BE College, and it was a residential college, and his residential quarter was a very big one. Their only daughter, Julie, a past Palit professor and head of the Department of Chemistry, Calcutta University, was studying at that time in Loreto House, Middleton, adjacent to Fleury, with the Park Street. She used to drop Julie every day before 9 o'clock in the morning, and then used to come to Science College at around 9:30. After the school, Julie used to come to Science College and had some tiffin and did her homework sitting in the cubicle of Professor Mrs. Chatterjee. All the students were very fond of Julie. She was looking innocently beautiful and full of life. One day, I remember Julie accidentally broke a success apparatus, and Oshimagi scolded her like anything and even started beating her in the lab. Escape. Julie cried and wanted me to go to BE College that night. I went and managed somehow to save Julie. Oshimagi personified all the apparatus and loved them as living beings. Sometimes she also moved away from the people and identified herself with the apparatus she loved so much. I used to go to BE College on Sunday and sometimes stayed overnight and came back next morning directly to Science College, especially during the writing of my thesis. My mother allowed me that. In fact, I was almost like a family member. Julie sometimes learned drawing from me and studied Bengali with me. In the house, Oshimagi behaved very nicely and kindly to me, but in the laboratory, she was a very strict master and would not spare if we did something wrong. Some apparatus should be always kept cleaned and dried so as to be used any time of need. All the flasks and sometimes the beakers containing materials should be properly labeled and preferably with date. The sample tubes were to be cleaned by boiling them in a beaker containing nitric acid and a few drops of alcohol, followed by thorough washing with water and dried. The corks of the tubes were to be wrapped with tracing paper. For sample drying, Abderhalden apparatus was used, and then the samples were kept in desiccator. Professor Chatterjee first introduced the seminar system amongst the students in our department, and at the beginning, the seminars remained confined within the respective teachers group, and then it was open to all the students of the department, and also the viva exams of the PhD students, which were earlier private, were open to the departmental students in the form of a seminar. One of the greatest contributions of ours was the building up of the instrumental facilities in the department for the researchers. Initially, IR machine came, then one HNMR, 80 megahertz, 90 megahertz, 100 megahertz, 300 megahertz, and finally 400 megahertz we have. Instruments came as a boon to the researchers and that facilitated the research rate amongst the students, and the results were well equipped with data and found good journals for the acceptance in the form of paper. She also arranged for the liquid nitrogen and liquid helium for cooling the magnets of the animal machines, and also arranged for the dilated solvent to be used for making the solvent a sample solution. A big project of UNDP through UC was operative in the department, and exchange of scientists program started operating. All the organic chemist teachers were sent abroad to work in reputed laboratories and to soak ideas through interactions and work under expanded facilities. This helped in research as well as in teaching. I recall one incident which still emotionally moves me. In 1968, we were stuck up in Jalpaiguri in a devastating flood caused by the rise of the water level of Tista and its tributary Corolla River that runs through the city Jalpaiguri still now. The water level was much above the danger level. As a consequence, there were thousands of human casualties and livestock. We took shelter on the column of our under construction house. The old house was demolished, which is a bungalow type, and we stayed standing nearly for 2 days, more than 36 hours, without food and drinking water, and finally rescued by military. We were saved but lost all belongings. Damaged rail tracks were under repair and water at what footing rate. There were several landslides in Darjeeling. Darjeeling and Jalpaiguri districts were disconnected with the rest of the world. My sister used to go to Shialda station every day for any positive news about us. Trains started taking detours, and finally we reached Shialda station after 2.5 day train journey, which normally takes 10 hours. In the evening of the day of her arrival, the doorbell rang. I opened the door and found Ashimaji standing there. She held me in her bosom and cried. Initially, I thought that something wrong happened in her house. Her mother was not keeping well. But then why would he come to us? I wondered. No, she cried out of joy. She found us unhurt. We knew she loved us, but that day we realized the depth of love. She was not only a teacher, she was also our mother. Otherwise, that type of emotion could not be erupted. That day, in the late evening, she sent through Vimunnu a big tiffin carrier full of food, rice, vegetables, dal, fresh curry, and she didn't even forget to give fish curry, and she didn't even forget to give salt and green chili separately. I cried looking at the food given with great love and care. Misfortune doesn't come alone. She lost her husband and she lost her father in the middle of 1968, and in the same year, in November, probably on 9th, she lost her husband all on a sudden, who died of irrecoverable cerebral stroke. That day, the marriage ceremony of her telephone operator Nilu Babu's son was celebrated, and we are all invited. I and Dr. Tarapasu went separately, and Professor Shuru Mukherjee was also there. It was fixed that Dr. Baroda Chatterjee would come to Science College from GE College in the afternoon, and Ashimaji and Dr. Chatterjee and Julie would go together, and they would take with them Professor Satyen Bose. We stayed up to 9 o'clock. Mrs. Chatterjee did not appear. We thought she would come late, and we left. Next early morning, our doorbell rang. I opened the door and found Professor Amitabh Sen of Bose Institute, wrapped in a wrapper shawl. I thought that he came for just collecting milk from the cowshed near our house, and I welcomed him within the house, and he didn't enter. He said, yesterday night, Professor Baroda Chatterjee died of cerebral stroke. Professor Sushil Mukherjee was already there and instructed him to inform us and to come to B College as soon as possible. It was like a bolt from the blue to us. Our son was a baby at that time. We kept her in my mother and started for B College and entered the house from the side of the kitchen and found Mrs. Chatterjee sitting on her bed. In the living room, full of neighbors. The neighbors were there, mostly the wives of Professor Chatterjee's colleagues, but none could approach Mrs. Chatterjee. She was too shocked to cry. In the living room, Julie was crying ceaselessly and she was exhausted. As soon as Ashwati saw me, she said loudly, "Bunny, Dr. Chatterjee chole gele." She cried and said loudly, and she cried for the first time. I sat by her side and said, "Nothing, could say nothing." Dr. Chatterjee was lying peacefully on a bed in the living room. His students and colleagues were all around. I remember Dr. Tripurari Chakraborty came. He recited from Gita and then he uttered the following lines, sitting by the side of the dead man, perhaps on behalf of Ashimadi. Tripurari Babu said, "Amar জীবনে তুমি বাঁচো গো বাঁচো, তোমার কামনা দিয়ে চিত্ত মোর যাচো, আজ তুমি মোর মাঝে আমি হয়ে আছো, আমার জীবনে তুমি বাঁচো গো বাঁচো." Her brother Sharshida came along with his mother and wife. He took care of the whole situation. Dr. Chatterjee's elder brother and nephew all came from Gushkara, the native village of Dr. Chatterjee. Finally, the body of Dr. Chatterjee was taken away to the burning hut of Shivpur. Ashmadi felt a big vacuum. I stayed in her house for consecutively 3 to 4 days, keeping my child to Dr. Talapatra and my mother at Calcutta. I slept between Julie and Ashmadi. First 2 nights she could not sleep, uttering soliloquy about the blissful moment she spent with Professor Chatterjee. After a month or so, she came to Science College, and on the first day, she was emotionally gripped and fainted, followed by a heart attack. She was moved to the PG hospital, where her brother was the director at that time. She was treated and stayed in the hospital for some time and came back later, gradually recovered and allowed her to hope and threw herself fully into research and teaching. She knew what is the remedy of all miseries that shattered the lives. The most pervasive and valuable of mind's all defenses is belief in self, and she had that quality, and a wave of relief washed over her. With stunning confidence and energy, she threw herself completely into work. She considered her work to be her life jacket and spinal support, and she knew that posterity would judge her by her work, and thus she was gradually growing at peace with her past. For the outstanding contributions on natural product chemistry, she was awarded all the prizes of India government that were open to a chemist of the country. She received honoris causa from some universities of the country. As mentioned earlier, she received S.S. Bhatnagar Award, C.V. Raman Award, Goel Prize. She was made the member of the Rajya Sabha and awarded Padma Bhushan, the 3rd highest award by the government of India, and conferred the distinct citizenship of West Bengal by the Mayor of Calcutta Corporation. She was the first female Padit professor of Calcutta University, first female dean of the Faculty of Science, first woman to be awarded DSc from any Indian university in 1944. She was the first Premchand Rajah Scholar of Calcutta University, first female. The Ministry of WC, that Women and Child Development, established 11 chairs in the names of Indian women scientists at the institutes across India to recognize and honor the Indian women scientists' contribution in the field of science, also to inspire young girls for greater participation in science and to achieve excellence. Professor Ashima Chatterjee belonged to one of those 11 chairs in the field of chemistry. We feel highly honored for the prestigious position and very much hope that this position should be instituted at the Calcutta University, where Professor Mrs. Chatterjee spent her life. She died at the age of 89 in 2006 after a brief illness. She will be loved, respected, and remembered as a teacher, as a researcher, as a research guide, and on the top of everything, as a passionate, humble, and kind human being. For her simplicity and sincerity, she was loved by Acharya Praful Chandra Roy and many senior professors of that time in the university. Apart from academic excellence, she was a possessor of many admirable qualities. She had a long training in singing, and I was fortunate to listen to her song one day at B College, and she sang Purno Chader Maya Ji Bhavna Amar with harmonium. She was out of practice, even though she did it perfectly well. There is no mistake in the sound or in the words. I conclude by offering again my salutation at her feet and reciting a short poem composed on her by me in Bengali as a tribute to her, and also showing a pencil sketch drawn by me when I was her research student. তুমি যা দিয়েছো কোনো মূল্যেই হবে না সে ঋণ শোধ, সে পাওয়া শ্রেষ্ঠ পাওয়া, জীবনের সেই মূল্যবোধ দেখায়েছে আলো, উজ্জ্বল আশা, সকল শুভ কাজে দিয়াছে ভরসা। তুমি জ্বালিয়াছো মঙ্গল দ্বীপ আলোকিত করি পথ, জ্ঞান ও স্নেহের তরণীতে মোরে করিয়াছো পারাপার। জানি না কতটুকু তার পেরেছি করিতে গ্রহণ, সরিয়া তোমার দান অকৃপণ, বিনীত প্রণাম করি নিবেদন। I sincerely thank Dr. Subhendu Mondal for kindly giving me some information on Professor Mrs. Chatterjee, which I have incorporated in my present talk. The picture is shown here. দেখা যাচ্ছে কি ছবিটা? না, দিনা ছবি ছবিটা দেখা যাচ্ছে কি?
No, no, no.
এবার
No.
দেখো তো
No.
কি করলে দেখা যাবে কি করলে? না আমার মনে দেখা যাবে না নিতে।
No, we can't see it.
হ্যাঁ,
Some reflection is coming actually.
এবার দেখা যাচ্ছে না?
We can see now.
ভালো করে বোঝা যাচ্ছে না?
Yeah, now we can see it. Yes, yes.
এটা আমি অনেকদিন আগে যখন আমি ওনার কাছে রিসার্চ করতাম।
She was quite young. Yeah.
ভালো বোঝা যাচ্ছে না ছবিটাতে।
No. We can see now.
হ্যাঁ,
We can see it now. Yeah. Now it is. We can see it.
Yeah.
দূরে রাখতে হবে। দূরে রাখলে তো বোঝা যাবে। ঠিক আছে। পেন্সিল স্কেচ আছে।
Very nice. So, thank you, Professor Tolapatro, for your nice and informative lecture. You have focused several aspects of Professor Ashima Chatterjee's life, and thank you for sharing those with us. You have shared those via your walking through your memory lane, and with these words I again thank all the speakers of this session also for their lectures, and at last I would like again to convey my homage to to Professor Ashima Chatterjee, the legendary scientist of this century of our country. And I would also like to thank again to the conveners and the organizers of the symposium for giving me the opportunity to chair this session, this special session, brother. And thank you all. Okay, over to.
May I request to Banidi, Bani Madam, to give your this write up to Chemical Society. We may publish in our periodical, which is a educational part, so that will help the future generation.
Yes, it is so informative. Very informative.
I could follow what you said, please, once again. Professor Chitra Sinha?
আমাদের পিরিয়ডিক্যাল যে বইটা বেরোয় সেই বইতে অসীমা চ্যাটার্জি সম্পর্কে লেখার জন্য আপনার এই লেখাটা দিলে আমরা পাবলিশ করব কেমিক্যাল সোসাইটি।
ডেফিনেটলি আমি একটু ঠিক করে দিয়েছি, এডিটিং করে দিয়ে দেব।
She has shared so many things. Yeah.
Thank you.
One more thing I would like to mention that it was an award lecture, and the award to Professor Bani Talapatro was shown at the beginning of this session by Professor Kosturi Mukhopadhyay. online, and it will be posted to the residential address of Professor Pani Talapatra in near future. Okay, thank you.
Thank you.
Instead of posting, could be delivered by messenger.
Right. It can be delivered by messenger.
Yeah.
Many of you know my house.
Okay.
Some of my students are there, you know. Ashok Malik can take, can bring. Sanjay Bhar can come.
Yeah. We'll do that. We'll send by person.
By messenger.
By messenger will be better.
Yeah, yeah.
Now over to the convener.
Yeah, Professor Vimlesh, please.
Thank you. After listening to this overwhelming story and the life through, it's like I'm really emotional right now. I believe so does the others. So shall we take to the next session, Professor Kasturi? Yes.
Yes.
Since we are running a little bit late, and I really thank on behalf of the organizing committee to Professor Reena Ghosh for taking that very nice script, the earlier session. So now we are moving to the next special session. So I thank you to all the earlier speakers. So now I'm continuing for the next session. So good afternoon to all the dignitaries, scientists, faculties, and students. On behalf of the Indian Chemical Society and organizing committee member of the Professor Ashima Chatterjee special session in 58th ACC 2021, I would like to invite you all to the next special invited lecture award session. We feel extremely fortunate to have Professor Sharmila Banerjee, Professor Anju Chadda, Professor Sheila Ramashisha, and Professor Samita Banerjee as delegate speakers for the respective awards: Marie Curie, Rosalind Franklin, Kamla Soni, and Rohatgi Mukherjee Memorial Award. And these awards are given to all these special contributors to the science. I request Professor Kasturi Mukhopadhyay to showcase the award medals here in the online mode. These medals will be posted at the respective address, which have been shared to us soon. This award is for Professor Sharmila Banerjee. Professor Kasturi, next one, please. Professor Anju Chadda for the Rosalind Franklin Memorial Award. Professor Kamla Soni Memorial Award is for Professor Sheila Ramashisha. And Professor Rohatgi Mukherjee Memorial Award is for Professor Samita Basu. So this session, thank you, Professor Kasturi, for showcasing these medals. This session will be chaired by none other than the special renowned scientist, Dr. Tulsi Mukherjee. I briefly, there's so many big list of his achievements, so just I will go briefly over it. Dr. Tulsi Mukherjee is former director in chemistry group at Bhama Atomic Research Center, Mumbai, distinguished scientist, Government of India, senior professor at Homi Bhabha National Institute, former director at Shah Chulman Center for Surface Science and Nanotechnology in Gujarat. He did his MSc from University of Calcutta and PhD from University of Bombay. He is a fellow academy member of National Academy of Sciences and Maharashtra Academy of Sciences. He is a recipient of several awards. Few awards includes ICS Acharya PC Ray Endowment Award, ICS Dr. P.K. Bose Memorial Award, CRSI Silver Medal Award, Lifetime Achievement Award from STRAPS, SMC, SRR, etc. So the list is really big. He received several fellowships. Few of them are like British Medical Council Research Council Fellowship, British Cancer Research Campaign Fellowship. He is a visiting professor at various universities and institutes in China, Japan, UK, France, Germany, Poland, USA. I think I should say worldwide, and IAEA expert mission to Namibia. So his research areas includes photochemistry, free radical chemistry, time-resolved fluorescence spectroscopy, surface science, and nanotechnology. So far, he has published 423 journal publications in his account till date, and there are maybe few more in near future. So I request Dr. Tulsi to take up the lead for the next session.
Thank you for the invitation. Screen is blank. Chittaranjan? Okay, you are there. Okay, that's okay. I thank all the organizers, particularly Kasturi, for inviting me to chair this special session, special award function. And I must mention that it is an all-women award. All 4 recipients are women, and that's a great thing. I will not spare more time about this, and I start straight away on the first lecture by Dr. Sharmila Banerjee, whom I had to mentor just before and immediately after her entry into Bhabha Atomic Research Center, but then she shone on her own merit, and right now she is an outstanding scientist by grade. She heads the Radiation Medicine Center, and she is also a professor of nuclear medicine and project director of Radiological Research Unit of famous ACTREC of Tata Memorial Center in Kharghar. She is also a professor at the Homi Bhabha National Institute, Department of Atomic Energy. She is fellow of Indian College of Nuclear Medicine and chairman of the Radiopharmaceutical Committee of Diagnostic and Therapeutic Radiopharmaceuticals. She is an IAEA expert in radiopharmaceuticals, and in that capacity she had to visit many countries, and one of the best awards she has got is very prestigious, is the Department of Atomic Energy Homi Bhabha Award in 2010. She has more than 250 publications and review articles, and her talk, as you know, all of you know, is evolution of radioactivity in nuclear medicine, an unending human quest for betterment of life. I invite Sharmila to deliver a lecture. What happened, Kasturi and Chittaranjan?
No, I'm there.
Hello, am I audible?
Yes,
Yes.
perfectly.
Yeah, I'll share my screen. Yeah. Screen to share.
We are running nearly 40 minutes late, so I'll request all the speakers to restrict the time as scheduled.
So my slides are visible, right?
Yes.
Yeah. So good evening to all of you. At the outset, I would like to profusely thank the Indian Chemical Society and the joint organizers of this meeting for giving me the opportunity to deliver the Marie Curie Memorial Award lecture. I feel indeed honored and humble in equal measure for this. I also thank Professor Tulsi Mukherjee for his kind and generous introduction. This special session is associated
Professor Sharmila, you are not audible anymore.
I think she got disconnected.
That was muted, maybe.
No, she is still connected.
She is got hanged, the computer looks like.
Supposed to be.
She is actually in US.
Oh.
Oh, that's the issue.
Yeah. Yeah. She is in US. Yeah.
We'll wait, she'll get reconnected.
I think she's not even understanding that she's, not. Yeah. Now she's connecting again. Yeah.
Professor Kasturi, can you please text her?
Looks like Sharmila is not able to connect.
Can we go to the next speaker? Good afternoon, Mr. Chairman.
Yeah, I have to be authorized for that. I have no problem.
Because I'm sitting in IIT Jammu where there's no current in the rest of the city. So I'm a little nervous. I might also have a similar problem.
Actually, her computer, I called her, her computer got totally blackout. She's trying to join. The computer gone blackout, her. That she told me.
He could join through the mobile also.
But the slides are in computer, no?
He cannot send it to you. So what we should do?
No, through mobile.
She's coming. She's coming. She's telling me wait for 1 minute.
Okay.
It always happens, So
no problem.
She's calling me again. Let me. Hello. Hello. So what to do?
Just 1 minute, you please.
Yeah. We are waiting for you. Can you connect by mobile?
না মোবাইলে লেকচার কানেক্ট করতে পারবে না
No, she can through mobile she can send a PPT.
No, yeah, okay. Yeah, we are waiting. Don't get nervous. We are waiting. Yeah.
I'm in US.
I know.
So, I don't know whether there is some, all the while it was working. I attended all the lectures in fact.
I know, I have seen you. Yeah. So, yeah. Just
visit me for another 2-3 minutes.
Yeah, definitely. Yeah, no problem.
মিনওয়াইল বানিদি প্রণাম তুলসী বলছি আপনি আছেন এইমাত্র তো ছিলেন
কে বলছো
আমি তুলসী বলছি
তুলসী ও আচ্ছা হ্যাঁ খুব ভালো তোমাকে দেখলাম
বানিদির কম্পিউটার তো আপনার নাম দেখাচ্ছে
একটা কম্পিউটারে দুজনই আছি একটা কম্পিউটারে দুজনে আর তোমার মিসেস তো
হ্যাঁ ও আছে লাইনে অ্যাকচুয়ালি
না ও বললো যে খুব ভালো লেগেছে ওর নামটা হচ্ছে
শিরূপা।
শিরূপা, হ্যাঁ শিরূপা বলাতে, শিরূপা মুখোপাধ্যায়, তখন হঠাৎ করে মুখোপাধ্যায় বলাতে বুঝলাম যে এই তুলসীর স্ত্রী আর কি। যাই হোক, অনেকদিন পরে একটু কথাও শুনলাম, একটু চেহারাও দেখলাম।
হ্যাঁ, তা আপনাকেও প্রণাম জানাচ্ছি
আচ্ছা,
দুজনেই।
আমাদের আন্তরিক আশীর্বাদ নিও তোমরা দুজনই। আমি তো মানে আরেকটা বই নিয়ে খুব ব্যস্ত ছিলাম বহুদিন, তো মাত্র কয়েকদিন আগে পাঠালাম ওটা। ওই আমাদের দুজনেই লেখা স্টিরিওকেমিস্ট্রির উপর বই।
আনমিউট করে বলো।
ও আনমিউট তো করা আছে
না, আপনার না।
ও আচ্ছা, না আমি বলছি আমরা
প্রণাম জানাচ্ছি।
হ্যাঁ, আমাদের স্টিরিওকেমিস্ট্রির উপর একটা বই স্প্রিঙ্গার লন্ডন থেকে বার করছে।
ভেরি গুড।
নেক্সট ফেব্রুয়ারি মাসেই বেরোবে। আজকে একটা চিঠি পেলাম, বলছে যে মেটা ডেটা পাঠাও। মেটা ডেটা তোমরা করবে, আমি কেন করবো? আগের বই তো এরকম বলেনি। মেটা ডেটা মানে বই সম্বন্ধে সমস্ত ডেটা দেওয়া, দিয়ে অ্যাডভার্টাইজ করা ইয়েতে, গুগলে। হ্যাঁ, তুলসীর সঙ্গে কথা বললাম, তো তোমার সঙ্গে কথা বলতে চাইছিলাম।
হ্যাঁ, আমি জল খেতে গেছিলাম।
হ্যাঁ, এখন আসলে কথা বলতে পারো।
কোথায়?
না বললে কথা বলবে।
আরে বানিদি, আপনাকে তো প্রণাম জানালাম, খুব ভালো লেকচার শুনলাম, অনেক কবিতা।
থ্যাংক ইউ ভেরি মাচ।
কবিতার অনেক ইমোশনের ব্যাপার নেই
আছে তো। বানিদি যেটা ভুলে গেছেন, আমরা সবাই অসীমাদিকে মাস্টার বলতাম আড়ালে।
হ্যাঁ, মাস্টার জানি তো।
আর ক্লাসে যখন রোল কল করতেন, কেউ ইয়েস ম্যাডাম বলতো না, ইয়েস স্যার বলতো।
আর তুলসী তোমার যে মাস্টারটা ঢুকেছিল না, সেটা জুলিও এখন বলে মাস্টার। ওরা মামি বলে না, কিছু বলে না, মাস্টার বলে।
আমি জানি
কি যে নাম তোমরা আবিষ্কার করেছো।
আমরা নয়, আমাদের পূর্বসূরীরা।
না ওদেরও সিনিয়ররা।
তাই?
আরে আমি যখন রিসার্চ করি তখনই তো কেউ মাস্টার বলতো।
হ্যাঁ, প্রথম থেকে
আমি অসীমা দিয়ে বলতাম।
স্যার বলতো সবাই।
অসীমা থেকে আমি অসীমা দিয়ে বলছি।
না অনেকে স্যার বলতো।
না, স্যার বলতো অনেকে, কিন্তু তুমি তো অসীমা দিয়ে বলতো।
আমি অসীমা দিয়ে বলতাম।
আমিও সামনে থেকে অসীমা দিয়ে বলেছি, কিন্তু আড়ালে ওই লোকে মাস্টার বলতো।
হ্যাঁ, আড়ালে বললেও সে আলাদা। না, অনেকে সামনেই বলতো গিয়ে।
কস্তুরী কি অবস্থা?
Yeah, she's trying to join. I just called again. She's trying to join from another computer. So she wants another 1 minute time. I think we have to be a little patient because she's far away and she, yeah. What to do? You know, it happens. These glitches. It happens.
যন্ত্রের উপর তো কোনো রকম কন্ট্রোল নেই।
No control. So you have to have a little patience. I think. Yeah, we are running out of time a little late.
লিটল না, আমরা এখন অনেক লেট।
I don't know how we actually it's just very packed program, and that's why.
বন্ধ হয়ে গেল, লোডশেডিং। হ্যাঁ, তাই তো। এখন কি লোডশেডিং নাকি?
অশোকের খুব শীত লেগেছে মনে হচ্ছে, গলায় মাফলার দিয়ে একবার।
হ্যাঁ, না আমারও তো
ভীষণ শীত। সত্যি শীত মানে এবার শীত একটু বেশি পড়েছে না?
মানে শীত
আমাদের ভীষণ শীত করছে।
আমার মাথায় বা কানে গলায় ঠান্ডা লাগলে কাশিটা বেড়ে যাবে।
আমি ভাবছি যে একটু শীত হলে।
Yes, I think Sharmila Banerjee has joined again. Yes. Yeah, Sharmila Banerjee joined again. Yeah.
হ্যাঁ, এটা শর্মিলা।
Very good.
Yeah. So yeah. Yes.
He's present.
এতক্ষণ পরে আসছে।
বিচ্ছি লাগে না, বন্ধ হয়ে গেলে মাঝখানে
সেই ছন্দপতন হয়, তাছাড়া টাইম যায়।
যে বলে তার খারাপ লাগে তো।
হ্যাঁ,
খাচ্ছে হয়ে যায়।
কি হচ্ছে দেখো।
Hello, I'm back. Am I audible?
Yes, perfectly. Go ahead.
Yeah, and my slides are also visible, right?
Yes.
Yeah. I'm sorry for the technical glitch, but I had to change my laptop. I think from the beginning of the meeting, I've logged in. I have not faced this problem. Anyway, I'll go to immediately to the second slide. As I said that the outline of my talk will be my homage to Professor Ashima Chatterjee and Marie Curie, and that will be followed by an overview of the evolution of the nuclear medicine program, particularly in the Indian scenario. Now, Professor Mrs. Ashima Chatterjee, she was an outstanding chemist. Many speakers before me have spoken in details about her, so I will not be venturing into it. She was an extraordinary teacher and academician, and she has spent her lifelong research in finding new biologically and pharmacologically active compounds from plant sources. I was extremely fortunate to have her as a teacher in our postgraduate classes, and so I have seen her as an extraordinary teacher, and she has contributed in other branches of organic chemistry. In other words, she was an institution by herself. She left a legacy and a school of organic chemists. Coming to Marie Sklodowska-Curie, she was an icon in the world of modern science with 2 Nobel Prizes in 2 branches of science, physics and chemistry. Her early life and education consisted of, she was actually born in a very poor family in socially and politically unstable Poland. Her parents were teachers. She worked hard as a governess and tutor to support her studies. And at that time in Warsaw, there was very less opportunity for women for higher studies, so she had to migrate to France. And in France, she was fortunate to have the great physicist like Gabriel Lippmann, who was a future Nobel laureate, to be her teacher, and even the great mathematician Henry Poincare. In 1890s, this was an interesting time in France where interdisciplinary cross-pollination of path-breaking ideas was taking place, and she was fortunate to be studying in France in the Sorbonne University during that time. I will not read out from this slide, but I would like to mention that during the course of her research, she found that an ore containing uranium was more radioactive than could be accounted for by its uranium content itself. She was certain that this was due to the presence of some other radioactive element, and thus her research led to the discovery of 2 other radioactive elements, that is polonium and radium. What is lesser known about her is that she was the first to demonstrate the use of radioactivity for medical purpose. During World War I, she promoted the use of X-rays. She introduced radiological cars to take X-rays of wounded soldiers. In the last 2 years of the war, more than 1 million soldiers were X-rayed to locate the exact position of bullets during surgery, and many lives were saved. She personally trained doctors and nurses in this new radiological technique, and she was the first to use radioisotopes for the treatment of neoplasms. This was a landmark event, and thus it laid the foundation of using radiation for medical purpose. Marie Curie's relentless resolve and insatiable curiosity made her an icon in the world of modern science. Her work was extremely physically demanding. One can just imagine that she has isolated 1/10 gram of pure radium from tons of pitchblende. And at that time, mind you, the nature of radioactivity, the impact of radioactivity was not known. So how physically challenging that work was, one can really imagine. In fact, till date, her manuscripts, her papers are all still radioactive, and so much so that if one has to access them, they need a special permission, a special waiver, and they have to wear protective gears. So in other words, I can say that in the real sense, as well as in the literal sense, as well as in the metaphoric sense, one cannot touch her achievements. She championed the use of radiation in medicine, and she fundamentally changed our understanding of radioactivity. So that was Marie Curie. Now coming to our program, now I will come to our group's work on the application of radiation in the field of medicine, particularly that of cancer. Before I go to that, I must mention about another visionary, Dr. Homi Jahangir Bhabha, who is considered as the father of the Indian national nuclear program. I can do no better than quoting what Sir John Cockcroft has said about Dr. Bhabha. He said, I quote, human progress has always depended on the achievements of a few individuals of outstanding ability and creativeness. Homi Bhabha was one of them. Now, this shows the different milestones of the nuclear energy program in India. And what I would like to highlight in this is, as early as in 1963, Dr. Bhabha's vision of the immense potential of the use of radioisotopes and radiation for the human healthcare application was envisaged, and that gave birth to the Radiation Medicine Center in 1963. Now, in the first appointment letter, that Dr. Bhabha had given to the first director of Radiation Medicine Center, Dr. G.G. Boy, he writes that, I quote from that letter, that we are interested in promoting the use of isotopes in medicine for research, clinical investigation and therapy, and in assisting the advance of medicine generally by providing this additional tool for both long-range and short-range medical research. So what I would like to say here is the application of nuclear energy for human healthcare application is one of the core visions of Dr. Homi Bhabha, and it was not an offshoot of the actual nuclear energy program. So in fact, I would like to say that India is fortunate to have today the Dhruva research reactor, which produces large number of medically important radioisotopes which are used in healthcare applications, particularly in cancer, and it is able to cater to the significant demand in the country. So India had an early start with the commissioning of the Apsara reactor in 1956, followed by the Dhruva reactor in the 80s, and India is significantly in a very good position to meet the radioisotope demand of the country. Now I come to the evolution of nuclear medicine. Here I would like to mention that what is nuclear medicine? It is a medical specialty which utilizes the nuclear emission properties of radionuclides in the diagnosis and in the therapy of various physiological and metabolic disorders, mainly cancer. These radionuclides are tagged to pharmacologically active molecules, and the radiolabeled products are called the radiopharmaceuticals. Nuclear medicine has evolved over the years, starting from the use of the technique which is known as radioimmunoassay, abbreviated as RIA, which is actually the estimation of very low levels of drugs, metabolites, and hormones in the blood, to the present day target-specific radiodiagnosis and radiotherapy. Now, there are several challenges because this field is a multidisciplinary field, and where organic chemistry plays a very important role. And here I would like to highlight that development of new radiopharmaceuticals and other drug development programs requires a multidisciplinary approach, and it is very always challenging for various reasons, such as there are different pharmaceutical components have to be designed, different radioisotopes have to be envisaged, the affinity for chelation of the radioisotopes with the organic moiety has to be considered, and of course the target specificity, which is last but not the least, has to be of prime importance. So there are several challenges in designing of new agents. Our early efforts was to synthesize ligands which are here I would like to mention that cancer is not a single disease with a single cause. For cancer management, early diagnosis is very important. There are radiopharmaceuticals which image and imaging techniques for in nuclear medicine, which helps in the detection of cancer. These are called the diagnostic agents. Similarly, there are agents where the radioisotope used is a particulate emitter, and those are the agents which are used for therapy purpose, that is for actually killing the cancer cells, and they are called the therapeutic radiopharmaceuticals, which are used for the treatment of cancer. Our group has been working in both these areas, and I will try to show you a few examples of the diagnostic radiopharmaceuticals and then move on to the therapeutic ones. Now, basically, the diagnostic radiopharmaceuticals are based on that of technetium, and our early efforts was the synthesis of these ligands, which are simple ligands, which are very target specific, and on labeling with technetium, they had the localization power in the site specificity. They had site specificity, and they were used for the diagnosis of different kind of cancers as well as different kind of metabolic disorders. Slowly, we moved on to the more challenging ones. This is technetium labeled MeB and then tetraphosphine. Now, there was a shift of focus at this point of time. Mind you, technetium is a gamma emitter, and it's used for actually the SPECT imaging technique, that is single photon emission computed tomography. However, the focus shifted to that of PET, that is positron emission tomography, and the isotope used was either fluorine-18 or gallium-68, and therefore, but many of the centers do not have an access to the cyclotron, and therefore they had to bank on the technetium radio tracers, and therefore the technetium labeling had to evolve over a period of time. That is, there were new trends which had to be introduced, and those new trends were introduced making use of the versatility of technetium chemistry. Actually, technetium has a varied oxidation state from -1 to +7, and it's a chemist's delight. And so gradually the technetium was used for the chemistry to improve the labeling strategies, and in the process several cores what we call here are the preformed synthons which were used. They could be isolated as individual species, and these cores were used, and amongst these cores there were several cores like technetium tricarbonyl, technetium nitrido, PNP, so on and so forth. And I have got specific examples, and a host of compounds have been prepared, complexes have been prepared using these different cores, but I have got some specific examples which I'll show you. The first example is the use of the technetium tricarbonyl core. Here I have shown you the radio labeling of a particular ligand, that is mesonidazole. Mesonidazole is a particular ligand which is used for imaging of hypoxia after labeling with technetium. Now, the gold standard for imaging hypoxia is fluorine-18 labeled mesonidazole, and here I show you the technetium tricarbonyl core for labeling with mesonidazole for using it as a diagnostic agent for imaging hypoxia. Similarly, the use of the technetium nitrido core. This nitrido core is another preformed core which is used for dimerizing of two tripeptide ligands, which are RGD, that is, it's an acronym for arginine, glutamic acid, and D-aspartic acid. And this is used for the imaging of melanoma tumors, which express integrin receptors alpha V, beta 3 on the tumor surfaces. This is the example of the technetium nitrido PNP core, which is used as a metal fragment again. And here I show you the complex which is formed by labeling folic acid cysteine as a ligand, and the technetium folic acid cysteine radio tracer is used for imaging of the myocardial perfusion. This is the another approach using the 4+N mixed ligand complex of technetium. Here we have a +4 ligand tetradentate ligand array and a monodentate isocyanide ligand.
Shamila, your PPTs are not coming.
Sorry?
Your PPTs are not coming, only you are visible.
Oh, is it?
It's coming.
It is not your fault,
coming.
madam.
You have to pin. You have to pin down.
It
is coming.
It is coming.
You make
We
it.
are seeing.
Yeah, you have to. Professor
No,
Mukherjee.
no. Professor, due to Professor Dhara, he tried to present something.
After that, only
overridden
problem
by-
came.
No, but it is coming to my computer. I can see the
No, it
whole
is not
slide.
coming in the console.
I have not
so
touched my
everybody
computer.
cannot see it.
No, no, slides are not coming in my computer also.
It is
No,
not
No,
coming
you
in the
just
console.
unpin. You
It
unpin
is
it. No,
coming in my computer.
No, no,
my
she is
PC
unpin
delivered.
already.
you
She
just
is unpin
unpin
already.
it. You know there is a pin. You just unpin it. It will come.
Go to slideshow.
No, ma'am, she is not unpinned.
You just unpin it. It will come because it is coming to my computer perfectly. I have unpinned it and it is coming. Yeah.
Should I continue?
Yes,
Yeah.
you continue.
Yes.
Unpin ko
Continue.
chahe.
Yeah.
Yes, please, Professor.
Yeah.
Sir.
Okay. So this is the 4+1 mixed ligand complex of 99M technetium. Then coming to the the latest development in 99M technetium labeling is the application of the click chemistry route. Incidentally, the copper catalyzed 2+3 cycloaddition reaction, which is known as the click reaction, was first proposed by Barry Sharpless, and as you all know that he was awarded the Nobel Prize in Chemistry in the year 2001 for this. The click reaction has been used for labeling of a variety of biological vectors, and here I show the application in labeling of two molecules, that is progesterone as well as testosterone, for targeting some specific cancers. So this is the application of the click route for the labeling of biological vectors like progesterone and testosterone. And now, as you know that Parkinson's disease is an age-related neurodegenerative disorder, it poses a considerable challenge for its detection, and very few compounds, that is because very few compounds can cross the blood-brain barrier. So it poses a considerable challenge to physicians, and therefore its diagnosis becomes a very important thing for the treatment part of it. And here we show you a particular ligand, TRODAT, and this was labeled with 99M technetium, and it was used in Parkinson's patient, where you see the image of a normal volunteer's brain with a normal uptake. This is supposed to be the normal uptake, followed by patient about the imaging studies in a patient where you see a very diffused uptake of the radio tracer. So this is one of the examples where our work has been clinically translated into patients. Now coming to the second example, this is technetium Hynic TOC, what we call. Hynic is an acronym for hydroxynicotinamide, and TOC is tyrosine octreotide, which is an octapeptide. And this work has been carried out by one of my students, and it's a very challenging work actually. This peptide has been synthesized, and it has been labeled with this Hynic, what they call bifunctional chelator. And this technetium labeled product has been developed into the form of a kit, which is marketed by our marketing authorities, that is BRIT, Board of Radiation and Isotope Technology, and it is used as a diagnostic agent for imaging of neuroendocrine cancer. As you can see that neuroendocrine cancer patients have been imaged with this particular product. Coming to the development of tetraphosphine. Tetraphosphine is this molecule. The synthesis is extremely challenging, and this also has been formulated in the form of a kit. After the synthesis was achieved, it has been formulated in the form of a kit. It has got its regulatory approval, and it is used for myocardial perfusion studies. It is injected into a human patient for myocardial perfusion studies. So then I will shift, having talked about technetium 99M as a SPECT radio tracer, I will shift to gallium-68, which is a PET radio tracer. There are several advantages of gallium because it is available in, there are many centers, nuclear medicine centers, which do not have an access to the medical cyclotron. Medical cyclotron means you can use fluorine-18 isotopes, whereas they have an access to the portable germanium gallium generators. So that gives an advantage for the use of 68 gallium as a radio tracer, PET radio tracer. Then it is a PET isotope, and PET images are always better than SPECT images in terms of their resolution and their sensitivity. So the gallium chemistry was developed to a large extent, and the agents that were developed by us was, here I show that there were several agents, gallium dotatate, dotaTOC, NOC, and as you can see alongside I have written the applications. That means starting from neuroendocrine cancer to prostate cancer, then bacterial infection imaging to breast cancer, and finally the last agent, that is BPAMD, is used for bone imaging in cancer metastasis. And here are some of the representative images that I have shown. Now, having talked about diagnostic radiopharmaceuticals, I go to targeted radionuclide therapy, that is that therapy using targeted radiation. This slide pictorially shows the energy of the radiation up to what level it can penetrate. For example, alpha radiation with 5.3 MeV energy range can penetrate up to 0.1 millimeter in tissue, whereas beta with a range of 1.7 MeV can penetrate only 10 millimeter, can penetrate 10 millimeters. So depending upon the penetration power of the radiation, we can envisage agents for treating different types of cancer. And as you can see that A is in terms of the cell nucleus dimension, B is a single cell that is 0.1 millimeter, C is few cells, and D is about 100 cells. So depending upon this, we can choose a radioisotope which can be used for specific treatment of cancers. Now, at this point of time, radionuclide therapy has a tremendous growth. It is an emerging modality, and it has a tremendous growth. And the thing is, here we have to think about isotopes other than that of iodine 131 and 32 phosphorus, which were the traditionally used radioisotopes. And at that point of time, one has to identify some other isotopes in terms of their better logistics and better nuclear properties. And that was the time when the potential of lutetium-177 was unraveled. Now coming to one very promising area of therapy, that is PRRT, that is peptide receptor radionuclide therapy. We started our work using the peptide vector lanreotide. That is, we synthesized lanreotide, which is an octapeptide with this particular sequence, and then we prepared the lutetium labeled derivative of lanreotide DOTA, and we tested its efficacy for targeting peptide receptors overexpressed in some neuroendocrine cancers. And slowly we switched over to the better agent, that is DOTA-TATE. Again, this is an acronym. TATE is tyrosine octreotide, and it is a better vector in terms of receptor targeting. And incidentally, this radiopharmaceutical was developed in BRC, and simultaneously at this point of time, we were able to optimize the production logistics of lutetium-177 from the Dhruva reactor, and that itself has got its regulatory approval. Its production, the processing, and its purification to the clinical grade was approved by the regulatory authorities. And this particular radiochemical precursor was of clinical grade, was used for labeling of a host of biological vectors. And here I show you the labeling of lutetium DOTA-TATE. This is one of the example. This is the example where a lutetium labeled product has been clinically translated into patient, and this happens to be the first radiopharmaceutical which is approved in India for use in neuroendocrine cancer patients, for treatment of neuroendocrine cancer patients. And at present, more than 20 centers in India are using this agent, and more than 10,000 patients have been treated, if not more, with this peptide labeled radiopharmaceutical for the treatment of various types of neuroendocrine cancer. Now, coming to the story of development of lutetium labeled phosphonates, we have been working on
Professor Banerjee, you please unmute yourself. You got muted. Professor Sharmila Banerjee, you please unmute.
So all this while you were not able to hear me?
No, just one slide. Just 1 minute.
Okay,
just
okay.
one. For a few seconds.
Actually.
Yeah, it's fine. Yeah.
So here I talked about the phosphonates that we have synthesized. We have synthesized several phosphonates, but out of that, one is an acyclic and the other is a cyclic phosphonate, which we have actually labeled with lutetium, and we have clinically translated into patients. So these are the typical examples of patient images acquired in patients who are suffering from skeletal bone pain, skeletal metastatic cancer. Now, coming to this particular example, this is a concept which is actually a very new concept which is coming up in nuclear medicine. This is called theranosis, where theranosis, we can have it's a new concept in nuclear medicine where a matched pair of radionuclides, that is a diagnostic radioisotope and a therapeutic radioisotope, is used in the cancer management. And this provides the opportunity of personalizing cancer treatment. And one such example is the success story of 68 gallium PSMA. PSMA stands for prostate specific membrane antigen. So 68 gallium PSMA 11 is used for this. 11 and 617 denotes the difference in the chelating groups. Otherwise, the molecule is the same. And 68 gallium PSMA 11 has been actually used for the diagnosis of prostate cancer, and lutetium labeled PSMA 617 is actually used for the treatment of prostate cancer. So these two agents have been developed and they have got the regulatory approvals in 2017, and thereafter it is being used in several centers in India. And BRC was the first one, our group was the first one to actually develop these two products, and they are being widely used in the treatment of prostate cancer management. Here you see some representative examples. As I said, PET is very sensitive, and there you see the PET images acquired in a prostate cancer patient, and we carry out the therapy using the therapeutic isotope, that is lutetium-177. Coming to radioimmunotherapy with 177 lutetium. Now, lutetium-177 is a medium energy transmitter and with a imageable gamma photon. So what I would like to say is, in this particular treatment, that is in radioimmunotherapy, one needs an isotope which has got a sufficient long life, because the monoclonal antibody, which is used as a biological vector, has got a very long residence time in the blood. So if it is labeled with a short-lived radioisotope, then it decays off even before it reaches the target site. Therefore, radioimmunotherapy with a long-lived isotope, and that too with lutetium, is always a very desirable thing, because lutetium has got ideal theranostic properties. That means the same isotope can be used for imaging of the disease, imaging of the particular cancer, as well as for the therapy of the cancer. That is, the half-life of lutetium is quite high. And utilizing this, two products have been developed. One is lutetium labeled rituximab for treatment of non-Hodgkin's lymphoma, and the other one is lutetium labeled trastuzumab for Herceptin positive receptor expression in breast cancer. And here I show you the typical images acquired in a patient with breast cancer using lutetium trastuzumab. These are the agents which are now being used in India for the treatment of non-Hodgkin's lymphoma as well as for treatment of breast cancer. Now here I show you some examples of the wide variety of molecules that we have labeled with lutetium. That is, we have got an estradiol conjugate, and these are promising candidates which are worth evaluation for the next stage for clinical translation, but they are in the preliminary stages at this moment with initial promises. One is the estradiol conjugate, one is for targeted therapy of hypoxic tumors, and then targeted therapy of breast cancer. Coming to one of the recent developments, we have made 177 lutetium labeled nanoparticles as drug delivery system. This is an example where a carbon nanoparticle is used as a carrier for receptor targeting. Here, RGD peptides and lutetium DOTA have been incorporated on the surface of carbon nanosphere for targeting integrin receptors, which are overexpressed in melanoma tumors. Now coming to another radioisotope, a therapeutic radioisotope, 188 rhenium. Here, 188 rhenium is a very hard beta emitter with an energy of beta max of 2.12 MeV, and therefore it is very suitable for treatment of large sized tumors. Mainly it is used for the treatment of liver cancer, which happens to be the largest organ in our body. So for treatment of liver cancers, rhenium 188 is an ideal isotope. And just as you know that I have talked about the technetium nitridocore, rhenium and technetium, they belong to the same group of the periodic table. So rhenium nitrido complexes are also similarly formed as I have shown you examples of the technetium nitrido complex. And here we have labeled this particular ligand, that is diethyl dithiocarbamate with rhenium nitridophore. It shows the concept of a dimeric ligand and dimerization of the same ligand using the rhenium nitridophore. And this particular complex has been actually evaluated in patients, and this is after we have got the regulatory approval, and this is used in the treatment of liver cancer. Here you see the uptakes in the liver, and this is it proves to be of considerable promise in the treatment of liver cancer. Now coming to the last but not the least of the therapeutic isotopes, yttrium-90. Now yttrium-90 is an isotope which has to be imported at present, which had to be imported at present at a very prohibitive cost. Again, yttrium-90 has got a half-life of 2.28 MeV. That is, it's a hard beta emitter, and apart from all its other applications, yttrium proves to be a very good isotope again for liver cancer. Now in BRC, this has been made possible. The isolation of yttrium from the high-level liquid waste that we get. There's a lot of nuclear waste that is generated. And for yttrium, the parent isotope is strontium-90. Strontium-90 is a fission product which is present in high-level liquid nuclear waste in large quantity. And this isotope strontium-90 was separated from the high-level liquid waste. And mind you, it is a very challenging work because huge amount of radioactivity has to be handled for this. And it was purified to the clinical grade product. And this product, yttrium acetate, has also got its regulatory approval. And it has been used in the labeling of products which are used for treatment of neuroendocrine cancers and non-Hodgkin's lymphoma. I will not show you the examples, but there are two products which have been developed in recent times with yttrium as the radioisotope. Now here I have tried to show the products which have been clinically translated. Here on this side, this list is not a comprehensive list, but some of the very important ones have been listed here. Amongst the diagnostic products you see from technetium and gallium, and in the therapeutic products we have got mainly lutetium, then rhenium and yttrium. So as I said, this list is not complete. There are other things, but these are the most important ones. Now to conclude, I would like to say that I hope that I have been able to give you, in spite of all the technical hitches, I'm sorry for that, but I hope I have been able to give you a overview of the evolution of nuclear medicine and its particularly in reference to the Indian scenario, how discovery of radioactivity has opened new vistas for the betterment of human lives. It has given birth to nuclear medicine. Nuclear medicine is an evolving modality with the introduction of new radioisotopes, new targeting vectors, and the introduction of hybrid imaging techniques. Now we talk about not only SPECT and PET, we talk about SPECT CT, PET CT, PET MRI. So there is a hybrid technique, imaging techniques are being introduced, and this has added new dimensions to the use of nuclear medicine for medical purpose. And of course, I tried to show you some of the examples where how vital the role of chemistry is in the development of nuclear medicine or the application of radiomedicine for betterment of human lives. Now, to commemorate the Marie Curie's second Nobel Prize in Chemistry in 1811, 2011 was celebrated as in 1911, 211 was celebrated as the International Year of Chemistry, and that shows the importance of chemistry in the development of radiation medicine. So, ladies and gentlemen, it was indeed a privilege for me to be able to speak in front of this august gathering. Thank you very much.
Sorry. Thanks, Sharmila, for an excellent talk, of course, with interruptions.
Yeah. Any questions I would like to, I can address a few questions.
Yeah, I was a British, DNA structural chemist. And this lecture will be given by Professor Anju Chadha. Title is Catalyst for Organic Reaction from Whole Cells to Enzyme. Anju Chadha is very well known in this area, and she is also in Jammu, IIT Jammu. She is an expert in chemical biology, organic synthesis and enzyme mechanisms, green chemistry, and biodiesel chirotechnology. She has more than 120 research publications. Anju ji, all yours. Yes, Professor Chadha, you can take over.
Yes, thank you very much. I'm now presenting my screen and can you hear me? Hello?
Yes.
You can hear me, right?
Mm-hmm.
Kasturi, how do I unpin? Kasturi, are you there?
Yeah.
How do I unpin? You're talking about unpin.
You go to the chat, right hand side, there are persons, and you see the presentation, then there you have to unpin.
No, there is nothing. In call messages only.
No, now there is no presentation, but who is present?
No, yeah, that's correct. When presentation starts, you can go to the speaker's box.
That's
where she's
presentation.
presenting and presentation. There is a pin symbol. Just click that.
Let's click that. Yeah.
Can you see my screen?
Yeah.
Yes.
Okay. And you can hear me, right?
Yes.
Correct.
So at the outset, I would like to pay my respect and deep tribute to Prafullo Chandra Ray, whom I consider as one of the best and role model chemists of our country. Not just a chemist, not just the inorganic chemist, but also an entrepreneur. And in this day and age when translational chemistry or science is very important, I think his enterprise also lives along with his chemistry. So my salutations to Prafullo Chandra Ray. And of course, Asima Chatterjee, under whom we have all seen these exemplary reactions, phytochemicals, organic chemistry reactions, which people have been talking about. My salutations to her. And the unsung hero, Rosalind Franklin, who interfaced again with biochemistry and chemistry. So here we have three stalwarts, inorganic, organic, and biochemistry, all coming together and giving us the kind of chemistry that we have probably never seen before. I also am an interdisciplinary chemist, trying to do my best in various kinds of fields, most importantly in the field of biocatalysis. And my title is Harnessing Biocatalysts for Organic Reactions from Whole Cells to Enzymes. I'm glad some other speakers have already alluded to this, so it won't be entirely new. Just to explain the title, whole cells are entire cells where microbial cells are used for a biotransformation. They all contain enzymes, and we've gone on to purify the enzymes to understand the mechanism. And biocatalysis is today one of the most promising technologies for the sustainable synthesis of molecules for pharmaceutical, biotechnological, and industrial purposes. Now, this is, of course, a little bit of humor, but it's to be taken seriously. Nature is the supreme chemist, and way back in 1981, there was this from an organic chemist's ode which said, "Lord, I fall upon my knees and pray that all my syntheses may no longer be inferior to those conducted by bacteria." Now, synthetic organic chemists, which has impacted every aspect of modern life, has not really taken into this very seriously. But still, their synthesis needs a lot of improvement, efficiency, scalability, and so on and so forth. But they have sort of kept away from this. And I'd like to quote here Casey Nicolau, who's also one of my present-day heroes in organic chemistry. He says it is also important to re-emphasize that organic synthesis has a long way to go before it can be considered competitive with biosynthesis, nature's way of
Plate
making.
घेऊन जाते इमिट होतो ती.
The standards of nature, that is close to 100% yield, little if any waste, and
Mr. Chadha, you please unmute yourself. Professor Chadha, just unmute. It's got muted. You are
now?
Yeah, it's fine now. Yeah.
Yes. So did you miss something? Did you hear what Nikolov said?
No. We did not miss anything. Yeah.
All right. So what are biocatalysts? They are enzymes basically. Now, of course, we all know that RNA also can act as a biocatalyst, and they are the use of biocatalysts is biocatalysis. That is the use of natural substances to effect organic reactions. Since enzymes themselves are made of L-amino acids, you can consider them to be huge organocatalysts if there is no metal, or organometallic catalysts if there is a metal involved. And nature is so wise, undoubtedly, the use of metals is generally those of high natural abundance and low toxicity: iron, copper, zinc, cobalt, manganese, magnesium, or molybdenum. Now, this is really something to remember. There is no man-made catalyst which can beat an enzyme which has a turnover of up to 10⁻⁶ with high selectivity, regioselectivity, stereoselectivity, and chemoselectivity. And also, enzymes function under near neutral pH, normal temperature, pressure, and in aqueous media, fulfilling a large number of conditions of green chemistry. So clearly, it's one of those technologies which can be considered sustainable for the synthesis of a vast number of molecules. Now, if these enzymes are so efficient, then why is it not obvious? Is it not obvious that we should utilize them for organic synthesis? And since 90s, there is a steady increase in the use of enzymes and biocatalysts for the synthesis of various molecules. So it's better late than never. And it's nice to see that a lot of people are today looking at enzymes as the ultimate catalysts. And nature is the best teacher. So we have here enzymes which can do practically every reaction. But for now, we have only 6 classes of enzymes. More recently, we even have enzymes which can affect Diels-Alder reaction and so on and so forth. So oxidoreductases, transferases, hydrolases, lyases, isomerases, and ligases. Now, starting with lipases, we looked at some of the enzyme reactions. And this was when I was in industry. There was this target molecule, which is an intermediate for prill drugs, which are antihypertensive drugs. They could be, since it's just one asymmetric center, you could have R or S. And these are the prill drugs which we use it for. So the retrosynthetic strategies could be enzymatically, you can reduce this prochiral ketone, or you can resolve this racemic hydroxy compound. Here you will get, in asymmetric reduction, you will get 100% quantitative yield theoretically, and in racemic, you will get 50% of each enantiomer. And we used lipase and showed that this could be done effectively. And it's very gratifying that this is today a textbook material. Nobody wants to now use an acid, make an ester, and then try and separate diastereomers. They can simply use the lipase. This was way back. We also tried, this was also a nice little experiment, which I did as a Humboldt fellow way back in Germany. You have the tertiary butyl oxirane, and you can open this as a chlorohydrin, resolve this, close it back, and you can get all kinds of reagents, which are alkyl zinc reagents. They can add to aldehydes to give you another range of molecules. Now, interestingly, that was about resolution. But if you have the prochiral ketone, you can use enzymes from different sources. If you use the carrot cells from tissue culture, which people generally throw off, which I said I will use instead, and if you have this Candida yeast, you can see that you get 2 different isomers. So this is happening because in these 2 enzyme systems or biosystems, 2 different enzyme biosynthetic pathways get kicked up. So that was very nice, because then we could make a whole lot of standards for ourselves and we need not order them. And having done that, I chanced upon this paper where they actually use the racemic and get quantitatively only one. It's not a resolution. So it's called a deracemization. And if you need only one enantiomer, what you can do is simply deracemize. So we tried that with this candida, and lo and behold, we've got a range of over 250 chiral synthons. We have the diols, we have ketoesters, keto acids, amides, heteroaryl aliphatics, and so on and so forth. So we have beta ketoesters, beta hydroxyesters, alpha hydroxyesters, not the keto. This is all due to deracemization. All this has been published over the years, and various students have taken their PhD. But just for the sake of the students, I want to say that this is not hit and trial. There's a lot of interesting chemistry happening in this. And one of the two challenging questions were establishing the absolute configuration of the optically pure products formed, and also establishing the mechanism. In this, of course, it was imperative that we used one optically pure molecule, so that we make the diastereomers, the Mosher acid or Mosher fluoro derivative of the acid, make the diastereomers, take the NMR, and then enzymatically also you can get enough so that you can establish your absolute configuration. So this is the one which has come from the racemic. I should have really turned this around, but I think this is now clear. This one is for the racemic, and this is what we get enzymatically. Could it be RR or RS? And we established that this was S over here. So this is an interesting thing. It feels like you're playing with the jigsaw puzzle, fitting in all the peaks and playing around with it to establish the absolute configuration. Needless to say that this was the best method. We tried various methods, but since this was successful, we stuck to this instead of using Schiff's reagents. Now, the mechanism, of course, was a little bit of a puzzle. If there were two isomers to start with, which there were because it was racemic, then how are we getting only one? So what was happening to the other one? We proposed that this was getting oxidized and then getting reduced, which meant that there was an oxidation and then a reduction, or an enzyme specific for oxidation and then for reduction. So we called it stereoinversion. And this was known in literature when we went back and saw that people have done enough and more work with the cofactors NADPH, where they've shown that the pro-R or pro-S can either attack from the Re or Z phases of the keto. So clearly there was some stereochemistry involved in this, and part of it was studied. There are 4 possibilities here, but of the 4, only 3 enzymes are known which do the stereochemistry as predicted. E4 is yet not known. So this was the background. Okay, so we went ahead, and the proposal was, if we have a deuterium labeled beta hydroxy, we chose to do it with beta hydroxy, then on oxidation we should lose the D, and again it should pick up an H on reduction. So let's see whether that happens. So that would clearly indicate that a keto intermediate is formed, and then finally it would pick up a hydride again, and you would get your product. And if you didn't have a methane proton here which could get knocked off, then you shouldn't get the product. So this is what we tried to prove, and an elegantly done experiment, we confirmed by NMR, by this doublet, that yes, indeed, we were getting the keto intermediate, and this can be formed only if there is oxidation of the racemic starting substrate. And if there is no methane proton, there is no such reaction. So stereoinversion it was. It is also true that this candida likes only these kinds of trans substrates, not the cis ones. Even though they get inside the cell, which we proved, it is only the trans which act as the substrate. So there was something about the active side of these enzymes which was accepting this but not this. In the case of this molecule, which is the ethyl 4-chloro-3-oxybutanate, notice there is no aryl substituent here. And if you grow the cells in glucose or you grow them in glycerol, you get 2 separate isomers. This is wonderful. You don't even have to do anything. You just have to choose the right substrate. Again, you kick a different kind of pathway each time you give a different kind of substrate for growth. And this, of course, was very helpful because this is an intermediate in a drug which is used for as a nutraceutical, L-carnitine. This also was nice. Some of it is patented, some of it was industry driven, and we're grateful to the industries who came forward and saw some sense in what we were doing. In addition, we saw a symmetric reduction of phenyl glyoxols, of primary ketoamides, and it's very interesting how we can land up with so many molecules. But we thought making D amino acids would be good, even L amino acids, because they were very expensive. But Candida doesn't like to do any of those reductions. So we had to make the N-acetyl and then use the same Candida, but it's a hydrolase reaction. So you can get either the N-acetyl D ester or you can get the N-acetyl L acid. Nevertheless, it was important to know how one can approach the problem of getting optically pure amino acids. Now, this is, of course, trying to convince organic chemists that they should integrate the enzymatic steps in their synthesis. And this, with Propargyl derivatives of this hydroxy compound, we did the deracemization and went on to close the ring in a nice paper which is reasonably accepted, and that used the whole cell deracemization and to get the chromino 4,3-bo, the pyrrolidone. This is also very important to know that many people shy away from using these whole cells or enzymes. That is not really a very big effort right now, because what we have been using is what is called resting cells. It's not a continuous fermentation. So you simply grow the cells, sediment them, and resuspend them as a reagent. So they're basically reagents. I would like to call this Candida a deracemizing agent. If you look at the mechanism, you recall that I mentioned oxidation. So then we decided that if it's doing all this, let's just close it here and just let's make it do an oxidation. At that point, people were trying, there were some industries also trying to ask us whether we can get the oxidation to stop to aldehydes and let it not go to acids. And this was possible for us. And we did get to see a lot of those molecules also. So oxidation also helps. It's regio and enantioselective, selective, as we showed in the oxidation of diols. We can also do the oxidation of aromatic primary alcohols to aldehydes. So far, so good. Lots and lots of papers which established that as a versatile biocatalyst. It was time for us to look at some purification and see what are these enzymes and how do they differ with their active sites and at the molecular level that they give us this different kind of stereochemistry. So we started off with the first one, which was a reductase, but this student didn't want to do it from the wild type. She came back to me and said, ma'am, I'm going to try the recombinant one. So recombinant is always one step removed from the wild type. Anyway, she got the pure one and she established that it does take the ketone, and aldehyde is preferred actually. When she tried with the alpha ketoesters, they were not very good, but aldehydes were better. Ketones were the last preferred. So what was going on in whole cells is not necessarily what we pulled out as the enzyme. There are multiple oxidoreductases. And this was zinc dependent, it's dimeric, and we go on to characterize that. All the time, this is acid with what we established as the gold standard in our lab. So it was not doing the alpha ketoesters as well. So we had to revise that, and it's probably an aldoketoreductase. Nevertheless, we did the crystallizations, got the crystals of the pure enzyme, and collaborated with Professor Gautam of Madras University to get this structure. And we've got some interesting insights into the structure of this at 1.86 angstrom resolution. If you look at the holoenzyme and the apoenzyme, you see that we have the holoenzyme has two subunits, and it is NADPH specific and it has a catalytic. These two things are zincs. One is catalytic, one is structural. So what really is going on with the structural zinc? Catalytic zinc, we sort of understand. It helps make the carbonyl a little more reactive by pulling it towards itself, being electronegative. So we still are trying to answer this question by purifying this enzyme further. And again, doing the reactions and seeing what was its, whether it really is the aldoketoreductase, what are its substrates, and trying to characterize it completely. So overall, it looks like it is an aldehyde aldoketo reductase prefers aldehydes to alpha keto esters, and the various substrates are projected here. And we realized also that whole cells behave really very differently from pure enzymes. And just a word of interest over here, if people are interested in these kinds of asymmetric reductions, it's a good idea to use whole cells and not purified enzymes, because whole cells have the whole package of cofactors and one need not add expensive cofactors. And they work really well. Very charming to see some of these very simple reactions work without any effort, or almost no effort. So this is again coming back to the reaction with the point of structural zinc and catalytic zinc. We're trying to answer this question. Zinc has cysteines generally tethered with 4 of them in the alcohol dehydrogenases, but in this catalytic zinc, this need not be so. I wonder why. And we're trying to answer those questions, trying to see the role of structural zinc in these enzymes. Still under study. We know that there are 2 zincs for sure. We've done a whole lot of studies to establish that. And we know that it's NADPH specific, but it's still not very clear that side-directed mutagenesis work will throw more light on this. So, yeah, this is the same thing which I said. We've made these mutants and we still have to get the results of that. Now, that was the one which was supposed to be the R reductase. The S-specific carbonyl reductase also was purified, and we saw that this was better disposed to alpha keto esters, ketones, and then aldehydes. We called it S-red and studied it in great detail and found out what it prefers, what it doesn't, its stereoselectivity. This doesn't contain zinc. Very interesting. It is also recombinant, and it shows different kinetics for different substrates. So enzyme kinetics is really an amazingly complex issue. Even though Michaelis-Menten kinetic model has lived for 100+ years, it explains very little when you're really looking at enzymes and the kinetics. So this is about S-red, and there is some little bit more detail which we've done recently in MM calculations and quantum, because we couldn't get the crystal of this. We're trying to understand from those studies, computational studies, what is it that we know about the active site? The question of why the stereochemistry differs in the 2 is still not very clear. However, the wild type SADH, which a student has recently purified, this is Jelena, whose thesis is still underway. She's just got very good results, and she should be submitting in 6 months or so. She's got it pure. The S-red recombinant is pure, R is pure. And this one is tetrameric, this is tetrameric, but this one is dimeric. Now, potential, all of them have xenobiotic metabolism potential also. So along with cytochrome P450, these enzymes also seem to do xenobiotic metabolism. And if you compare them further, you can see that the reaction with acetophenone, their oligomeric state, the metal, the optimum pH, temperature, stability, cofactor specificity, and enantioselectivity are nicely worked out in this table. And wild type is really, really something else. See the activity with acetophenone, compare these 2. The zinc dependence is there. So CPCR looks more like the wild type, not the S-red. Even though most of the molecules...
Ma'am, we cannot hear you. Is there some problem? Is anybody also...
You cannot hear me?
No, I can hear.
I can also hear. Yeah, we all can.
We can all hear.
Ask her to pin that her screen.
Yeah, it's fine. Yeah, go ahead, Professor Chadha.
So we have managed to compare all these, and it turns out that my gut reaction that we should be working more with the wild type still holds. So I'm not very convinced that even though you can make a lot with the recombinant ones, it's important to understand the enzymes which are already there first. And this is again just a cartoon showing us that you have alpha keto esters, then ketones, then aldehydes for the recombinant CPCR, recombinant S-reds, and the wild type. So you see there are whole lot of substrates which are possible. to make optically active when you just use a simple candida. And we haven't left the candida. Many people ask me, why don't we try other organisms? I think this organism has enough and more. We haven't finished with it as yet, because we have this amine reductase also over here. This we did with whole cells, a very well coated paper. People initially wouldn't believe it, but we get optically pure amines from this with just incubating this molecule to start with and getting an optically pure amine. This was way back. And subsequently, Turner and all in England just grabbed that and published a whole lot, drowning the whole subject, so to speak, of amine reductase. So we were a little slow for various reasons, and now we have the amine reductase, which is pure, but it turns out it's not simple amine reductase. It's an ornithine cyclodeaminase family enzyme. It's recombinant. It's not wild type. See, we were slow also because we tried to do the wild type all the time. Those guys just go ahead with recombinant and make generalizations of all kinds. Anyway, this amine reduction by this enzyme is quite interesting. You can get a reduction, you can get amines, you can also get alkyl amination, which is another very important reaction. We worked out also the mechanism of some of this, even the reductive amination. We have seen different molecules for starting with alpha ketoester and the amine. So really the sky is the limit. Dehydrogenation, oxidation by the enzyme, that also seems to work. What we expect is what we've got. So this is about our work with whole cells to amines. And of course, I wouldn't be fair if I don't mention the work of Frances Arnold. She got a Nobel Prize in Chemistry in 2018. I like this whole business of being completely interdisciplinary. She's actually a chemical engineer who's delved into directed evolution of enzymes and biochemistry, biology of all kinds, chemistry of all kinds, chemical engineering, chemical processing, everything goes on in her lab in Caltech. And she believes that if you're going to change the world, you've got to be fearless, which I guess works very well because she sent out a team to the, I don't know which part of the world, somewhere in one of the poles, to get really thermostable enzymes which could make a carbon-silicon bond. And she has some 66 odd industries with double the number of patents and so and so. And this is what I think Dr. Reddy's vice president, what was his name? Dr. Bandichur also mentioned. This is a famous example of a transaminase which is used in sitagliptin today. They have done away with rhodium as the catalyst. And this engineered transaminase directly converts the ketone to the amine, which is wonderful because the fluctuating cost of rhodium and the compelling atom efficiency of the enzyme process really shows that the enzyme process is the winner. And this has happened because of directed evolution. Merck and Codexis are manufacturing based on the enzymes. So we are already here now looking at enzymes. Another very important example is that of cytochrome P450. As a PhD student, I worked a lot with these enzymes. They are xenobiotic metabolism enzymes, but at that point, I didn't realize that directed evolution would land them into such an important enzyme system for doing such important organic transformations. So there is inherent promiscuity in these enzymes. Why? Because they have a very big substrate range. And they can, basically the philosophy is they want to make any lipophilic molecule into hydrophilic so that the body can throw it out. So there's lots and lots of nice hydroxylation reactions of all kinds of substrates. Now they have done a wonderful job of directed evolution, and now it can do a transfer of a carbene intermediate to an alkene to form a cyclopropane. Carbene and nitrene transfer reactions took off from there, and CH insertion of sulfonyl nitrines to form CN bonds. Carbon insertion into a C-Si bond. So really the sky is the limit when it comes to directed evolution. The paraphernalia required for directed evolution is huge. It's very, right now, cost intensive because they have, all these people have robotic arms and robots in the labs which are doing most of the screening. And, you know, directed evolution, but the word itself means that you crunch the whole process of millions and millions and years of evolution into a time scale which suits you, which is a few generations. In the lab, it means probably a couple of days or weeks. So that is a huge amount of hardware, apparatus, etc., etc. But it's getting there. And today you have look at this. These are natural reactions by cytochrome P450, and these are the reactions of non-natural. So before we used to just do what enzymes we thought could do, and screen them and try and do them. Today, you make the enzyme do what you want it to do. You can design it and you can push it to doing that. And that is a big, big jump. It's a little difficult, but I'm sure in another 10 years, what Nicolaus said, maybe we'll be close to mimicking nature's efficiency in doing some of the organic transformations. And also, these are environmentally benign relatively. So I think that is really the answer to a lot of the synthetic organic chemistry black marks which they have gained over the years. Eventually, we will get there. That's our hope. And I have lots of people to thank, all the past and present students, IIT Madras, IIT Jammu, all the funding agencies, government, industries, ever grateful to my team and very many people who have always supported research and especially science in India. My deep respects and tribute to all the three, and to a big thank you to the organizers for thinking of me. The person from Bimlesh, from Shivnara who called me the other day, I really thank you, and Professor Kasturi, who's been really very nice about the whole thing. Thank you ever so much for your attention, and I'll be ready to take any questions. Thanks a lot. Yep.
Thank you very much for an excellent talk. We have to now jump to the third talk, which is the Kamala Sohoni, who was first Indian woman. And this talk is scalable ultra-thin CDA/CDT photovoltaic device. I found Professor Sheila Ramsesha actually tapping the table because she has been patiently waiting in the side screen. She is a graduate from Bangalore University, postgraduate from Bangalore University, PhD from IISc, undergrad Professor Sienna Rao, and her specialty is electronic and magnetic properties of low-dimensional materials. She is a postdoctoral fellow in the Oxford University, UK, and Princeton University, USA. And in IISc, she has worked in aerospace lab, high-pressure studies of electrical and structural transformation in solids, high-pressure, high-temperature synthesis of molybdenum disilicide for high-temperature application, solid oxide fuel cells, and so on and so forth. And she has more than 100 publications with 6 patents. So without waiting further, I call upon Professor Sheila Ramsesha to deliver a talk.
I think Professor Chadha has to, remove the presentation.
Yes. Anjuji, please remove the presentation.
Present. Okay.
Professor Chadha, please remove your presentation. Yeah. It's
okay.
fine.
Yes, okay. Thank you very much, Professor Tulsi, for the kind introduction. And at the outset, let me thank Professor Chittaranjan Sinha and Professor Kasturi Mukhopadhyay for this invite. And of course, Asima Chatterjee, Rosalind Franklin, and Kamala Sohoni have been pioneers in their respective fields. And it is women like these that paved way to women like us to pursue a career in science. So, it's a big salute to all these great women, who have contributed so much and sacrificed so much in their lives. Okay, now without spending much time, because we are already running behind schedule, let me start my talk. Okay, I'm going to talk about scalable ultra-thin cadmium sulfide, cadmium telluride photovoltaic device, because in recent times, the renewable energies and green energy has been in big emphasis. And then let me start with the little work we have done on this. So the outline of the talk is going to be motivation for the project, aim of the project, and of course, the methods and materials, results and conclusion. Okay, the motivation basically is that around the world, the electricity generation has been increasing, ever since the industrial times, and in recent times, it is just going sky high. So with the electricity generation, because coal is mostly used for generating electricity, the carbon dioxide emission has also gone up tremendously. So, of course, 2020 was a very unusual year where we saw a dip in the carbon dioxide emission. That's because of various other reasons, not because of the development or industrialization. So now, because carbon dioxide is a greenhouse gas and it kind of absorbs heat from the earth and releases back to the earth, and it has lots of other.
Sorry, Professor Sheila, sorry to interrupt you. Like I'm still on the slide 1. Is it others also, or is it on me?
Are you moving? We are not moving?
No.
It's electricity generation part?
No, it is not moving, madam. It is not moving.
We are at the scalable ultra thin, the title slide.
Oh, no.
Only title we can see.
Oh, no. Okay. Let me then do it slightly differently. A tab. Okay, let me do share. No, I can't do that. Intro. Now, can you see?
Yes. Can you please take it on the presentation mode?
Yeah, I've taken it on the presentation mode.
Okay. So,
It's not coming?
no, we can go ahead with this one. At least this is visible.
One second. Let me just correct it. No, it has to be. It has to go in this mode. Okay. No, I'm sorry. I just have to do it that way. Okay.
Fine. The previous one was fine. Yeah. You go ahead. Yeah.
Okay, see that, but the slides keep moving. That much you check.
Yeah.
Now, are you seeing anything?
It's coming.
No, it's blank.
Yeah, it's not coming. Yeah.
No, anyway, I'm sorry. I'll just try to do what best I can. Okay.
Yes, we can see it. Yeah.
Okay, so this is the motivation. Okay, so let me go to the next slide. Yeah, I'm sitting in the US and I'm trying to make a presentation. No, it's not.
We were able to see the previous mode.
Try. It will happen. Try. It will happen.
Okay, okay. We'll just try to do what best we can. Huh?
Yes.
Window, it doesn't work with Windows. So let me do the full screen itself. Can you see now?
Yes,
it has come.
Yeah.
Okay, thank you. All right. Electricity, because of the electricity generation, we are focusing a lot on dioxide, and we know carbon dioxide is a greenhouse gas, and it kind of absorbs a lot of heat from the earth and then releases back to the earth, and so because of that, we end up with global warming, and carbon dioxide does not go away even for 100 years. So now, can you see?
Yes, we can see. Yes, we can see.
Okay, the new one. Okay, so now the global warming projections, from different sources, from different centers around the world, have given something like, some of them even go up to 5 degrees increase from pre-industrial period by 2100. But the COP26, recently held in Glasgow, they wanted to restrict it to 1.5. So now, how are we going to do that? And this is India at night. Even in India, the power consumption has been going up quite steadily. If you see the night picture of India in 2016, compare it with 2012, you can see so many more lights, and lights is just one of the factors. The number of industries that are running, the number of small scale industries, large scale industries, the cottage industries, everywhere, power is being consumed. So just even looking at the lights, we have increased our consumption quite a bit. Now, electricity generation in India, this is the 2019 scenario. I did not want to bring in 2020 because it was a very unusual year. So you see that 76% of the power consumed in India is generated from coal, and very small amount by other resources. So now coal means a lot of carbon dioxide, sulfur dioxide, whatever you can think of, all the muck that comes in, along with all the carbon fine particles and things like that. So it's not a very clean way of generating electricity anyway. So now what can we do? We have to reduce the carbon footprint, and then we have to use more of renewable energy resources. And the best way to do it is use all the surfaces of a building to generate electricity. So now the focus here is that if we can convert these skylights and the windows into electricity generation devices, then what happens? Okay, so that is the aim of this project. So now solar cells, of course, silicon-based solar cells, they are the workhorses, because everywhere they are setting up only silicon-based solar cells. But then our focus has been on thin films, cadmium telluride and cadmium sulfide. Cadmium telluride has a band gap of about 1.45 eV. Cadmium sulfide has a band gap of 2.4 eV, and this is the solar spectrum that you are seeing on the right side here. and cadmium sulfide, has absorption in the very peak of the solar spectrum. Cadmium telluride is also not so bad. Compared to silicon, these are very good materials. These are direct band gap materials. So these are good systems to use. Now, even the silicon solar cells or the gallium arsenide, which are very high efficiency ones, they use very expensive processes like sputtering and closed cycle sublimation, thermal or e-beam evaporation, and then so they are highly expensive, and they require very high vacuums, and so because of that, the size of the solar cell is restricted. Now, if you're looking at silicon single crystal solar cells, the growing of single crystal solar cells is very challenging because you do not want any impurities in the silicon, and you do not want any defects in the cell because the bubbling and lot of other efforts are involved. And in India, we do not grow single crystal silicon in the country. So now that's the reason why we went for chemical bath deposition. Now this is a simple process. It does not require very expensive equipment. It is very cost effective, and large area deposition is possible, and it is scalable, and multiple samples can be deposited simultaneously. Now if we go into the actual cell configuration has a substrate and it has a back contact, and then we have the p-type conductor, we have the n-type conductor, and that's where the p-n junction comes into picture, and then we have the top contact, and then that is connected to the power supply. Now the method we have developed is something very simple. All it requires is a beaker, okay, which is temperature controlled in a bath, and then solutions. That's all, right? Now to deposit cadmium telluride, we require a thermostat of 92 degrees centigrade, which is maintained at 92 degrees centigrade. And this cadmium acetate is the source for cadmium, and tellurium dioxide is the source for tellurium. Of course, being chemists, we all know that TiO2 does not dissolve in water, so you require some amount of acid in it. And then, we have to control the pH for proper precipitation. And then, once it starts precipitating, it deposits on the ITO coated glass. ITO is the back contact here. Okay, so now we have deposited cadmium telluride. Of course, after deposition, because the deposition is through precipitation, it is amorphous. But then, we have to do a small heat treatment so that, it crystallizes. And once it crystallizes, the area shrinks. So because lots of gaps open up, and then, you have to redeposit again. So, 2 or 3 layers of cadmium tellurides have to be deposited, one on top of the other. And then, we go into the deposition of cadmium sulfide. So it's again a similar process. It's just the solution chemistry that we have to worry about, and then the temperature control in the bath. So cadmium sulfide can be deposited at 80 degrees centigrade. And again, cadmium acetate is the source for cadmium, and thiourea is the source for sulfur. Now, after depositing the cadmium sulfide, again, you have to do the temperature annealing, and then you deposit the top electrode, and then you do the device testing. So it's as simple as that. Now here, you can see that the leftmost is plain ITO glass, The top right is after deposition of cadmium telluride before annealing, and then the right one is the lower left one is cadmium sulfide, just cadmium sulfide deposited, and then the bottommost is the thin film device. That is, we have both cadmium telluride and cadmium sulfide layers on it. So you can see that it is absolutely transparent. So now if you look at the XRD and microstructural analysis, yes, and then the cross-sectional SEM of the device, you can see the cadmium sulfide, cadmium telluride and ITO layers very clearly. And then of course the AFM, this thing. And this is the top surface of the SEM of the top surface. So you can see nice crystallites. Now optical and electrical characterization. Of course, cadmium sulfide band gap is very clearly visible here. And then the cadmium telluride band gap is very clearly visible here. And suppose we look at the transmittance, you see the absorption is hardly 15% from the ITO. I mean, after the ITO of course, absorbs about, it absorbs about 15%. And then our device absorbs about 15%. So now, and then of course, we have done the IV curves and then, the semi-log plot to get the ideality factor, etc., etc. And then the quantum efficiencies. And then, this is through the device, the IAC tower. I mean, this is absolutely transparent, and then, this can be used for the windows, right? But only problem is that, most of the windows these days have the 3M films, which are bluish in color. This will be yellowish in color, yellowish or brownish in color. So one has to get used to that color difference, and then, it should be fine. And here are, number of devices that we have made. Is the slide visible? Hello?
Yes, it is visible.
The VOC and JSC?
Yes.
Yeah, okay. So here, we have given the VOC and, the current density for various devices that we have made, and some of them are extremely good, some of them are not so good, but that depends on control of the process. And so far, until I left, we were able to achieve about 2% efficiency with 15% absorption. So that is the key factor there, and it can be improved further. So if any chemist in the audience is interested in it, I can share the information and they can continue with the work. Now, another thing that we did was setting up a solar plant on top of the library, IAC main library. And then this, the power generated from here was connected to the central tower building, the central office where, you have all this administration block. And this project was done under MNRE. That's the Ministry of New and Renewable Energy Resources. And so, we generated quite a lot of power, and then about 15% of the power consumed in the central office came from our plant. It's only a 20 kilowatt plant, but still, it was able to supply 15%. Now, another project we did was on putting solar panels on a moving train. This is a Shatabdi Express, which runs from Chennai to Coimbatore. and it moves at tremendous speed, about 120 miles per, 120 kilometers per hour speed at times. And so, it was an engineering challenge to hold the solar panels in place during this, all the turns and things. And and there was a lot of friction, going on. So in spite of all that, we were able to achieve this the experiment and then get a lot of data. And of course, Ministry of Railways has taken up this work, and they are trying to do this. Okay, so in conclusion, a simple and cost-effective process for fabricating solar cells is developed. The parameters are optimized, and then the structural and optical and electrical characterization are carried out. So, and then I would like to thank Dibecha Center for supporting this research, and my students Nityayani, Amrita, and Shravant and Vashishta for supporting the work. Thank you very much.
Thank you, Professor Sheila. Very good talk and in time. Now we go to the fourth and last lecture, covered lecture, which will be given by Shamita Basu. She has retired from Saha Institute of Nuclear Physics, but still teaching in several institutes. She is a graduate and postgraduate from Calcutta University, PhD from Jadavpur University, under the guidance of famous Professor Mihir Chaudhuri in spectroscopy. Incidentally, I always claim I am the first student of Professor Mihir Chaudhuri. When he came back from University of California, our batch was the first one he taught, and since I stood first in that, so I always claim I am the first student, and Professor Chaudhuri, we call him Mihirda, he never objected. Shomita is of course my junior. Then she joined St. Xavier's College, then SINP in 1992, retired in 2018. She is an authority in photochemistry and spin chemistry, particularly the photo-induced electron transfer reactions and magnetic field effect. And this is the very title of her topic today. She has 16 PhD students and 150 papers behind her. Shamita, all yours.
Yes, thank you. Can you hear me, Tulshita?
Pardon?
Can you listen to me? Can you?
Oh, sure,
am I audible?
Yes.
Okay. Perfectly. Go ahead.
Okay. Now, good evening to all. Now, it is my. Shall I make this screen this size, or I will make it full screen?
Make it full screen then, if
full
you
screen,
can.
that is better. If you cannot,
if you can. We can say it, yeah.
Yes, I can do it. Okay. So, good evening to all. Now, it is my privilege, and I am feeling honored to have this award from Indian Chemical Society. And this is the second time I am receiving awards from this society. However, this time I know Professor Rohatgi Mukherjee very well. Okay. When I worked at Indian Association for the Cultivation of Science, I met her at Jadavpur University. And I was very much impressed by her soft and kind attitude towards students and her elegance as well as modesty. Okay. And I like to thank the organizers, especially Professor Kosturi Mukhopadhyay and Professor Chanda Mukhopadhyay, for giving me this opportunity to share our work in this session. Okay? And however, I must thank my students, because this award is for their hard and sincere work, motivation, and deep knowledge in chemistry and allied subjects. Okay? Now, in our MSc classes, Professor Mihir Chaudhuri, later he was my PhD supervisor, sir, taught us photochemistry. Okay? And at that time, he referred a book, and that is on fundamentals of photochemistry.
And that book was written by Professor K.K. Rohadke Mukherjee. That book was excellent book, and the striking feature of that book is that each chapter contains a summary at the end, and that was very much useful for us. Okay, and you see on the front page of this book, there is a Sanskrit sloka, and the meaning of that sloka in English is that all that exists was born from the sun. Okay, and this is the logo of Indian Photobiology Society, and she was the founder secretary.
Sumita, your slides are not moving. You are on the first slide.
Okay.
Yeah, please. Yeah, go to the second slide. Yeah.
So this one, this is the second slide. Okay. Can you see it? Oh, Suri?
Yeah. Yes, you can see now. Yes.
So this is the logo of Indian Photobiology Society, and you see, she was the founder secretary of this Photobiology Society. And the meaning of the sloka is that all that exists was born from the sun. Actually, these photosciences are executed just by absorbing light with the wavelength within the wavelength region of the electromagnetic spectrum of sun. And the best example of this photochemistry is the photosynthesis. Okay? Now, what is the basic mechanism of that process? It is electronic transition from the highest occupied molecular orbital to lowest unoccupied molecular orbital of a molecule just by absorbing light. And the whole process can be explained by this simple Jablonski diagram. You can see that most of the molecules remains in the ground singlet state. That means two electrons have spin orientations in the HOMO as antiparallel. Okay. Now on photoexcitations, the molecules are going to the excited states and they are coming back to the ground state either by non-radiative internal conversion or by radiative fluorescence. On the other hand, they can get their corresponding triplet configurations where three states are have same energy, okay, and the total spin angular momentum is equal to 1, whereas in case of singlet, total spin angular momentum is equal to 0. And these triplet species are non-fluorescent, so from there the molecules are going coming back to the ground state either by non-radiative intersystem crossing or by radiative phosphorescence. Now, if we really want to study the excited state property, then we must have two basic instruments, and those are absorption and fluorescence spectrophotometers. And if we want to characterize the non-fluorescent transients, that means short-lived species, we have to use transient absorption technique, and that is laser flash photolysis. And we have detected the fluorescent transients just by using this time correlated single photon counting kinetic spectrometer or femtosecond up conversion. Okay. And next, you can see this is the schematic diagram of the laser flash photolysis instruments. Okay. Here we are using different harmonics of NdArc laser to excite the molecules from the ground singlet to higher singlet states, and from there by non-radiative process triplet species are formed, or we can their radical or radical ions may also form, and these non-fluorescent species are probed by pulse xenon lamp. Okay. Now, when we did our magnetic field effect experiments, a pair of Helmholtz coil was placed inside the sample chamber, which can produce a DC magnetic field of the order of 0.08 Tesla. That means 800 Gauss. Okay. Now, from the laser flash photolysis study, we can measure the average lifetime of the transient at a particular wavelength from the decay profile. And we can also have the spectrum of the transient non-fluorescent transients just after a particular time delay after laser flash. Okay. Now, you can see that these photo-induced chemical and biological phenomena, they involve electron transfer, hydrogen abstractions, proton bond cleavage, like that. And in all these processes, you can see these radical ion pairs or radical pairs are formed. Okay. And those reactions, mainly the photo-induced electron transfer reactions.
Somebody is presenting why the slides has changed. Is it with me only? Monindra Bera
Yes.
is presenting.
Monindra Bera? Who
I
is
don't
that?
know. I don't know. I'm just.
No,
Is it-
I am presenting. I am
Yeah, but
presenting.
I know. Some different slides came. Maybe it's yeah. Now you present, yeah. Yeah,
Okay,
it's
now
fine.
this is fine now? Okay. Now these photo-induced electron transfer reactions depend on structure of molecules, nature of solvents, and spin state of the chromophore in the excited state. Now, this is the schematic, this is the mechanism of photo-induced electron transfer reactions where either donor or acceptor molecules are excited. Donor means they are rich in electron and they can donate electron to the molecule which has deficiency in electrons. And this type of radical ion pairs are formed, and these radical ion pairs are also termed as exciplex, and they can either undergo back electron transfer for recombination products, and or they can form these free ions which are highly reactive. Okay. Now, to study how how the structure of the molecules can modulate the reaction pathways. Okay, so we have selected different derivatives of carbazole which act as electron donor as well as chromophore, and different derivatives of cyanobenzene which act as electron acceptor and fluorescence quencher. Okay, now in case of N-ethyl carbazole and 1,4-dicyanobenzene, you can see exciplex is formed. Okay, however, in case of pentamethyl carbazole tetracyanobenzene, you can see this, we cannot find any exciplex formations. We can see only the radical ions are formed, and we have detected those radical ions in 10% SDS micellar medium. Now we have interpreted the result as such that in case of ethyl carbazole diacyanobenzene, the electron transfer takes place with singlet chromophore, whereas in case of pentamethyl carbazole diacyanobenzene or tetracyanobenzene, this electron transfer occurs in the triplet states. Okay, but we have to prove that. Now, before proving this thing, I want to show you a couple of slides. You see, these geminate solvent separated ion pairs are the primary products of photo-induced electron transfer reactions. Now, in non-polar medium, they will form this contact ion pair or exciplex, whereas in polar medium, they will form these free ions as escape products. Now, the spin correlations of these SSIPs is also very important. If initial electron transfer occurs in singlet state, then the spin correlations of these two unpaired electrons will be singlet. That means two spins are anti-parallel, total spin angular momentum is equal to 0. And this singlet spin correlated radical ion pair will form contact ion pair or exciplex rather than free ions. Now, if prior to electron transfer, if intersystem crossing takes place.
Shomita di, unmute. Just got muted. Shomita di, you unmute. You unmute.
This one?
Yes.
This is
yes,
okay?
It's fine. Yeah.
Now I have to share it again, no?
It's fine.
But I cannot see. I cannot see.
Oh, but I can see your slides.
We can see your slides.
Yes, we can see your slides.
Cannot.
Maybe you go to your presentation.
Yes, I am.
You go to. We can see.
I am stop sharing. I am.
Okay.
I am again sharing it. Okay.
Yeah. No problem.
Okay. So prior to electron transfer,
yes.
Again problem. Can you see?
It's coming. Yes.
Is there now?
Electron transfer. If intersystem crossing takes place, then that electron transfer will occur with the triplet species, and the spin correlation will be triplet, that means parallel spins. Two unpaired electrons will have parallel spins, and the total spin angular momentum is equal to 1, and that SSIP will form free ions rather than exciplex as recombination product. Okay. Now, irrespective of formation of solvent separated ion pair with singlet or triplet spin configuration, there will be an interconversion between these two in presence of hyperfine interaction, that means coupling between electron and nuclear spin present in the system. And this type of interconversion will be maximum when the separation distance between these radical ions will be as such, where exchange interaction energy between these two electrons becomes negligible. And at that point, the energy state of singlet and these three triplet states will be same. Okay. Now, in that case, we will have maximum intersystem crossing. Now, here, if we apply an external magnetic field of the order of hyperfine interactions, then you can see these triplet states become non-degenerate, okay, due to Zeeman splitting. And this singlet to triplet interconversion will be reduced. So if initial radical ion pairs are formed in singlet state, then in presence of magnetic field, singlet yield, that means exciplex luminescence will increase. And on the other hand, if initial radical ion formation occurs in the triplet state, then in the presence of magnetic field, triplet yield or free ion formation will increase. Now you can see that in case of ethyl carbazole dicyanobenzen, in the presence of magnetic field, the exciplex formation increases. So we can say that here initial electron transfer occurs in singlet spin state. However, in case of pentamethyl carbazole dicyanobenzen or tetracyanobenzen, radical ion formation increases in presence of magnetic field, which tells that here electron transfer occurs with triplet chromophore. Okay, so magnetic field effect is a very nice tool to identify the initial spin state of the electron transfer process, and that will modulate the reaction pathways. Okay, and another thing is that it can help to assess the interradical distance where exchange interaction becomes negligible and we can have maximum field effect. Now we have studied many systems and we have found that key factors for magnetodynamic behavior are solvent dielectric, exciplex energy, and steric bulk present on donor or acceptor, regulating the optimum interradical distance. Now we have shifted to another system, that is phenazine, and these aromatic amines DMA, DMDPM, and aliphatic amine, this triethylamine, this is quite soluble in water. And here also electron transfer occurs in triplet state, and we can see nice magnetic field effect in 10% SDS micellar medium. But when we use this molecule, this dibenzoaciphenazine, which is an efficient hydrogen bonding probe, unlike its parent phenazine molecule, we can see that this molecule can undergo electron transfer with these amines. However, we can see magnetic field effect in homogeneous acetonitrile water mixture instead of SDS micelles, where micellar cage can provide sufficient space for separation of component to make exchange negligible and the lifetime of the transients increases. Okay. Now, you can see that DBPZ, DMA, DMDPM system, in presence of magnetic field, the increase in ion and charge transfer complex are happening. Whereas in case of triethylamine and DBPZ, electron transfer, due to electron transfer, we cannot identify the radical ions. We can identify only the charge transfer complex in the triplet state. Now, we have inferred the result as such. Here we can see magnetic field effect in homogeneous acetonitrile water mixture, because here the optimum separation distance between DBPZ and DMA is maintained by the intervening water molecules through hydrogen bonding. Okay. Now we have to prove that again. Now there is another parameter which is called BHAP. BHAP is a measure of hyperfine interaction present in the system, and that is the field at which half the saturation of the effect reaches. Now theoretically we can calculate the BHAP values from these hyperfine interaction constants and nuclear spin. We always think that experimental BHAP should be very close to calculated BHAP. However, you will see that in most of the cases, experimental BHAP is far greater than the calculated BHAP, because we always take quencher concentration much more than the chromophore concentration. Here, DMA concentration is much more than the DBPZ concentration. So after electron transfer, electron will hop from one donor to another donor, and so it will induce lifetime shortening and energy level broadening. So excess magnetic field will require to overcome the hyperfine interaction. Okay, so experimental BHAP value will be greater than the calculated BHAP values. However, there are some cases where this optimum separation distance cannot be reached. And so due to the presence of super exchange, that means where J is not negligible, their experimental BHAP value is lesser than the calculated BHAP. Now you can see in case of DBPZ TEA system, where we can observe only the formation of charge transfer complex, since TA is soluble in water, it can come closer to this DBPZ. And so here, this optimum separation distance to make exchange negligible cannot be reached. So due to super exchange, here experimental BHAP value is lesser than the calculated BHAP value. Okay. Now, next we have changed our system to the molecules which have some biological relevance, and we have studied the interactions between menadione and anti-cancer drug with DNA bases like adenine, adenosine, etc. And we have observed that here electron transfer occurs in acetonitrile medium, but there is no magnetic field effect. Okay. However, when those molecules are caged in micellar medium, you see hydrogen abstraction takes place. Okay. Why? Because menadione and adenosine or adenine, they remain in the hydrophobic region of the micelles, and their hydrogen bonding is facilitated, which makes hydrogen abstraction. Okay. Now later we have extended these studies with another quinone derivatives, 19 antaquinone, and all the DNA bases, they are nucleosides and nucleotides, and we can have this table. Okay. And we have also tried to see how metallointercalators can undergo electron transfer reaction with DNA. So this is the copper phenanthroline or tyrosine tryptophan substituted copper phenanthroline metallointercalator, and this is the cup thymase DNA, and from guanine electron is being transferred from guanine to the metal centers. Okay. And here also we can see very an appreciable amount of magnetic field effect in homogeneous buffer medium. Now why we can see that? Because you see these metallointercalators are non-planar in nature. So after electron transfer, they can manage the optimum separation distance just by hydrophobic and electrostatic interactions. Okay. And now this observation was also obtained with the pyrrole copper sheet base complexes, and this is the methyl unsubstituted pyrrole complex. It is termed as CuL2, and there is another pyrrole complex, methyl substituted pyrrole complex, that is CuL4. Okay, and this CuL2, that means methyl unsubstituted one, is much more planar than this CuL4, that means methyl substituted one. And so this CuL2 can cleave DNA much more than this CuL4. So in case of CuL4, due to this non-coplanarity with DNA, it shows better electron transfer and magnetic field effect. However, when we have measured the BHAP values, the increase in experimental BHAP compared to calculated BHAP is greater in case of CuL2 than that in CuL4. And that is because you see CuL2, that means methyl unsubstituted one, can intercalate DNA much more than the CuL4. So their interstrand hopping is far greater than the interstrand super exchange. Whereas in case of CuL4, both interstrand hopping and negative interstrand super exchange exists, which makes the experimental behalf, increase in experimental behalf lesser than the calculated behalf compared to the CuL2 system. Now, similar type of things, that means determination of optimum separation distance between donor and acceptor can be obtained in case of drug-protein interactions. When menadine interacts with lysozyme, you can see the distance between them is around 2 to 3 angstrom. Here we can see electron transfer, but not any magnetic field effect. However, in case of proflavin, acridin, ALO, when they are interacting with this human serum albumin, in that case, the interradical distance is around, say, 12 to 13 angstrom. Here we can see appreciable amount of electron transfer as well as magnetic field effect. Now, very recently, we have synthesized luminescent carbon dots, and these luminescent carbon dots are aminated, and these aminated carbon dots are linked with menadine directly, and in another case this is linked with menadine with some spacer, that is homocysteine thiolactone. Okay. And the donor acceptor distance between the distance between this donor and acceptor for the first one is around 6.5 angstrom, and for the second one, that is 13.2 angstrom. So this one, that means where the separation distance is around 13.2 angstrom, here we can observe very nice magnetic field effect as well as electron transfer and magnetic field effect. And appreciable amount of electron transfer we can see with this compound. Okay. And so this compound can be used as a very good quinone sensor to estimate excess quinone in the cell. Okay. And very recently, we have reported that the presence of these nanoparticles can change the reaction pathways. I have already discussed the reaction pathways of menadine while interacting with adenine or adenosine. Now, in presence of gold nanoparticle, the reaction mechanism is hydrogen abstraction. But when we have used iron nanoparticle, the reaction mechanism becomes electron transfer. And similarly, just by changing the nature of micellar medium, that means just by using cationic CTAB micelle, we can have electron transfer with menadine and carbon dots, and not this hydrogen abstraction reaction, which we found in case of SDS micellar medium. So you can see that this magnetic field effect, really it is a very nice tool to modulate the reaction pathways of the photoinduced electron transfer reaction. It tells that triplet chromophore can be used to increase the free ion formation compared to the recombination product, and also it will assess the separation distance. That means it can act as a ruler to measure the separation distance between donor and acceptor, and it would be very much useful for biomacromolecules or for larger systems. Okay. Lastly, I like to thank all of my collaborators. Professor D.N. Nath of Indian Association for the Cultivation of Science. He helped me a lot at the beginning of our work in functioning the laser flash photolysis setup and magnetic field effect setup. And I like to thank Chitra Raha. She helped all of my students in laser flash photolysis experiments, and Ajay Das and Tapun Pai for instrumentation. And for synthesis, Manush Kutti, Professor Enak Kamani, Dr. Kallol Bera. I am thankful to them. And for theoretical modeling, Professor Dhananjay Bhattacharya, Professor Shagota Dasgupta, Dr. Uttam Pal, and Dr. Uttam Pal is still helping our students in molecular dynamic calculations. And for biological studies, I'd like to thank Professor Partho Shah, Dr. Vaishi Chakraborty, Dr. Chondima Das, and for nanomaterials, Professor Vishnu Satpathy, Dr. Dulal Senapati, and Dr. Arnav Maiti of Akal University, Punjab. He helped me when he was one of the research associates in our department. And I should acknowledge all the members of Chemical Sciences Division of Shah Institute of Nuclear Physics, and obviously for FANNI, Department of Atomic Energy. Lastly, I am showing the photographs of all my students, you see, and they are established more or less. And lastly, I like to thank for your kind patience. Okay.
Thank you,
Thank you,
Shamita.
Shamita, for a beautiful talk. Thank you.
Thank you, Shamita. And
Thank you.
this brings us to the end of the fourth lecture. I will end by one small anecdote. Professor Rohadgi Mukherjee taught us photochemistry immediately after her marriage. She became from Rohadgi to Rohadgi Mukherjee. And I was her very favorite student. I visited her several times. And not a single time she uttered my name correctly. My name was always top on to her. Then I had to point out. And secondly, unfortunately, we have overrun a little bit because the number of slides were too much. And there was also technical problem. But still, I will say it is a very successful session. And I thank all the 4 speakers and the organizers for giving me this chance. Thank you very much.
Thank you.
Thank you.
Professor, if I can make a small quip, since you said your mentor was a photochemist and she would mispronounce your name, maybe she was seeing things in a different light, pun intended.
Yeah, I think we are, in the end of this session, Ashima Chatterjee special scientific session, and I'm kind of emotional and overwhelmed. Like what an incredible session we had, and I like to take this opportunity actually to give the vote of thanks and to thank all of you for successfully completion of this session and giving tribute to our legendary scientist, Professor Ashima Chatterjee. And in this event, I'm taking the opportunity like to thank Professor G.D. Jadhav, President, Indian Chemical Society, and Professor Dulal Mukherjee, because both of them actually proposed this special session, which is dedicated to our legendary scientist, Professor Ashima Chatterjee. Thank you, sir. And I like to thank Professor Chittaranjan Sinha too for believing in me. When he called me, I was kind of overwhelmed that whether I'll be able to do this job. But at every step, he helped me in such a way. Thank you, sir, for all your help. And now like to thank our team members, Professor Chanda Mukhopadhyay and Professor Bimlesh. It's such a, to work with you, it is such a effortless. Thank you so much. And a great applause and big thank to our both chairperson, Professor Reena Ghosh and Professor Tulsi Mukherjee, for gracefully conducting the meeting. Thank you, sir, for accepting the invitation and for your valuable time. My heart now fills with lots of gratitude and respect for our distinguished speaker for not only sparing your invaluable time to grace the occasion, but also enlightening us with a commendable talk on the subject. To the award recipients, I bow down my head for your dedication to the science. You are inspired. You are really inspired to us, to all the young members, and you have indeed put your whole best efforts to make this event unforgettable. We really owe you a lot. And in this particular, I'd like to mention Professor Bani Talapatru. Madam, the way you presented, you shared your personal things of the Ashima Chatterjee. We really feel emotional, and I'm feeling, so happy that I am a part of this. And least but not, I'm actually trying, as we are getting very late, so I'm trying to finish it. And lastly but not least, I like to thank the organizer and also the audience, and particularly and also the participants. And another person I like to mention, Dr. Rahul Bhattacharya. That the way he helped me, I don't know how come, he picked up the phone in the first ring. So I like to thank from my bottom of the heart, Dr. Rahul, and I like to thank all the audience and the participants still we are 43, still we are this audience is full, and I feel energetic that in such a way that Ashima Chatterjee special session has been ended in such a nice way. And so I thank for the grand success of this event, and thank you one and to all. Thank you so much for this session. Now I like to hand the this mic to Professor Chittaranjan Sinha.
Professor Kasturi, is it possible to take
wonderful Professor Mukhopadhyay, Kasturi Mukhopadhyay, Chanda Mukhopadhyay, and Professor Dimlesh Locha for your wonderful management for this session, and the speakers like Professor Sharmila Banerjee, Professor Unji Janda, Professor Sila Ramsesa, and Professor Sumita Basu, along with the remembrance of Professor Ashima Chatterjee and the speakers like Akhilesh Verma, Ramses, Madam Banidi. So you have the wonderful contribution. Although we are 1 hour late, but it is not the late. Rather, we learn many things from our speakers, and it is in fact, in our council meeting, we have decided extra session for the women scientists, but it is not that. In fact, Dr. Kasturi objected it should not be in the name of women scientist session. It should be in the name of some other scientist. That's why we have selected in the Ashima Chatterjee, our master from University of Calcutta and first DSC of the country, the DDSC. Okay, now we are switching over to
Professor Sinha. Sorry to interrupt.
Our chair, Professor Tapas Chakraborty, he is with us. Professor Tapas Chakraborty, now the director of Indian Association for the Cultivation of Science, and he is a well-known figure in the chemistry. So he needs not do any introduction for Tapas Babu. So I do request Professor Tapas Chakraborty to chair the session of Lifetime Achievement Awardee speech Professor Aurobindo Kumar Das. So I just request Professor Tapas Chakraborty to conduct the session. Professor Aurobindo Kumar Das.
I request like all the awardees, we can take a click on the screen.
Yes, all the, so that we can take a picture.
Yes.
All the awardees,
Yes, please.
Please, take your, video on. Shomita Di? Professor, I think Professor Anju has left. Professor Anju has, I think Professor Chada has left. Dr. Vimlesh,
Okay, so we can still click. It's possible.
Vimlesh, you also come to video.
And kindly send us a copy of this picture.
My screen is not working. Anyway, it's
Okay.
good to see you all together. So I'm just taking a click. Yeah.
Yeah, Professor Sinha, can I start?
Yes.
Just wait,
Please go ahead.
Professor Chakraborty, just
Yes.
wait.
Okay, the photograph session, the photo session, fine.
One photo session. Professor.
So I have taken. Yes.
তাপস কেমন আছো তাপস?
হ্যাঁ স্যার আমি ঠিক আছি একদম।
Thank you.
Thank you. Thank you. Thank you very much.
Please
Thank
send
you.
us the picture.
Okay.
Please send
I
us
think
the
this,
picture.
I hope that I can now start. And thank you very much, Professor Sinha. And I am extremely happy to get this present responsibility to introduce today's evening speaker. And for this Lifetime Achievement Award of this Indian Chemical Society 2021. And this award is going to Professor Aurobindo Kumar Das. So let me briefly introduce Professor Das to this audience for this evening lecture. Professor Aurobindo Kumar Das had received his undergraduate and master's degree at the Calcutta University. And he did his PhD from Jadavpur University, and he was a teaching and research associate at this Ohio State University in America, and visiting researchers at this University of this Valencia in Spain. Professor Das has made significant contributions to the metal-ion speciation in diverse matrices, correlation of the stress metal variations upon low-dose radiation on human, low-cost methodology for arsenic and other heavy metal removal from the drinking water. Professor Das was the pioneer in introducing this environmental chemistry and also this green chemistry at the postgraduate level studies. He has rendered remarkable services at this University of Kalyani, West Bengal, as the Vice Chancellor during 2004 to 2009. And as a researcher, he has published more than 175 original papers, review articles, invited articles. And Professor Das is the author and this co-author of the dozen of these higher level books on bioinorganic chemistry and the green chemistry. He is an activist of the People's Science Movement and wrote numerous articles on popular science. For his contribution, Professor Das was elected life member of this Indian Chemical Society, honorary fellow of the West Bengal Academy of Sciences and this Technology. So with this brief introduction, I request Professor Das to deliver his evening lecture. And the title of his lecture is Teaching Green Analytical Chemistry, Methodologies for Green Laboratory Experiment. Professor Das, please.
Very good evening, Professor Chakraborty, for your kind introduction and the August gathering of this seminar. Really, it has been very much pleasant for me to be bestowed upon the Lifetime Achievement Award and the opportunity to deliver this lecture. Now, this particular lecture, I would say that it will be different from the previous lectures because it will be some kind of my experience throughout my life as a teacher because I said strongly that I started my career with teaching environmental chemistry. When I used to teach environmental chemistry, I could show my students the example of air pollution when they are working in the laboratory. But about 4 decades afterwards, when I left the university and I started teaching green chemistry, I could not show my students the example of green laboratory class. So that is the difference. That is the thing which I am going to highlight among the August gathering, because it is the problem throughout my life. I have thought about it, and I would now like to give this thought to the scientist, great scientist of this country and the authorities of Indian Chemical Society, so that at least something can be done where the laboratory environment in the UG and PG classes can be improved, so that the students will not be working under the polluted environment and they are compelled to inhale the gases, or I would say that they will be given some alternative so that they feel that chemistry is not a nuisance subject. Rather, it can also smell good while you are working in the laboratory. So that with this intention, I am presenting this lecture, and I need your kind serious attention so that the can be, please, Professor Sinha, the next one. Next one, please. Yes, for the presentation, next one, yes. So what I would like to say that qualitative and quantitative analysis can be tracked back to old pre-biblical times and have been significant throughout the human history, while nowadays
They are the key to the modern society functioning. This is mainly because environmental pollution is a burning issue and its monitoring is indispensable. Analytical chemistry is an area where efforts have been made for a long time to enhance the analytical characteristics, sensitivity and selectivity for the newly designed methods. But unfortunately, sustainability, safety and environmentally friendly aspects are not important so far. Majority of our colleges, universities not only lack laboratory infrastructure, quality chemicals, funds for running expenditure, etc., but also involve toxic reagent consumption, waste generation, introducing a brick to pollute the environment. Next, please. The green analytical chemistry is one of the frontier areas of analysis of science, which has attracted considerable attention in recent years. The figure on the right, you can find that the evolution of literature on green analytical chemistry from 1995 to 2018. At the moment, there are about 900 publications per year in this active area. The left bottom corner gives the instrumental technique used in green analytical chemistry, where we find that liquid chromatography occupies about 20% of the whole work, whereas molecular spectroscopy occupies 14%, and other instrumental techniques are also there to do the green analytical chemistry. Next, please. Principles of green chemistry well known to everybody, but the green analytical chemistry principle, there are also 12 principles like the green chemistry, but it goes by the mnemonic significance. See on the right, on your right, you can see the significance. So it stands for, S stands for select direct analytical techniques, followed by integrate analytical processes, generate little waste and clean it chemically, never waste energy, integrate automation and minimization, favor renewable reagents, increase safety of operator, carry out in situ measurements, avoid derivatization. Note that sample number and size should be minimum, choose multi-analyte and multi-parameter detection techniques, eliminate or replace toxic reagents. So these are the 12 principles of green analytical chemistry. Next, please. Teaching green analytical chemistry, the challenges. There are a couple of big challenges. We must mention that so that we find some solution. It is a challenge to move from research laboratory and the pages of the journals to the real world, and to integrate the principles of green chemistry and practices of green synthesis and analysis according to university curriculum. Efforts have been made in order to incorporate green chemistry principles to analytical practice, but this brings new challenges, including education and teaching of green analytical chemistry. Greening teaching practices face the challenge of strong theoretical effort together with modification in analytical practices, and this should be started from practical work recommended to students. So that is the biggest challenge, I would think. The challenge today is to establish new objectives without devoting the existing ones. It must convert all teaching materials from the subject and content of the theoretical lessons to the laboratory practices. Another big challenge is to create a team of motivated teachers able to make a tremendous pedagogical effort. That is the lacuna from our part, because we always go by inertia. So we don't like to change our even theoretical topic. So in case of practical, we really little bit reluctant to enter into the laboratory and do the practical seriously, and then to change from old to new. That is really big motivation needed for the teacher. Next, main concept of
teaching green analytical chemistry. The heart of green analytical chemistry beats on 5R, where R is the reduction. The 5 reductions are reduction in resources, reduction in energy, reduction in waste, reduction in risk and threats, reduction in costs. Keeping these 5 in the mind, teaching green analytical chemistry should be focused on the following 5 items. Number 1, use of less toxic solvents and reagents. The student should be given the idea of that. Less power consumption. The experiment should be, practical experiment should be based on that. Reduction and online decontamination of waste, automation and miniaturization. Finally, lower cost of the analytical procedure. Next, please. Integration of strategies for education in green chemistry. There are 3 major points to do that. Higher education has a critical role to play in producing sustainable learners by helping them to understand the connections and interdependence among environment, energy sources, and economy. Education in green chemistry requires initiative consideration of energy efficiency, safer reactions and reagents, catalysis, solvent replacements, minimum steps, alternative feedbacks. According to United Nations Environment Program 2006, a green curriculum must promote initiatives from all education and scientific organizations to review programs and curricula in order to address the challenges of sustainable development, strengthening the role of teachers. Next, please. This is the most important part of my lecture. This is the monograph on green chemistry laboratory experiments. You know that Green Chemistry Task Force Committee, DST, it was established in 2000, in the first decade of 2000, and we know that it consisted of Professor S. Chandrasekharan as the chairman, Professor R. Brakaspati as the member secretary, Professor B.C. Ranu as the monograph committee coordinator, and other learned aid members. In the monograph on the first page, it is written that green chemistry is an essential part of chemistry curriculum. Thus, teaching of green chemistry in classroom and laboratory should go simultaneously. In India, although green chemistry is being taught in few colleges and universities, laboratory experiments remained largely the same, being taught 50 years back. I must add now 10 years. I must say that it is the same thing going on. So 60 years back, the difference, the gap between theory and practice, now the gap has increased between theory and practice. Many of these experiments, particularly involving toxic chemicals like liquid bromine, potassium cyanide, benzene, carbon tetrachloride, are not at all safe to the human health. Thus, a need for monograph with safe green laboratory experiments is felt by academic community. The task force shouldered the responsibility of bringing out that monograph. What was there? Efforts were made to demonstrate green experiment for a reaction already taught in the theory class, including, that is the summary of the monograph, 17 organic preparations, rearrangement and oxidation reactions were there. 5 of them were meant for UG, 12 of them were meant for PG. 4 inorganic preparations were there meant for PG. There were in details the organic and inorganic qualitative analysis for UG. Remember, we all the chemists had a hard time in the undergraduate classes doing the qualitative analysis, and in the postgraduate classes, the qualitative analysis. You know that when we are a student, my three teachers are maybe present here, Professor D.C. Mukherjee, Professor S.K. Talapatra, Professor Bani Talapatra. They may kindly remember that towards the end when we were there, we were the first batch of students where semi-micro qualitative analysis were introduced in the postgraduate level. Professor H.K. Saha, late Professor Saha, was doing our practical, and we heard the name of semi-micro qualitative analysis in our postgraduate classes.